Hi, I'm Brighton Godfrey.
And I'm Ankit Singla.
Welcome to our class on cloud networking.
In this course, we'll learn how networking works inside massive-scale cloud infrastructure, with data centers with tens of thousands of servers connected into a network. Consolidating compute into such large facilities yields benefits from multiplexing. We are sharing the same infrastructure over many different applications. It also yields economies of scale. But what's special about networking in the cloud?
Well, that's a good question. Cloud computing brings new challenges for networking, and that's what we're going to be learning about in this course. To begin with, these networks are huge. Tens of thousands or even over 100,000 servers in the largest data centers today. And the applications that these machines are running are big data processing applications that need much more high-performance connectivity between the servers, not just the occasional communication with the client out to the internet, than in traditional data centers.
So both these challenges, the scale of the network as well as the demands the applications place on them, mean that the traditional techniques for networking clusters just do not work in these settings. So we'll look at the design for the largest data centers today and see how they address these challenges.
We'll see both how servers and switches are connected together into a physical network, and also how we deal with traffic through that network. The network needs to handle traffic demands that vary across time. Further, when such large collections of devices form the infrastructure, failures occur often. They're not just the common case, they're a way of life. So these concerns call for efficient and fault-tolerant traffic engineering.
On top of such infrastructure run a variety of applications, including those for big science, but also pretty much every web application you can think of.
Running these applications requires, as we mentioned, big data processing across machines behind the scenes. But also, they have new kinds of real-time demands driven by interactions with us humans. So whenever you visit a website, that appears to be one interaction from your perspective. But in fact, behind the scenes in a cloud infrastructure, there can be hundreds or even thousands of queries to back-end servers in order to assemble responses and give you the web page that you asked for.
So we'll examine the traffic patterns that the applications create and the challenges that springs for networking in these settings. The diversity and the nature of these traffic patterns is another key difficulty in cloud networking.
To give one example, we're going to learn how TCP's design is pushed to its limits by traffic characteristics in data centers, and how the resulting performance problems are being dealt with today in new ways.
And of course, given that all of this infrastructure is being shared not only across applications, but also in public clouds across multiple paying cloud users, we need isolation across these users and applications, not only in terms of performance, but also in terms of security. This forms another major theme that's different in cloud networking.
We'll learn about addressing this need through network virtualization. Furthermore, with the large number of devices and the dynamic environment of data centers spinning up and down new virtual machines and so on, configuring and managing the network the old-fashioned manual way is error-prone and becomes infeasible. Thus, we're going to discuss architecting networks using software-defined networking, which exposes an abstract, centralized view of the network on top of which network management functions become programmable.
So far, we've been looking at things inside the data center. We'll zoom out later in the course and get a broader perspective. Data centers are, after all, one piece of the picture. Consolidating all of this compute and storage inside data centers also means that we are creating a separation between users and their data and the services they use.
So that physical separation between humans and their compute and data is another key challenge for cloud networks. To deal with this, the largest cloud providers today run multiple data centers across the globe to provide better service to clients in different geographies. So serving clients in Sydney from New York isn't going to cut it. It's too slow, it's not going to be responsive and feel interactive enough, and it will be bandwidth inefficient.
But then, how do we connect these multiple geographically distributed data centers? We need to ensure freshness of data and services across these sites, and that can lead to massive volumes of traffic being moved across data centers over expensive long-haul connectivity. In this course, we look at cutting-edge traffic engineering techniques for efficient use of that expensive bandwidth.
So having that collection of geo-distributed data centers helps, but dozens of data centers might not be enough. We need thousands, tens of thousands of sites to get very close to users. So many cloud services also depend on what are known as content distribution networks, or CDNs, for lowering the distance and thus latency to users. CDNs spread cloud services across the globe, ensuring that most clients are within an acceptable distance or latency to the cloud services. We're going to learn how CDNs work, efficiently distributing content across sites, as well as directing clients to appropriate sites to get their content as quickly as possible.
Nevertheless, while CDNs do help with latency, they do not work for all use cases. For example, with multiplayer online games, users that are geographically widely separated need to be connected at low latency. This is not a scenario in which a CDN will be very helpful.
So we're going to briefly discuss the value of low latency connectivity over the wide area public internet, as well as what's causing the internet's large latencies today.
And if you're wondering what this pigeon is doing here loaded with a USB stick, well, you'll have to wait and find out. Won't want you to miss that, would you?
I wouldn't. Throughout the course, not only will we discuss useful networking techniques, but also the intuition behind them.
We'll see that the cloud setting creates interesting challenges for networking, but also many new opportunities for network design. After all, in these environments, the entire network stack can be managed often by one operator.
As a result, the landscape is changing rapidly. In fact, the vast majority of techniques we'll discuss in this class were invented within the last few years.
And of course, several challenges remain unaddressed, which means that applications must step in to take charge of their performance. One example of this that we'll see in the course is video streaming applications, which must make a careful trade-off between the video quality and the number of pauses they make for buffering.
On all the topics we just mentioned, you'll see us in lectures, but we also have a programming assignment component, where you yourself will manage your own toy network. You'll collect measurements, make observations, and improve performance for applications such as video streaming and memcached by improving a network emulated on your own machine.
The programming assignments are designed to be small, easy, and fun. They do not require much background outside of what is being discussed in this course. Taken together, they require you to fill in 15-20 lines of code, which, if you have programming experience in any language, should take you no more than a few hours. That said, the programming assignment setup also provides opportunities for further tinkering and exploring. In addition, there is a completely optional and ungraded assignment as well, which involves you running a network measurement tool included with the programming assignment setup, which gathers data and helps research on networking. With this data, together we can create a latency atlas of the internet, which we'll share with the class.
Lastly, throughout the course, we're going to enjoy some interviews with leading networking experts involved in the design and architecture and management of big networks and networking applications. These interviews will help cement the concepts we learn, and also give you a peek into the practice of networking at some of the largest services in operation today.
The course website will supplement the in-lecture learnings, and the course forums provide an excellent way to ask us and your fellow students questions and to suggest improvements. We are excited to be teaching this course, and we hope that you'll enjoy it.
Welcome to the class.
In this lesson, we'll examine data center applications and network traffic, and see what this implies for the network's design. Pretty much every popular web application we use today runs on data center networks. Not only do data centers run these applications, but they also run support tasks which make the information available for these applications. For example, if you're thinking of web search, you have to create search indices by collecting data from the web and processing it. So this is something that these data center servers work together on. Such infrastructure also supports big science applications such as climate modeling. All of this creates massive amounts of data being moved around inside data centers. Let's take a slightly closer look at how something like a web search query might work. So I make a search query, it hits a server in a data center. This server might query several other servers, which further might communicate with other servers, and so on. These responses are then collated, and the final search response is sent to me. This kind of a traffic pattern is referred to as scatter-gather or partition aggregate. So you're scattering the requests and then you're gathering the results. For one query, there might be a large number of server-to-server interactions within the data center. If you think this picture is complicated, take a look at this. This is what Bing's query workflow for producing the first page of results for a search query looks like. So the query comes in here at the top. It's split into multiple requests, which further might be split into sub-requests and so on. So you can see the scatter pattern in play here. A server makes several different requests to fulfill the search query. And then you can also see the gather pattern closer to the end of this graph, where the results from multiple different subqueries are gathered and processed together. And in the end, a response is produced, which is sent to the user. The processing of a query can be a multi-stage process, and each step can involve as many as 40 different sub-requests. And this kind of scatter-gather pattern is not exclusive to search. Facebook, for example, also sees several internal requests in processing a user request for a page. Loading one of Facebook's popular pages causes an average of 521 distinct requests on the back end. For the same page, in the 95th percentile, you require 1,740 items to be fetched. So really, inside these web applications, you can make a large number of requests in fulfilling one user request. Further, these data centers also run big data processing tools such as Hadoop, Spark, Triad, databases, which all work to process information and make it available to these web applications. These data processing frameworks can move massive amounts of data around. So what does the actual measured traffic in data centers look like when they're running these applications? The short answer, unfortunately, even though it seems like a cop-out, is it depends on the applications you're running, on the scale you're running them at, and the network's design as well as the design of the applications. But nevertheless, let's take a look at some of the published data. One thing that's unambiguously true is traffic volume inside data centers is growing rapidly and is the majority of traffic that these servers see. The majority of traffic is not to and from the internet, but is rather inside the data center. Here what you're looking at is data from Google showing the traffic generated by their servers in their data centers over a period of time a bit more than 6 years, which is on the x-axis, and on the y-axis is the aggregate traffic volume. The absolute numbers are not available, but over a 6-year period, the data volume grows by 50 times. Google has noted that they see traffic doubling every year. Google's paper is not quite clear about whether this is data center internal traffic only, but Facebook has mentioned that machine-to-machine traffic is several orders of magnitude larger than what goes out to the internet. So really, most of the traffic in these facilities is going to be within the facility as opposed to and from the internet, and it's growing quite rapidly. So what does this traffic look like? One question we might want to have answered is about locality. Do machines communicate with neighboring machines, or is traffic uniformly spread throughout the data center or such? So here we have some data from Facebook that goes some way towards addressing this question. Let's focus on this part of the table where all of Facebook's data center traffic is partitioned by locality, within rack, within a cluster, within a data center, or across data centers. As you can see, roughly 13% of the traffic is within a rack. So these are just machines within the rack talking to each other. A rack might host some tens of machines. For example, 40 machines seems to be quite common. Then we see that there is 58% of traffic which stays within a cluster but not within the rack. So this traffic is across racks within a cluster. Further, 12% of the traffic stays within the data center but is not cluster local. So this is traffic between multiple clusters in the data center. Also interesting is that 18% of the traffic is between data centers. This is actually larger than the rack local traffic. So locality in this workload is not really high. Also worth noting is that Hadoop is the single largest driver of traffic in Facebook data centers. More data on rack locality comes from Google. What you're looking at here is data from 12 blocks of servers. Blocks are groups of racks, so a block might have a few hundred servers. This is a smaller granularity than a cluster, but a larger granularity than a rack. Here what you're looking at in the figure on the right is traffic per block that is leaving for other blocks. So that is non-local traffic. For each of these 12 blocks in the figure, you see that most of the traffic is non-local, so most of the traffic goes to other blocks. Now there are 12 blocks here. If traffic was uniformly distributed, you would see 1/12 of the traffic being local and 11/12, that is roughly 90%, being non-local, which is exactly what this graph shows. Part of this definitely stems from how Google organizes storage. The paper notes that for greater availability, they spread data around different fault domains. So for example, a block might have all its power supply from one source. If that power supply fails, you lose everything in that block. So if data is spread around well over multiple blocks, you might still have the service be available. So this kind of organization is good for availability, but is bad for locality. Another set of measurements comes from Benson et al., who evaluated 3 university clusters, 2 private enterprise networks, and 5 commercial cloud networks. The paper obscures who the cloud provider is, but each of these data centers hosts 10,000 or more servers running applications including web search, and one of the authors works at Microsoft. The university and private data centers have a few hundred to 2,000 servers each, while the cloud data centers here have 10 to 15,000 servers. The cloud data centers 1 through 3 run many applications including web, mail, etc., but cloud 4 and 5 run more MapReduce style workloads. One thing that's worth noticing is the amount of rack locality here is much larger, 70% or so for the cloud data centers, which is very different from what we saw earlier for Google and Facebook measurements. There are many possible reasons for these differences. For one, the workloads might be different. Not even all MapReduce jobs are the same. It's entirely possible that Google and Facebook run large MapReduce tasks which do not fit in a rack, while this mystery data center runs smaller tasks that do fit in a rack, and hence traffic is mostly rack local. There might also just be different ways of organizing storage and compute. There's also a 5-year gap between the publishing of these measurements. Perhaps things are just different now, app sizes might have grown substantially, or people have changed how they do these things. Having looked at locality, let's turn our attention to flow level characteristics. How many flows does a server see concurrently? Facebook's measurements, and I quote here, web servers and cache hosts have hundreds to thousands of concurrent connections. And Hadoop nodes have approximately 25 concurrent connections on average. In contrast, for a 1500 server cluster running Hadoop-style workloads, the numbers are much smaller. 2 servers within a rack and 4 servers outside a rack is the number of correspondents for a server. So a server talks to 6 other servers in the median. Contrast that with the 25 in Facebook's workloads. The only things we can conclude from this, perhaps, are that A, there are differences across applications. So web, servers, caches, and Hadoop all have different numbers of concurrent flows, and also that even all Hadoop workloads are not created the same. So Facebook's Hadoop workloads seem to be different from this mystery data center workload. Another thing we are interested in finding out is what is the arrival rate for flows? How soon do new flows arrive in the system? Facebook's measurements put the median flow inter-arrival time at a server at approximately 2 milliseconds. The mystery cluster has inter-arrival times in tens of milliseconds, so less than a tenth of Facebook's rate. Regardless of the difference in these two measurements, one higher order bit that's worth mentioning here is that at the cluster scale, the flow inter-arrival times would be in the microseconds if you had a 1,000 server cluster, for example. So really, new flows enter the system at a very high frequency as a whole. What about flow sizes? Most Hadoop flows, it seems, are quite small in Facebook's measurement. The median flow is smaller than a kilobyte, and less than 5% of flows exceed a megabyte or last longer than 100 seconds. For caching workloads, most flows are long-lived, but they're bursty internally. So you can think of these as perhaps long-lived TCP connections where you do not want to incur the costs of a TCP handshake and a rate increase due to slow start every time. So you keep the TCP connection alive, but data is only exchanged sporadically. Also of interest are heavy hitters. So are there a small fraction of flows that move most of the bytes? For this set of measurements, the answer seems to be no. Heavy hitters are roughly the same size as the median flow and are not persistent. So some flows which might be moving a large fraction of the bytes now do not continue to be the heavy hitters in the next time interval. These measurements do agree pretty well from the measurements from the 1500 server cluster also running Hadoop, where more than 80% of the servers last less than 10 seconds, but more than 50% of bytes are in flows that are also small or short, less than 25 seconds. Some part of this, in particular the heavy hitters being roughly similar in size to the median flow, stems surely from application-level load balancing. For example, for caching, if you're spreading the load across these different caches, you will see roughly similar flow sizes. So where do we go from here? What does data center traffic look like? We don't have a definitive answer, and right now not a whole lot of data is available. There are, however, some conclusions we can draw from the nature of data center applications as well as the points of agreement of these different data sets. We look at these in detail, but briefly. 1. Data center traffic internally is quite big and increasing. 2. We have very tight deadlines for network I/O, that is, we are targeting small latencies for applications like web search in particular. 3. Because we have a large number of flows, we'll see congestion in the network and problems like TCP incast. 4. We need isolation across multiple applications that are running in these data centers. 5. Centralized control at the flow level might be difficult because of the large flow rates we are seeing. So let's talk about each of these in more detail. One thing that's amply clear from these measurements and from the growth of these applications is that need for bandwidth in data centers is rapidly growing. As applications scale, we need to provide higher and higher capacity networks, and in a cheap and scalable and fault-tolerant manner. We want efficient network topologies and efficient routing to achieve high capacity. Apart from moving large volumes of data around the data center, we also want to do this at very small latencies, particularly for applications like search, where the deadlines for responses can be very small, tens of milliseconds. Just looking at this Bing query workflow tires me out. Let's take a small candy break. Here, I have a bunch of candy I've collected, and I'll drop in this washed and cleaned stone into it. It's roughly the same size and weight as the individual pieces of candy. Now, if I were to pick a piece from this box randomly, I'm highly likely to end up with candy. No teeth broken. So that worked. But if I grab a handful of candy now, let's see what happens. Oh, here it is. I have the rock now. This makes an important point. It's a simple point about probability, but when you're making a handful of selections, you have a higher chance of coming up with one of the undesirable objects, if there's even just one undesirable in a lot of objects you're choosing from. This is a lesson we'll shortly use in terms of how web requests work. So as we discussed, the deadlines for network I/O in the data center can be quite small. Now suppose that all of your web servers are really nice and their response times are quite small. For most requests, in fact for 99% of the requests, they issue responses in 10 milliseconds or less. But for 1% of requests, they take an entire second to respond. This is an example I'm stealing from Google's Jeff Dean. Now if you're making just one request, the odds that your response will take 1 second or be slower than that are just 1%. But if you were to make 100 requests and wait for them all to finish, the odds are 63% that you'll have to wait a second or more. Just like choosing a handful of candy from that box, you're likely to end up with one of those servers that responds slowly. Now, given what we've seen about the nature of the applications, they make lots of small requests, this kind of thing can happen quite often. 63% is very poor odds. You do not want your service times to be such large numbers. And as these services expand, the problem only gets worse. Thus, what we need is to reduce variability in latency and also to tolerate some latency perhaps at higher layers. For example, the application might make redundant requests and just takes the one that returns faster, because there will be some variation latency inherent to anything that's networked. With the large number of requests, we'll also see a large number of flows that share the network's capacity, leading perhaps to congestion and a problem called TCP incast. TCP incast is something we'll look at in more detail later in the course, but essentially, when a large number of hosts try to share the same buffer, when a large number of flows try to share the same network buffer, they overwhelm that buffer and network throughput drops and latency increases. There are various application layer fixes to this, but ultimately all of these complicate the application's logic. This is a problem that we should attempt to solve in the network, and we'll look at solutions to do that. Further, with the variety of applications that might be running together in these data centers, particularly if you're a cloud provider like Amazon, you also need to look at isolating these applications from each other. So if applications that are latency sensitive are stuck in buffers behind applications that are just moving bulk data, we'll see very poor quality of service. So we need some way of isolating these applications from each other. Applications with different objectives are, after all, sharing the network. Lastly, given that data centers see very high flow arrival rates, and most of the flows are short, that is not persistent, centralized control at the flow level could be very difficult to scale, particularly to large deployments of tens of thousands of servers. So perhaps we'll need distributed control, possibly with some centralized tinkering. The implications we've discussed here will factor into our discussion of all the topics we see in the course, from routing, congestion control, to software-defined networking.
So Ankit, having seen these examples of applications and the challenges they face, what should the application designer do about it?
There are possibilities for handling performance problems at the application layer. For example, with the tail latency, so if you have these requests you're making and some of them are coming late, out of 100, maybe 1% or 2 are coming late, what you can do with the candy example as we saw, you can make redundant requests, ask for the same object from multiple servers and take whichever result comes back first. This is something Google already does. Other than that, you can also just accept a poorer result. So you make these 100 requests, some of them are slower, you don't wait for them. So if 95 come back, you structure the application in such a way that that's good enough. So you just go with whatever result those 95 responses give you. But ultimately, these are all compromises, and the network should do better.
And you just want the network to have high performance for the application.
Exactly.
But that's not easy, because the whole point here is this is a cloud, and you're bringing together multiple different kinds of applications, different tenants, different customers into one place. So
Right.
the kinds of workloads you experience might vary a lot over time, might be very different across applications, and you want to be able to place any VM anywhere in the network to achieve the highest utilization that you can. Which means that not only are the workloads themselves perhaps unpredictable, how they map physically into a location in the data center might be unpredictable. So this will have some implications on how we design the physical infrastructure of the network.
Yes, physical infrastructure, routing, traffic engineering, congestion control, all of this will see impacts from how we make it work.
Sounds interesting.
We'll see all of those topics in the course. In this lesson, we'll look at the physical network infrastructure that underlies massive cloud data centers such as this one. Actually, this is just a shopping mall in San Francisco. But it's smaller than the size of the largest data centers today. And more of you have probably been inside a mall than inside a massive data center. So hopefully this gives you a better sense of the scale of these facilities. Planning a large data center involves many complex considerations, such as controlling the temperature and the humidity. What you're looking at here is a plan accounting for weather conditions in Prineville, Oregon, in the United States, in connection with the Facebook data center that's located there. Likewise, careful planning of the power infrastructure is required. All of this physical infrastructure supports a very dense array of servers and network gear, which might look something like this. This is NASA's Columbia supercomputer. The compute servers are arranged into racks or cabinets, which are lined up on the data center floor into aisles. Let's take a closer look at how these servers are networked together. In the manner you just saw, servers are typically stacked into racks for various reasons, including management ease and space efficiency. Servers in each rack are connected to a top-of-rack switch. The top-of-rack switch supports full line rate communication between all its ports. So if there was nothing else in the network, these servers could talk to each other at full line rate. The data center typically is composed of a large number of such racks, which are then connected into a network. The network's task is to enable these servers to work together on big data problems. If the network does not provide enough capacity, the servers are bottlenecked on the network and compute slows down. Increasingly, the traffic internal to data centers is much more voluminous than traffic to and from the internet. Further, this need is growing rapidly. Facebook, for example, has noted that machine-to-machine traffic inside their facilities doubles at an interval of less than a year. Google has put out similar numbers. So how do we design the network to network these racks together such that the network provides high capacity? What we'd ideally like to build is a big crossbar switch that connects all of its ports at full line rate. This is, however, really complex and costly because of the internals of that crossbar switch. It would need to have n-square connections. Well, we could do this at a limited scale, although perhaps we would use multiple big switches for capacity and redundancy. As long as the number of servers is small, this approach could work. Designs along these lines were in fact built. This here is a picture of a 2004 deployment at Google. A similar design was deployed at Facebook as well. What you're looking at here is 512 server racks, each with 40 servers, each of which has a 1 gigabit Ethernet interface. The top of racks themselves have 4 ports that each are 1 gigabit interfaces. Further, the big switches have 512 ports with 1 gig capacity as well. One thing you'll notice here is the disparity between the capacity of the server rack, which is 40 gigs, versus the top of rack's capacity going out, which is only 4 gigabits. This creates congestion if all of the servers wanted to talk to the rest of the network. There's only a tenth of the capacity available. As a result, the traffic has to be very local. This restricts application deployment and scale. Other disadvantages to this big switch approach are that it's very expensive. All the large switches at the top of this topology cost a lot of money because of their high port density. Further, this is specialized equipment and is available only from a very small number of switch vendors. A lot of it is proprietary technology, involves special purpose management interfaces, and is really quite inflexible and difficult to manage. Another disadvantage is that next generation line speeds, for example, if you're looking at this as a 1 gigabit network, the next generation might be 10 gigabits, and that will not be available at the same port densities. So if you have 512 port 1 gig switches in your network today, tomorrow you might not be able to buy the same number of ports at 10 gig. That will typically start at a much smaller port count like 48 or 96 ports. But perhaps the most serious limitation to this approach is scalability. You're limited fundamentally in how many servers you can have by the port count of these large switches. There are other ways to scale the network though. One alternative is to build it as a tree. Instead of having just one big switch or a few big switches, you organize your network as a hierarchy of switches of increasing size. So at the bottom still sit the racks and their top of rack switches, which further connect to somewhat larger switches and further on to bigger switches. This isn't quite a tree as you see it here, but it's really just a tree and some redundancy. This approach allows you to trade off scale of the network and capacity. So you might have more leaves or more racks here at the expense of limited capacity between racks. This does have its own problems. As machine-to-machine traffic increases, you might see something like this. If half of the top of rack switches send all their traffic to the other half, there will be congestion at the root of this network. This restricts application deployment in that you have to carefully plan to deploy applications in a particular part of the network, and that might not even be possible at certain application scales. It also makes for very poor fault recovery. A couple of failures can partition this entire network, leaving it dysfunctional. It also suffers from some of the same drawbacks that we saw with the big switch approach. The switches at the top of the hierarchy are still quite expensive, and your scale or capacity are quite limited. As a result, another approach that has become quite prevalent is to use closed networks. These topologies were designed in the 1950s for the telephone system, where the driver was actually quite similar. You want to connect callers to each other without having them wait. Such a network supports an arbitrary permutation of inputs and outputs, so you can connect any caller to any other caller. Here what you see is an 8-array closed network. That is, each device in this network has 8 ports. Now you might say that this actually looks quite similar to the big switch approach we are looking at, but there is a crucial difference. Here, all the building blocks of the network are quite small, and we are putting them together to build a larger switch, so to say. As you're looking at this, each device has 8 ports, but you're putting them together to build a 32-port network. And all of these ports can communicate with all other ports at line rate. This design has inspired the fat tree network, which you can think of as a folded closed network. Such a topology is built from small switches throughout. In this example, every switch has 4 ports. There are 2 ways of scaling such a topology. One is to increase the number of layers, and the second is to increase the number of ports at each device. In the example here, you have 3 layers of switches, 1 at the core and 2 at the aggregation. You can also have topologies with larger port counts. For example, if you used 96 port switches with the same 3-layer organization, one can build a fat tree with more than 200,000 servers. This topology is, in a sense, trying to achieve what the tree hierarchy fails to achieve: scalability with high capacity throughout. This visualization might drive that point home further. This is a visualization of a fat tree with a few hundred servers. The servers are at the edge in gray, and the switches are in red. The switches at the core are not shown here, those would be at the center. As you can see, visually this looks like a tree, but all those links that look like fat pipes are actually just aggregations of small links. Such a topology provides a large number of redundant paths between any pair of servers. In the example here, you see 4 paths between the same pair of servers. This has benefits in that if one of those paths is congested, you can use an alternate path. You can design such a topology to have full capacity throughout. In this example, both layers have 16 links. But you can also oversubscribe it if necessary. You might, for example, have a smaller number of core switches, and it will have half the capacity at that layer than at the lower layer. This will result in local clusters having higher capacity than the network as a whole. So you might think of them as placement groups, for example, where you place applications that interact closely with each other. Nevertheless, the use of this cluster mentality does limit the scale of applications you can deploy. Google has deployed in its data centers similar topologies. One instantiation is shown here. As you'll notice, in this topology there are a large number of cables, which can be a problem for physical layout. One solution to this problem is to aggregate these cables into bundles and to run them together on the data center floor. Nothing is changing here in terms of topology. You're only aggregating large numbers of cables and laying them out together. The topology is the same as before. The link speeds are not changing, the number of cables are not changing. It's only about physical organization. Notice also in this diagram the block on the bottom right, which says to external. This is the network's external connectivity. So far we have focused exclusively on how servers in the network are connected to each other, but we also need a way to connect them to the rest of the internet. So here you're treating them as just other endpoints in the network. So you might connect BGP routers, you might connect larger switches in these spots to connect to the rest of the internet. Coming back to our discussion of cable aggregation, this is one example. You see here aggregates of cables running under the floor of a data center. One point that bears mentioning here is that long cables necessarily have to be optics. Copper does not work beyond a certain length limit at these line rates. The loss is too high. In the design of these networks, this can be an important consideration. The long cables, being optics, need transceivers which are more expensive than the equipment we use for copper. As a result, one might vary the topology of the network in such a way as to have fewer long cables. Variants of this network design are actually quite common. Here you see examples from Microsoft and Facebook showing topology deployments in their data centers that are quite similar to what we just saw. So several big players seem to have converged to the same design. Nevertheless, there are other design possibilities too. For example, here you're looking at the 3D torus on the left that's used in the Gordon system at San Diego Supercomputer Center, and on the right is the hypercube that's deployed in NASA's Pleiades system. Different trade-offs come up with different topologies. For example, if you're looking at the 3D torus, that's a topology that's highly locally connected. Nodes only connect to a few close neighbors. Such a topology might be excellent for simulating physical processes. If you're looking at climate simulations, you might consider chunking up the atmosphere into blocks of air. where blocks of air will only communicate with nearby or adjacent blocks of air, in which case the application will mirror the 3D torus's connection pattern. Likewise, other topologies could be very useful for other traffic patterns. The 3D torus might not be a very good candidate for MapReduce-like applications where a large number of servers communicate with other large numbers of servers. Here we have looked at topology somewhat in isolation, but soon we'll tie this discussion to routing. Routing and topology have an interplay. Routing affects topology design, as well as topology design affects routing.
Okay, Ankit, so what did we learn in that lesson? I guess the first big point is just that we're at very large scale and very high bandwidth requirements between hosts, tens of thousands of them. So we can't any longer use just a few scale-up switches forming the backbone of the network. That would be very expensive, and even if we were willing to pay for it, we just can't get the kind of port density we need to network that big of a data center.
Absolutely. As a result, data centers these days are commonly built with close or leaf-spine topologies, where you'll use a large number of cheaper commodity switches networked together to build this large data center. These networks can be scaled arbitrarily large and use very simple building blocks.
And as much bandwidth as we want, as large as we want,
Right.
it becomes feasible, but it doesn't necessarily become cheap. You're still paying for a lot of equipment, and you still have challenges like cabling, huge numbers of cables. If you really wanted a fully non-blocking network between tens of thousands of hosts, that is, the host will never wait for the network. That would be a lot of equipment and a lot of cables.
Absolutely. And cable aggregation and physical organization, these things go a certain distance, but people are evaluating other solutions to this problem, right?
Yeah, so something I think is interesting is looking more towards some kind of radical, as yet unproven solutions in the research community. Some very cool stuff like using wireless as the links among racks in a data center.
Yeah, in fact, one proposal involves using wireless optics to connect the hosts or top-of-rack switches that need to communicate at the time based on the traffic you're monitoring in the data center, connecting them up dynamically with these lasers that are configurable at runtime. So you'll establish a connection in response to the traffic characteristics, and you don't have to run cables between every pair of racks or even build fabrics as dense as these closed networks.
Cool. So obviously a lot of new challenges to solve there from the physical layer on up, and we're not sure whether something like that will actually be cost effective in the future, but it's a very cool direction.
Absolutely.
And another direction that these hyperscale data centers might go is in trying to tackle that tension between getting the economy of scale of a huge data center versus being physically close to your users so you get low latency.
Absolutely. In fact, I think it's very attractive to have some compute, general purpose compute, closer to the edge where your customers are, right? Latency sensitive apps will greatly benefit from that. I will say though, that will require a lot of re-architecting for both the network as well as the applications. You'll have to change both.
Cool.
It's an interesting space to watch.
All right, we'll see you next time.
Today, I have with me Jason Kraft. Jason has helped us craft some very fun but easy assignments for you to study some of the materials we did in the course in a more practical way. So Jason, walk us through the assignments.
So we'll be emulating a data center using a toy topology in a network emulator called MiniNet. So our data center topology will consist of two levels of switches. The top level are called core switches, and the bottom are called edge switches. This terminology is important to remember, as we'll use this in some of our programming assignments. Each core switch is connected to every edge switch, and for the first three assignments, our topology will have two core switches and three edge switches organized just like you see here. Connected to each edge switch are hosts. For the first three assignments, we'll also have two hosts attached to each edge switch. In our data center, we'll be emulating a software-defined network, which has a controller which connects to all switches. And on this controller, we'll be running an open-source software controller called RIU, and we'll be extending a program that can control the network in a centralized manner. Switches and hosts are connected by links, and on each switch is a port for each link. So here we can see that switch S101, there are 2 links to core switches and 2 links to hosts. And these ports are important in an SDN since it's one way we can specify forwarding behavior. So let's take a look at how this works. Suppose our host H3 has IP address 10.0.0.3, and our controller program installs a rule at switch S101 that matches on H3's IP address. The first part you see here is the match, and the second part is the action. So if a packet arrives at switch S101 from host H3, we'll look for a matching rule in that switch. So the switch would find this matching rule and output it or forward out port 1. So the purpose of the first assignment will be to gain comfort with the setup I just described. So our data center will have 2 tenants, 4 hosts running iPerf, and the remaining running a video streaming server and client. We'll use the topology I just described earlier. And in this assignment, our edge switches will send all their traffic through switch S104. And this naive policy is obviously not optimal, since all traffic on the network must be sent through S104, while S105 goes completely unused. This also means that traffic from one tenant will have an observable impact on another tenant. And we'll see this in our video client as it experiences poor video quality. So let's start up our mini data center and see this in action. So first, you'll want to start a terminal, and you can use the shortcut on the desktop or install your preferred emulator. And we'll need 2 terminals for this. So you can either open 2 terminals or 2 tabs. In the first terminal, we'll want to move to the directory CloudNet MOOC, and we'll start our network emulator using the following command. You'll be prompted for the sudo password, which is MOOC, M-O-O-C. And then in the other terminal, we'll move to the directory CloudNet MOOC, mini-dc controller, and we'll start our RIU controller using the command RIU manager and pass it our controller application, controller.py. And then we'll go back to our first terminal and start up our emulator. So Chrome browser should pop up, and the video should start playing. And we can see that it plays in poor quality. And once you've seen enough of the video, we can end the experiment by typing exit into the emulator. You don't want to Control-C this window since there's an important teardown process. And for the controller terminal, we can just hit Control-C and ignore any of the output. So this concludes our introduction to the cloud networking assignments and the walkthrough for the first assignment.
In this lesson, we'll discuss networking in the context of server virtualization. How do we network the large number of VMs that might reside on a single physical server? Cloud computing depends heavily on server virtualization for several reasons. Virtual machines allow multiplexing of hardware, with tens to hundreds of VMs residing on the same physical server. Also, it allows rapid deployment of new services. Spinning up a virtual machine might only need seconds compared to deploying an app on physical hardware, which can take much longer. Further, if a workload requires migration, for example, due to physical server requiring maintenance, this can be done quite quickly with virtual machines, which can be migrated to other servers without requiring interruption of service in many instances. Due to these advantages, today, more endpoints on the network are virtual than are physical. So let's look at how virtualization works. The physical hardware is managed by a hypervisor. This could be Xen, KVM, or VMware's ESXi, or multiple such alternatives. On top of the hypervisor run several virtual machines in user space. The hypervisor provides an emulated view of the hardware to the virtual machines, which the virtual machines treat as their substrate to run a guest operating system on. Among other hardware resources, the network interface card is also virtualized in this manner, with the hypervisor managing the physical NIC and exposing virtual interfaces to the VMs. The physical NIC also connects the server to the rest of the network. So how are these VMs networked inside the hypervisor? The hypervisor runs a virtual switch. This can be a simple layer 2 switching device operating in software inside the hypervisor. It's connected to all of the virtual NICs as well as the physical NIC and moves packets between the VMs and the external network. Before we examine the details of this, it's worth noting that there are other ways of doing virtualization. One, using Docker, is becoming quite popular. In this model we just discussed, each virtual machine runs its own entire guest operating system. The application runs as a process inside this guest OS. This means that even running a small application requires the overhead of running an entire guest operating system. An alternate approach is to use Linux containers for virtualization, just like Docker does. In this setting, an application, together with its dependencies, is packaged into a Linux container, which runs using the host machine's Linux stack and any shared resources. Docker is simply a container manager for multiple such containers. Applications are isolated from each other by the use of separate namespaces. Resources in one application cannot be addressed by other applications. This yields isolation quite similar to virtual machines, but with a smaller footprint. The container packages can be much smaller than the multiple gigabytes needed for a guest operating system. They also do not need to run any redundant guest OS processes. This enables much higher density. A larger number of applications can be supported on the same physical machine than with the VM scenario. Further, containers can be brought up much faster than virtual machines, hundreds of milliseconds as opposed to seconds or even tens of seconds with virtual machines. Recent work on comparing performance across these two approaches, one using containers and another using virtual machines, shows that performance is quite similar with both approaches. How does networking work with such virtualization using Docker? Each container is assigned a virtual interface. Docker contains a virtual Ethernet bridge connecting these multiple virtual interfaces and the physical NIC. Configuring Docker and the environment variables decides what connectivity is provided, which machines can talk to each other, which machines can talk to the external network, and so on. External network connectivity is provided through a NAT, that is, a network address translator. However, multiple projects are working on extending network functionality in various ways, and ultimately we can expect networking to look quite similar in this scenario to what it looks like for virtual machines. In our discussion here, we've ignored certain details about virtualization, for instance, the distinction between Type 1 and Type 2 hypervisors. But the hypervisor VM model as described here will suffice for our discussion, so let's look back at it. As we saw earlier, the hypervisor runs a virtual switch to network the VMs. But who's doing the work for moving around packets? That's the CPU. Now, packet processing on CPUs can be quite flexible because you can have general purpose forwarding logic, you can have packet filters on arbitrary fields, run multiple packet filters if necessary, etc. But if done naively, this can also be very CPU expensive and slow. Let's see why. What does forwarding packets entail? At 10 gigabits per second line rates, with the smallest packets, that's 84 bytes, we only have an envelope of 67 nanoseconds before the next packet comes in on which we need to make a forwarding decision. Note that Ethernet frames are 64 bytes, but together with the preamble, which tells the receiver that a packet is coming, and the necessary gap between packets, the envelope becomes 84 bytes. For context, a CPU to memory access takes tens of nanoseconds. So 67 nanoseconds is really quite small, and we are trying to accomplish a lot in this time. For one, we need time for packet I/O, that is, moving packets from the NIC buffers to the OS buffers, which requires CPU interrupts. Until recently, a single x86 core couldn't even saturate a 10 gigabits per second link, and this is without any switching required. This was just moving packets from the NIC to the OS. After significant engineering effort, packet I/O is now doable at those line rates. However, for a software switch, we need more. If any of the switching logic is in user space, one incurs the overhead for switching between user space and kernel space. Further, for switching, we need to match rules for forwarding packets to a forwarding table. All of this takes CPU time. Also keep in mind that forwarding packets is not the main goal for the CPU. The CPU is there to be doing useful computation. Next, we'll discuss two starkly different approaches to addressing the problem of networking virtual machines, one using specialized hardware and the other using an all-software approach. The main idea behind the hardware approach is that CPUs are not designed to forward packets, but the NIC is. The naive solution would be to just give access to the VMs to the NIC. But then problems arise. How do you share the NIC's resources? How do you isolate various virtual machines? SRIOV, Single Root I/O Virtualization, provides one solution to this problem. The single root part will not be essential to this discussion, and we'll ignore it. With SRIOV, the physical NIC itself supports virtualization in hardware. So let's peek inside this SRIOV-enabled network interface card. The NIC provides a physical function which is just a standard Ethernet port. In addition, it also provides several virtual functions, which are simple queues with transmit and receive functionality. Each VM is mapped to one of these virtual functions, so the VMs themselves get NIC hardware resources. On the NIC, there also resides a simple layer 2 switch, which classifies traffic into queues corresponding to these virtual functions. Further, packets are moved directly from the NIC virtual function to the corresponding VM memory using DMA, that is, direct memory access. This allows us to bypass the hypervisor entirely. The hypervisor is only involved in the assignment of virtual functions to virtual machines and the management of the physical function, but not the data path for packets. The upshot to this is higher throughput, lower latency, and lower CPU utilization, and this gives us close to native performance. There are downsides to this approach though. For one, live VM migration becomes trickier because now you have tied the virtual machine to physical resources on that machine. The forwarding state for that virtual machine now resides in the layer 2 switch inside the NIC. Second, forwarding is no longer as flexible. We are relying on a layer 2 switch that is built into the hardware of the NIC. So we cannot have general purpose rules, and we cannot be changing this logic very often. It's built into the hardware. In contrast, software-defined networking allows a much more flexible forwarding approach. Next, we look at a software-based approach that addresses these two criticisms. This discussion will be based on work by Pfaff and al. We'll only see a very broad overview here, but I highly recommend that you check out the entire paper in detail because it'll not only tell you the final design choices, but also why those choices were made. It's a very interesting paper that walks you through the design process. So let's look at Open vSwitch's design. Open vSwitch's design goals are flexible and fast forwarding. This necessitates a division between user space and kernel space tasks. One cannot work entirely in the kernel because of development difficulties. It's hard to push changes to kernel level code, and it's desirable to keep logic that resides in the kernel as simple as possible. So the smarts of this approach, that is, the switch routing decisions, lie in user space. This is where one decides what rules or filters apply to packets of a certain type, perhaps based on network updates from other, possibly virtual switches in the network. This behavior can also be programmed using OpenFlow, which we'll cover later in our SDN section. So this part is optimized for processing network updates and not necessarily for wire speed packet forwarding. Packet forwarding, on the other hand, is handled largely in the kernel. Broadly, Open vSwitch's approach is to optimize the common case as opposed to the worst case line rate requirements. And as we'll see, caching will be the answer to that need. Let's look at how packets flow through this architecture. The first packet of a flow goes to user space. Here, several different packet classifiers may be consulted. Some actions may be based on MAC addresses, and some others might depend on TCP ports, etc. The highest priority matching action across these different classifiers will be used to forward the packet. Once a packet is forwarded, a collapse rule used to forward that packet is installed in the kernel. This is a simple classifier with no priorities. The following packets of this flow will never enter user space, seeing only the kernel level classifier. The problem, though, is one is still running a packet classifier in the kernel in software. What this means is for every packet that comes in, you're searching in this table for the right entry that matches and using that entry to forward the packet. This can be quite slow. The way Open vSwitch solves this problem is to create a simple hash table-based cache into the classifier. So what you'll do is, instead of looking at this entire table and finding the right rule, you'll hash what fields are used to match a packet, and the hash key is now your pointer to the action that needs to be taken. And these hash keys and their actions can be cached. So for subsequent packets of a flow, you'll only look at the hash match in the cache and use that to point to the table entry. So now you're no longer using an entire packet classifier. You're no longer searching through this entire table. You're just doing a constant time hash table lookup and using that to forward the packet. This works quite well for real workloads. The paper reports results in a large real deployment, showing high cache hit rates, over 97%, and low CPU usage at the end hosts. Let's look at one of the results in the paper in a bit more detail. The performance data was gathered from 24 hours of operations at a rack-space data center with multiple tenants. Each point on the scatter plot represents one of more than 1,000 hypervisors in this deployment. On the x-axis is the number of kernel misses per second, averaged over 24 hours. So this is the number of times we didn't hit the cache or the kernel classifier and had to go to the user space tables. As the number of kernel misses increases, CPU load increases as well, but it's almost always below 20%. In the vast majority of cases, below 10%. This might not be clear from the scatter plot, but data in the paper says over 80% of the hypervisors average 5% or less CPU load. A minor note here, the measured CPU load can sometimes exceed 100% due to multi-threading. Some of the top right points in the scatter plot demonstrate that. Interestingly, the authors found that all 6 instances of this happening in the top right corner were due to previously unknown implementation bugs. To summarize briefly, the hardware approach that SRIOV takes sacrifices flexibility in forwarding logic for line rate performance in all scenarios, virtually hitting native performance. While with Open vSwitch, the compromise made is to avoid targeting worst-case performance and focusing on forwarding flexibility. This brings to a wrap our brief discussion of virtualization in this part of the course, but we'll return to software-defined networking where we'll see a lot more on virtualization.
So that was an interesting lesson on Kit. So we saw how server virtualization has some implications for networking. So actually, virtualization is the lifeblood of cloud computing in a sense, because it allows us to get better economy of scale of compute, storage, memory resources. But that also actually means that the network dips deeper into the host, right? Because we have to virtualize the networking resources among the VMs on a single physical machine.
True. And that exposes certain trade-offs with both flexibility and performance. Flexibility in terms of things like being able to migrate virtual machines quickly together with their network state, and general purpose forwarding logic, right? You can have a series of operations on any single packet before you actually forward it. You might have firewalls or access control, for example.
Load balancers.
Right.
Yeah.
So that on one hand, and performance on the other, because you don't want to compromise on the rate at which you move packets from the physical interface, the network card, to the VM's memory. So you want the bandwidth, or rather the number of packets you can move per second, to be as high as possible. You want that. So you don't want to compromise on either of those things, and it's an interesting trade-off.
And performance, and especially performance consistency, is in fact one of the challenges for virtualization. So in the network, one way to solve that is that you allow the hardware itself, the NIC hardware, to understand that virtualization and allow it to multiplex between
With
different
SRIOV.
VMs with SRIOV. So that's one side of the trade-off space. And then at the other side of the trade-off space, we get a lot of flexibility, but some challenges in worst-case performance with a software switch like Open Virtual Switch.
Right. So going forward, it might be interesting to see if the advantages of these two approaches can be married together. Right? If, for example, we had some limited programmability in network cards themselves, we're not talking general purpose programmability like with FPGAs, which can be expensive, but rather only primitives that network pipelines typically use. General purpose rule matching, for example, right? Packet classification. If that can be generic enough in hardware, then we could have both the advantages, flexibility and performance.
Great. Looking forward to it.
Today, we will discuss routing. Routing solves the problem of how to find paths between sources and destinations in the network. For example, here you have a source and a destination, and the source wonders what path it can use to reach the destination. So you want to install, for example, some routing information in switches to be able to find those paths.
Now, one of the things that makes this a kind of tricky problem is that we want to do this in a distributed way. The switches and routers in the network will be making independent decisions about where to send traffic. And when we first start up the network, or if there's some change, we don't necessarily, at any local point, we don't have a view of the entire network. Okay, so if there are these entities that are making individual decisions, we might make bad decisions if we don't design a good protocol. We might make decisions where we don't get a shortest path, don't get an efficient path, or the worst case would be we get a path that actually results in a loop, where packets will follow a infinite loop, or at least a loop until the TTL drops down to 0. So that is one of the key insights in a very early and important layer 2 routing protocol, which is the spanning tree protocol.
The spanning tree protocol was designed by Radia Perlman in the 1980s to address some of these issues. So it achieves loop-free routing in simple networks. The core idea of the spanning tree protocol is to use a subset of the network's links to route on. The subset is a tree, so there are no loops. So you pick a tree, and then you use that tree to route packets on. What this means is you are giving up some of the network's capacity. You're not using the other links. You can bring those links up in case of failure.
Now, as we'll see, this, for a modern network, is a simplistic protocol. It's not good enough. But the advantage and the real impact of this protocol was that it is a simple protocol. And in the 1980s, it had a huge effect on accelerating the deployment of networks, because you can just plug in devices without any configuration, and the network works.
Precisely. Also, it's still being used in enterprise networks quite heavily.
So the simplification that the spanning tree protocol makes is it takes a large network and it kind of downsamples it to a tree. Okay? So this works well if your network looks like a tree, as in perhaps a traditional data center of 10, 15 years ago for an enterprise where if you squint a little bit, this looks like a tree. OK, it's not a tree. There's some redundancy for failover or links that you might bundle together and treat as one. But you can see the tree-like structure, and spanning tree can be made to work well here. But now, if we're moving to a data center that needs to carry much more traffic, east-west traffic between the hosts at the leaves, then we're putting a lot of load on the top of the tree, the root of the tree. And this means we need very large, physically large, and expensive switches to support that large volume of traffic, increasingly large volume, in a very small number of switches.
As a result, what people are doing in design now is building topologies that scale out horizontally as opposed to vertically. So you're not building the tree such that the top tier is very big in terms of using large and expensive switches. What you're doing is you're using numerous smaller, cheaper switches to build, for example, close-like networks, as in this example here. Spanning tree protocol is a pretty bad fit in these cases because if you think about it, if you take just a tree subset of this network, you'll be throwing away most of the capacity.
So there will be many links left unused, and we can't do multipathing, which we want for both load balance and capacity as well as fast failover, as we'll see.
Right. Also, the spanning tree is quite a fragile protocol. So if one device fails, your network is essentially partitioned. You have the tree, one device fails, the tree is partitioned. Further, spanning tree depends on broadcasting information throughout the network. What this means is there can be scenarios where, due to misconfiguration, you can have a broadcast storm. So the packets simply keep looping throughout the network, and you have no capacity left for actual traffic.
So this is an increasing problem as we build higher performance networks. And there's an alphabet soup of proposed fixes. It's hard to tell which of these is winning exactly.
If any, really. It's hard to gain an idea of what is gaining traction. Network operators are very conservative in their choice of moving to a new protocol because critical operations really depend on these networks. Further, there's lots of confusion. Proprietary flavors of these standards, for example, Brocade's VCS, Cisco's Fabric Path, these are flavors of the Trill standard. These just add to the mix and create confusion. There is in fact significant debate among operators as to which of these protocols might eventually replace spanning tree in deployments. Let's look briefly at Trill's design. This is just one of the proposed replacements, but it illustrates how one might get around these problems. What Trill does is run a link state protocol between switches. So every switch learns the topology of the network. Now every switch knows how to reach every other switch, and that's how you do routing. How you learn where the end hosts are connected has still to be managed through a separate protocol. For example, you might maintain a directory of which hosts are connected to which switch, or perhaps you flood that information as well. Given this setup, let's look at what Trill achieves. All links become usable because you have the entire topology, and multipath routing also becomes possible. Let's look at an example of Trill working. So in this case, the host sends its packet to the switch, which is in Trill's case called an R bridge, and this switch encapsulates this packet, adding information about which switch it needs to go to. So this is the destination switch. The host itself need not be aware of this topology information. The R bridge or the Trill switch has that information. Then it forwards the switch to the next hop that will help reach that destination switch along the shortest path. Every successive switch does the same. And finally, this reaches the destination switch, where the packet is decapsulated and then delivered to the end host.
So Trill fixes an important problem with the spanning tree protocol, which is that it now allows us to use any link in the network. However, there's still a single failure domain, and it requires new hardware to support this new protocol. And if you're running a large enterprise network, you're making some decisions that you probably want to take some conservative choices about what's going to be supported and interoperable years into the future.
For these reasons, one of the options under consideration is OSPF. OSPF has been used for a while in ISP networks. For example, OSPF is Open Shortest Path First. It's also a link state protocol, but it works at layer 3. So what that means is it routes on IP addresses instead of MAC identifiers. The protocol itself is quite similar. It's just a link state protocol, flooding of information or flooding of the topology information, and then use of that topology information independently at nodes. OSPF conveniently sidesteps many of the difficulties that spanning tree protocol faces, as we just discussed. Being a link state protocol, it has all of the advantages of Trill, but none of the newness. So it uses traditional routing. This is well established. It's been used for a while. Operators are comfortable with it. The disadvantage, however, is that it routes on layer 3, which means that you need a lot more configuration. You have to assign, for example, IP addresses and subnets and manage all of this instead of it being a plug-and-play protocol like with the spanning tree.
And we do, however, get better scalability because you can get that aggregation at layer 3. Still, however, with some scalability problems as you grow larger and larger, you're still flooding information about the whole topology everywhere. So that brings us to a more hierarchical version of OSPF.
That's right. Another disadvantage with OSPF is the lack of freedom in terms of traffic engineering. Even though you have these multiple paths, and you can use simple protocols like ECMP to use those paths, there's very little you can do to manipulate which routes are being used between which sources and destinations. So you can only, for example, meddle with link costs. So if you're using the link state protocol essentially calculates the least cost path. And costs are based on edge costs, right? For example, this might be a notion of distance in the network. A faraway node has a higher cost to reach. So you can meddle with the link costs in manipulating OSPF, but that's all you have freedom to do, more or less.
So having mentioned OSPF, there's another natural question, which is, well, what about all of the other routing protocols we use in enterprises and on the internet, namely BGP? Let's review what BGP is. BGP is the Border Gateway Protocol, so this is the standard global scale internet routing protocol. And what BGP does is it allows us to essentially do something very simple. If I'm a router in part of one AS and you're a router in another AS, I can offer you routes to certain destinations, along with some metadata like the sequence of ASs along the path and maybe some tags and community information. And then you will collect a series of routes, a bunch of options to various destinations, and you get to pick one of them, which of your neighbors you'd like to forward information to. So this is called a path vector protocol because you get a vector which is the encoding of the path for each destination. You have these options, and the path being recorded there in the announcement allows us to make sure that there aren't any loops in it.
Precisely. Let's walk through this simple example to see how BGP works in practice. This is a very high-level discussion. We'll be omitting factors that are not going to be relevant to the data center, for example. On the internet, one must say one of the most important features of BGP is being able to use policy, that's economic policy. You have relationships with other ISPs that you're connected to. Use that policy to distinguish who you are going to forward or expose routing information to. So that's something that we'll ignore here. We'll just focus on BGP's path vector protocol nature, the very basics of how it propagates routes. So in this example, we have a few different autonomous systems, ASs, which are connected to each other in this network. And this AS that we are going to look at, AS1, is going to propagate some announcements for this IP prefix to other nodes, to other neighboring ASs. So it sends out these announcements to its neighbors. The neighbors then further might choose to propagate those announcements, as shown here. Now, AS2 has already seen a shorter path to this IP prefix because it's connected directly to AS1. So it will ignore the announcement from AS5. Further, AS2 can forward that announcement to the other two ASs, AS3 and AS4. At this point, everyone has reachability to that prefix. So this is a summary of how BGP works. Notice that the paths are stored as a vector, as Brighton mentioned, in the routing table itself.
BGP, in fact, eBGP, which is the interdomain part of the protocol, is now being used in a number of major data centers as the routing protocol between switches within the data center. And that's, at some level, it's kind of surprising that we take this internet scale protocol and use it there. But what does it get us? Well, first of all, it's IP level. So we do get that aggregation across groups of IP addresses. So it avoids the layer 2 broadcast scalability issues, again, since it's a layer 3 protocol. BGP is a very well-tested protocol that is in many vendor implementations and allows us to use ECMP like several of the other options that we just talked about.
Just to build off what Brighton said, unlike OSPF, BGP was designed to be used in such a way as to be interoperable. So I could be an ISP in Switzerland, Brighton could run an ISP in the US, and BGP should work fine, regardless of how our implementations of BGP ended up being built. So they could be built completely independently of each other, and they have to work together. So this is something that vendors ensure. So BGP can provide much greater interoperability than something like OSPF, which might be designed for one domain in many cases.
We do also have to acknowledge some disadvantages of using a protocol like BGP here. Because it's layer 3 and not layer 2, virtual machine migration is going to be more complex. And we discussed that in another module. There will be slower convergence, particularly in BGP. Not a protocol that converges at microsecond scales. You can tune it, but there's still going to be delays as this distributed system finds new paths in the face of a change. And finally, when you're deploying BGP, there's along with the flexibility and control over routing comes a large set of possible knobs and dials to tune the protocol that makes configuration potentially more complex. So let's take a step back and talk about what we've seen. So we saw a handful of different protocols that look very different. Trill at layer 2 and OSPF, link state, and BGP, a protocol traditionally designed for the internet, now being used even in a network within one building. So what's going on there? Well, there's actually some commonality between all of these designs. If you think about what was insufficient with the spanning tree protocol, that was a reasonable protocol if we have a tree-like network where the problem of finding paths is a lot simpler. But now, as we get larger scale data centers to support lots of east-west traffic, we've basically got a pretty complex network, especially if you think about conditions like failure where the topology becomes irregular. We've got a pretty complex network now, even within one building. So that's why it makes sense to take a general purpose internet scale routing protocol and bring it into the data center and use it there. And that's kind of a feature of all of the designs we talked about, that whether it's at layer 2 or layer 3, there's basically now a pretty good general purpose routing protocol that we're using between switches in the data center.
What Brighton is saying also leads us into a separate point about exploiting the richness of these complex systems. So you have these topologies that no longer look like trees. They have multiple paths between various sources and destinations. And we've installed them perhaps using these general purpose routing protocols into the routing tables. Now, how do you use those multiple paths? How do you decide what traffic goes on this path versus the other path? You need some idea of what the network's conditions look like to be able to make these decisions. If some paths have failed, perhaps you can fall back on other paths without waiting for the routing protocol to converge. As we noted earlier, routing protocols can take on the order of a second, in the case of BGP particularly, to converge. So using this backup connectivity is really important. So this is what we look at in the next lesson. How do you use multipath routing in real time to overcome these problems? So far, we have talked about routing, in that how do we find paths through the network? Now, the question is, how do we use these paths for forwarding packets? That's what we'll look at next. Besides basic connectivity, we also want fault tolerance and traffic engineering. These are both things multipath routing helps with. The example we'll work with throughout is the fat tree topology, which, as we've noted before, has lots of parallel paths. For example, between these two servers, there are these 4 parallel paths. Can we exploit these paths for fault tolerance and traffic engineering? The goal of traffic engineering is to minimize network congestion. So you want to spread traffic throughout the network while ensuring that none of the paths are congested, or at least most of the paths are not congested. This is a difficult problem for several reasons. First, in these networks, as we've discussed before, there can be a large number of flows which are very short. So imagine that you're trying to gather information about the network's current state, the traffic's current state, and that state is changing quite quickly. Which brings us to the second problem. The problem of traffic engineering, that is load balancing network traffic, is computationally expensive. So you're trying to gather information about the network state, you're trying to solve this computationally expensive problem, and push out the results to the switches to make forwarding decisions. This brings us to the third concern. You'd like to solve this problem in a distributed way so you don't incur this challenge of collecting information quickly and making decisions and pushing them out. A distributed algorithm is not that easy to develop. For all of these reasons, data center operators settle for inexact solutions, the most common of which is randomized spreading of traffic with ECMP. ECMP is equal cost multipath routing. So let's see how ECMP works. To send traffic between these two nodes, the sender, that's the server on the left, will forward its packets to the switch. The switch now has two choices, known from the routing protocol. So the routing table entries might look something like this. So these are routing table entries that a routing protocol has already installed in the switch's routing table. ECMP's method of deciding how to forward packets is to simply pick one of these paths randomly. So it might choose port 1 for packets destined to 10.2.0.3. But this poses a challenge. Packet spraying is a problem for TCP. So if you're making individual decisions for different packets and those packets end up with this random selection on different paths, that can be a problem for TCP. Let's see why. Let's say the first packet ends up going through this path. It gets queued behind several other packets in the buffer at that other switch. In the meanwhile, the second packet with a different random choice ends up at this switch where there is no packet queue. The buffer is empty and the packet goes through to the destination. Finally, at some point, the first packet arrives here as well. Now the packets are reordered, and if the reordering is significant, TCP can consider this a loss. And that will mean that TCP will drop throughput by half. If this happens often enough, throughput will be very low. The solution to this problem is to use flow-level hashing. What ECMP does is it uses the hash of the packet's header to decide which of the random choices to make. So the output port is determined as a hash of the packet header. Further, ECMP can be done independently at each hop. In this example, you have two choices at the first switch, and then you have two choices at each of the successive hops. There are no further choices from the root switches. Each of the root switches leads to one unique path to the destination in this topology. This gives us a total of 4 path choices in this example. As you can see, ECMP's mechanism is really quite simple, and it works well for both layer 2 and layer 3 routing. This randomization-based approach works quite well for a large number of small flows. However, randomization will sometimes lead to imbalance in flow assignments. This can cause long-lasting congestion if multiple long-lasting data flows are mapped onto the same set of links, as in this example. So you have 2 of these flows mapped onto different links, but the other flows end up mapped by randomness to the same set of links. As we noted earlier, we cannot do randomization at packet level, which would get rid of this problem to a certain extent, because that causes packet reordering and causes issues with TCP. However, we don't necessarily have to do this at the flow level either. This is where the idea of a flowlet is useful. Let's look at the details of that concept. Let's say what you're seeing at the bottom is the packet stream coming in at the sender on the left. If the gap between groups of packets is larger than the conservative estimate of the latency difference between the two paths, we can send the packets, the packet groups that is, on different paths without risk of reordering. Such packet groups are called flowlets. This helps make load balancing more fine-grained. So yes, the per packet choice is not available to us because of a risk of TCP reordering, but we don't have to do things at a flow level as well. We can have something in between the two. This idea was proposed by Kandula et al. In 2007. A more serious issue with ECMP, perhaps, is that ECMP only makes local decisions without knowledge of failures further on the path. Let's look at another example. Here, as we know, the path from the root downward is unique. So once the packet has arrived at that rightmost root switch, there's only one path down to the server. However, the links further upstream of that path, the earlier switches going up, have no indication that that link has failed and that path is unavailable. Thus, ECMP making only local choices can do nothing to avoid this path. Note how in this topology, a failure-free path was available, but some of the traffic ended up on the failed path because of the randomized choices. Recent work has proposed a solution to this problem. This is very recent work called Conga from Cisco Systems. The key idea is to monitor congestion on paths in real time and pick the least congested path on a flowlet granularity. This requires maintaining a table at every leaf switch for every destination switch where you keep track of the extent of congestion on each of the paths between these two switches. And then you'll pick the least congested path on a flowlet basis. Let's look at an example. From switch A, which is connected to the left host here, there are 4 different paths to the target switch. And these paths each have different extents of congestion indicated by these values in this table, 3, 7, 2, and 1. The least congested path is path 4. So for the next flowlet that comes in at this switch, path 4 will be selected, and then the counters will be updated accordingly. Lots of details go into making this work in practice. For example, instead of actively probing the congestion between every pair of switches along every possible path, the data is piggybacked on data packets. So if you have exchanged some data packets with another switch, you can add the information about congestion between these two switches on these data packets. Even so, this approach may not scale for the largest data centers. This is an active research space with a 2014 research proposal already implemented in switches. So who knows what exciting new proposals we can expect in a few years from now. Again, to reiterate, we have single entity control in these facilities. The switch forwarding tables are quite large, tens of thousands of layer 2 and layer 3 entries in routing tables. The topology is known and is controlled by the operator. Topologies have lots of link and path redundancy, so watch out for more interesting developments.
Hi, in this lesson we're going to discuss congestion control. This is one of the core topics in any networking class that you might have in an undergraduate institution or background from running networks operationally. So here we're going to focus on just a high-level refresher and then talk about what's new in the cloud.
In this example scenario, we have servers stacked up in a rack connected to a switch which is connected to another network switch. Now we'll have some traffic flowing through this network, and all of these flows you'll see are sharing that link between the two switches. The question congestion control answers is how is this capacity shared across these flows? At what rate does each sender send traffic at? And why does this matter?
Well, the right rate is important to get because let's see, what happens if we send larger than the available capacity that's appropriate for this flow? We're going to get packet loss, we're going to get delay, as we'll discuss, and we're going to get an unfair capacity distribution, maybe between your flows, but also maybe between different tenants in the data center that you would not want to be interfering with each other in terms of performance. On the other hand, if you send at less than the available capacity, you have inefficient use of the network that can also harm performance of applications. So, Ankit, what's hard about this?
The problem is hard because the capacity is unpredictable. The available capacity for any sender is not really fixed. It depends on the scenario. We are building a general purpose protocol, like TCP, say, and the sender may be in different environments. It could be a wide area environment, it could be a data center environment, it could be a shared medium, or it could be an exclusive connection between two devices. All of this is not really known because it's a general purpose protocol. Also, the dynamics of traffic make things more complicated. Traffic could be bursty, flows can arrive at microsecond intervals, and there could be a large number of flows at any given sender. All of this makes congestion control hard because we want to make independent decisions by senders. So how do we address this problem?
Okay, so the basic mechanism we have for this in traditional congestion control is an end-to-end mechanism. That is, the sender is going to send a stream of packets through the network. We don't get any information directly from the network gear, the routers and switches, but when the receiver receives a packet, it will send acknowledgments back. And this tells us, first of all, we know the data was delivered and which data was delivered, so that we can ensure that the correct data is, in fact, reliably delivered after we retransmit if necessary. But also we get some hints about how quickly the data is being delivered and whether some is lost, in which case it's an indication of congestion. So that's the basic idea of acknowledgments.
Right. And these acknowledgments help set up what is a natural feedback loop. The sender treats the network as a black box, sends in packets to this black box network to the receiver, waits to receive ACKs from the receiver in one round trip time, or not if the packets are lost or the ACKs are lost, and adjusts the sending rate based on this feedback in terms of ACKs. And of course, this loop continues. So how does the feedback affect the rate of the sender?
Well, the basic idea is that if all of our packets are being acknowledged, we'll increase our rate, because it's an indication that there's spare capacity in the network. If we're seeing packet losses, or packets that are presumed lost, then we will decrease our rate. Now, this is, of course, hiding a lot, because when exactly do we take these actions, and how much do we increase, how much do we decrease in the given scenario? So we're going to skip the details. There are linked resources on the course webpage, and instead focus on what changes in the cloud environment. But we'll do just a brief overview.
Right. So here what you see should be a familiar graph. This shows how TCP adjusts the rate in response to feedback in terms of ACKs. The details of this vary across different flavors of TCP, but the rough idea is the same. What you're seeing on the x-axis are essentially iterations of that feedback loop, and the y-axis is the sending rate that TCP is achieving in that iteration. So here TCP is attempting to match the network's available capacity by reacting to the network's treatment of its packets.
We have to start somewhere, so that's the first question. Where do we start? And TCP starts conservatively with just 2 segments for the first window that it's sending. And then as the feedback comes in each RTT, each round trip time from sender to receiver, we double the sending rate until if we hit a packet loss, then we exit this slow start phase. Now, you'll notice that the slow start phase is slow because it started slow, but it actually increases very quickly, exponentially, until, like I said, we hit that packet loss, and then we move into the additive increase phase.
In the additive increase phase, TCP's rate does not increase exponentially, as Brighton mentioned for slow start. Rather, the rate is increased additively in response to ACKs being received. What happens when we lose a packet?
Well, when we lose a packet, that's an indication that now we've exceeded the capacity, and we're going to conservatively back off, generally by a factor of 2 in the classic TCP protocol.
5 points for Gryffindor. What's not shown here is TCP timeouts. Once TCP loses a large number of packets consecutively, say an entire window's worth of packets, TCP times the connection out, which means that after a long delay, it'll start again from slow start. And that long delay can be 200, 300 milliseconds, which in data center timescales is an age. Next, we'll talk about some of the problems with TCP's congestion control. Some of these are specific to the data center environment, and some apply more broadly.
All right, so let's see what some of the problems are with this TCP congestion control scheme.
First, the multiplicative decrease can be quite aggressive. Perhaps the rate that the sender was sending at was only marginally larger than the available capacity. In this case, cutting down the rate by half is a drastic reduction that's totally unnecessary and is inefficient because TCP will take a while to ramp up the rate again. Another
problem is that loss itself can be a poor signal of congestion, or how much congestion. So although a packet may be lost because the queue did fill up, which is the likely condition in a data center, we're not talking about a wireless network where there's a high rate of corruption of packets at the physical layer. It may be only a very brief, transient overrun of the queue. And backing off substantially is fixing a problem that in the future wasn't really there.
Brighton mentioned long queues, so let's look back at our example scenario. We'll zoom in on this buffer here. As the buffer fills up, the packets at the tail of this buffer have to wait for the rest of the packets to drain out before they can reach the port. This increases the latency that's observed end to end. This is a long queuing delay.
In fact, in data centers, queuing delay can be the primary cause of end-to-end latency within the network. So to illustrate this, let's borrow a demonstration from Rear Admiral Grace Hopper. So what is this here, Ankit?
This is about a nanosecond at the speed of light in vacuum, or a nanosecond at the speed of light in fiber. Now, if you're at a data center, about 1,000 times this distance might be the distance between two distant machines on the floor, right? So it covered that distance in about a microsecond. That's still a millionth of a second.
And in comparison, how long does it take to send a packet through the network? Well, imagine we have a jumbo frame that's about 9 kilobytes, and we're sending it through a 10 gigabit per second network. If you multiply that out, we're talking about 8 microseconds, which is already something like 8-ish times longer than the speed of light propagation delay through the actual wires end-to-end in the data center.
Right, working with that example for the 1 microsecond.
Right.
Although there are other delays in the network, all the devices take time to process packets and such, but in practice, tens of microseconds end-to-end are doable. These are numbers that have been reported from production data centers. So tens of microseconds of propagation delay when the queues are almost empty.
So in comparison, we had that 8 microsecond number for waiting behind one packet, potentially. Now we've got multiple hops. We might have multiple packets behind which we have to wait at each hop along, say, a 6-hop path in a pretty large data center. Were already substantially longer than that end-to-end latency that's been shown to be achievable without queuing delay.
As a side note, Grace Hopper, whom we borrowed that demonstration from, was a computer scientist in the Navy. She was also cool enough to have a missile destroyer named after her, as well as a supercomputer. Public service announcement, were I to do something awesome, I would pick the supercomputer to be named after me. She also popularized the term debugging. Back to congestion control in data centers.
So what we just saw in that digression was that if you have large queues that are backed up, then you can have easily an order of magnitude latency increase in the data center, which can significantly affect latency-sensitive applications.
Also, buffer occupancy is bad for isolation across different applications. Once a buffer is occupied, it's shared in many switches across the ports of that switch. So what that means is if one flow has occupied the buffer, other flows will start dropping packets, even though they're not headed to the same port.
Now, certain applications that we run in modern data centers exacerbate those latency problems. So let's take an example of a web service that we're hosting in the cloud. This web service is going to receive queries from clients, and these queries will eventually make their way to some web server which is facing the client directly. Now, to fulfill that query, we're going to have to aggregate results actually from many back-end queries to other databases. Like, on my website, I might have advertising results. I might show, items for sale from various databases. I might show results that are specific to the user. There can easily be hundreds of queries to multiple different kinds of back-end databases to produce the result that I actually want, which means that there's this fan-out or a scatter going to many different servers in the data center. Before those are gathered again back, the responses are gathered back at that aggregation point.
For such applications, low latency is crucial. Web search really depends on serving users in a very time-limited manner. User experience and the provider's bottom line both depend on providing timely service.
At the same time, sending all of that network traffic to many different servers is going to potentially increase queues, increase latency, and cause a severe condition that can occur, that's known as incast.
So incast has been measured both in the laboratory and in actual deployed data centers. One such measurement for synchronized reads on a storage cluster is shown here. On the x-axis of this plot is the number of servers sending data to this one read client. And on the y-axis is goodput in megabits per second. The maximum in this network is 1000, or about 1 gigabit per second. As you can see, as the number of servers increases on the x-axis, the throughput drops sharply. At about 5 servers, 5 senders that is, to this one client, the throughput has collapsed. This is a characteristic of the incast condition.
Okay, so what we've seen is a short overview of TCP and some of its problems. And in the context of running a cloud and running a data center, latency is very important in queuing because the physical distance is very short. So now if we back up the queues with all of the big data that we're sending, this can significantly increase latency for latency-sensitive applications, especially if there's a human waiting for many results to finish. And that sort of traffic pattern, when we're waiting for many sort of results to finish, is very common, the scatter-gather traffic pattern that can lead to a specific problem known as TCP incast. And next time, we're going to see how some of these problems can be solved.
Previously, we discussed several of the problems that TCP faces in the data center, including high latencies and TCP incast.
And there are other problems with TCP more broadly. Multiplicative decrease being too aggressive, the lack of isolation across flows. So how might we approach a solution to these problems?
It may seem that we are trying to achieve two somewhat conflicting goals. We want high throughput, for which we might desire large buffers, because if you have a large number of flows, bursty traffic flowing into that port, you want to be able to accommodate all those packets in the buffer. At the same time, if these buffers are full, packets queue up and you get long queuing delays.
So we want high throughput, we want low latency. Are these two goals fundamentally at odds?
Not quite. We'll see a proposal that addresses these, but before that, it's worth mentioning that this is not really a problem that's specific to the cloud setting. But the data center does exacerbate some of these issues, partly because queuing delay dominates propagation delay, which is not the case generally in the internet, and also because of the need for performance isolation across these different tenants that might be sharing a data center, and application patterns such as scatter-gather that cause incast.
So there's a particular need that drove the industry towards a solution. And we'll look at one of those solutions, data center TCP.
This discussion will be based largely on work by Alizadeh and al. That was published first in 2010 and is already in use in data centers, which is quite exciting to move from research to production in 5 years, probably less.
And if there's one key idea that's the starting point, it's this. Waiting until the buffer is full, as TCP does, to get this indirect signal from packet loss, that's too late. We've got to know faster what a good rate to send is.
Right, because if you've filled up the buffer you've lost, you've already incurred the large latency, and you're potentially exposing yourself to packet loss and incast. So one of the ideas that DC-TCP builds on comes from the ECN mechanism, which is explicit congestion notification. So let's look briefly at how ECN works. When a packet arrives at an ECN-enabled switch, the switch looks at the average queue length over a recent time window and makes a decision on whether or not to mark it with a congestion bit. So how's this decision made? The switch looks at two thresholds, a low threshold and a high threshold. If the average queue length is higher than the higher threshold, the packet is always marked with a congestion bit. If the average queue length is smaller than the low threshold, the packet is not marked with a congestion bit. In between these thresholds, the packet is marked probabilistically. Once the switch marks the congestion bit on the packet goes to the receiver, and the receiver copies it back to the ACK and sends it back to the sender. The sender can thus react to congestion before there is packet loss. The sender's reaction is essentially the same as what TCP would do, that is, scale the rate down by a factor of 2.
So it treats it like a packet loss, except that you don't have to pay the cost of a packet loss, you're just getting the signal.
Precisely. With DC-TCP, the switch's operation is even simpler. One, it only depends on instantaneous queue size, so it does not look at an average over time window or such. If the buffer's occupancy is higher than the marking threshold when a packet arrives, then the packet is marked with a congestion bit. And it's sent on to the receiver, and the receiver copies it back to the ACK and sends it to the sender, the same as before. This makes reactions to changes faster because now you're relying only on an instantaneous count, so you're not depending on a time average, which could be more stable than current conditions. So that could take, the time average could take a while to reflect the current situation in the network. So this is particularly valuable in highly dynamic situations like data centers.
But DC-TCP's key insight is rather than using binary signals of congestion, we're going to use a stream of those markings in order to estimate the frequency of the markings and therefore the extent of congestion, so we can make a much more intelligent decision about how to adjust the rate.
So here you're extracting multiple bits of information from the ACKs rather than the one bit you were getting earlier. Now, apart from keeping the buffer occupancy low by setting that marking threshold small, what this also does is ameliorate the problem with multiplicative decrease being too aggressive. Now you can scale back things in a proportional manner.
So the sender is going to maintain a running average of the fraction of marked packets, and the adjustment to its sending rate is going to be proportional to that fraction.
So to summarize what DC-TCP does, it marks the packets with congestion bits on instantaneous queue size at the switches, and then the senders use that feedback to extract multiple bits of information from the network about congestion and scale down the rate at which they are sending or scale up the rate at which they are sending accordingly. The marking threshold can be set quite low in practice. So this will give us low buffer occupancy because you'll indicate congestion quite early in the process. Also, the free room in the buffer that comes with this low buffer occupancy means that you'll be able to absorb traffic bursts. So you can deal with in-cache without losing packets, without TCPs timing out.
Now, DC-TCP has been deployed in practice, and we're mentioning one paper here from Glenn Judd at Morgan Stanley, illustrating some measurements of an actual deployment in their data center. And those experiments show 2 orders of magnitude lower latency compared with vanilla TCP.
And here you'll also notice that number, about 40 microseconds in the median with DC-TCP plus. DC-TCP plus because they've made some changes to the DC-TCP proposal. It's important to put these results in context though. DC-TCP is, after all, not the first to realize that multiplicative decrease is too aggressive. Proportionally reducing the rate is something that RCP proposed several years earlier. So let's take a brief look at what RCP did.
So the main idea of RCP is that the routers and switches in the network directly observe congestion and can explicitly decide what is a fair rate among flows. And so RCP set this explicit rate. At each switch along the path, the packets will be marked in a particular header field containing that rate as instructed by the switches. That could be then marked by the switches along the path, carried to the receiver, and sent back to the sender. And now this is an explicit indication, even on a packet-by-packet granularity, of exactly how fast we're supposed to send. So we get the right rate, and we don't even need slow start in that case.
DC-TCP succeeded in achieving deployment for 2 big reasons. One was its dependence on only existing hardware. So all the hardware that DC-TCP depends on, ECN bits at the switches, those are already built in to switches. Also, the cloud environment exacerbated the problems that needed solving, and DC-TCP fit that bill.
Now, that said, DC-TCP does have some drawbacks.
Right. For one, DC-TCP is not TCP friendly. So if you have a data center where you're running DC-TCP on some machines and TCP on others, the flows will not share bandwidth evenly. DC-TCP will hammer TCP because of its more aggressive rate control, right? TCP flows will fall back by half, while DC-TCP makes proportional adjustment, and over the long run, DC-TCP flows will do much better. So this is not good for fairness across different services if they are using these two different protocols. Now this problem and its resolution has been proposed in a recent paper. The same one we talked about earlier in the context of results, that is the DC-TCP plus proposal from Glenjud. The core idea is to treat these two protocols as different quality of service classes and to share capacity across these classes fairly.
Another issue with DC-TCP is that it doesn't address the issue of slow start. There's still that problem that remains. And applications like RDMA, for example, will care a lot about that slow start penalty where you have to pay multiple round trip times to get up to the fair sending rate, even if you're only sending tens of kilobytes, at least using default parameters for TCP. So getting rid of slow start, exactly how to do that, is also an active area of research.
Right. And of course, there are other opportunities for doing even better. DC-TCP does not address anything related to application level behavior. For example, if certain flows have higher priority, how do you do that? If certain flows are deadline oriented, how do you handle that? So in this lesson, we saw how DC-TCP addresses several of the problems we saw earlier with TCP. Nevertheless, there are opportunities for doing even better. For one, DC-TCP does not account for application behavior. What if certain flows are deadline sensitive? How do you address those? Also, if some application has a large number of flows, can you orchestrate rates across those flows, and such?
So Ankit, it's actually pretty exciting in a matter of a few years, this proposal going from research to deployment in the data center. We're seeing that kind of thing happen with a few technologies in this course. And in part, it's because one of the hard things about deploying new technologies in networks is coordinating across parties. Now here we need to coordinate across senders and network devices and receivers and make sure that they handle all those marked packets correctly. But there is one designer and operator of the data center, one organization, so that coordination can actually happen, and it's well worth it to get the performance.
Absolutely, and apart from this economic setting, the single owner aspect of it, the applications really are also driving the design of these proposals, right? The scatter-gather pattern is so prevalent in these data centers that really that problem had to be addressed. Latency as well as buffer occupancy to deal with in CAS.
Right, and you're bringing up now applications. We've spent most of this lesson talking about the network layer. But really what you care about is what is the performance on the application ultimately to complete its job, which might involve coordinating across multiple flows before you get the final answer that you want. Or it might involve some amount of coordination or isolation among applications flows belonging to different applications or different tenants. So there's a lot of interesting research along those lines dealing with optimizing rate control and congestion control in data centers, both in academia and in industry research labs. Hi. In this lecture, we're going to be introducing the architecture of software-defined networking, which, as we will see later, has important applications to networking in the cloud. The problem that SDN, software-defined networking, is addressing is one of complexity of existing networks. Networks are, in a sense, just like any other computer system or system of software, right? There's hard problems we're trying to solve, and even something that looks simple might not be easy when you actually go to code it. But worse than that, it's a distributed system, and even worse than that, there are no clean programmatic APIs, only knobs and dials to control certain functions. And if we're staying within a limited use case, that might be good enough. But if we have a large, complicated, heterogeneous network or are trying to use it in more interesting ways, as we will see, it can be very hard to build the network. A second problem is that network equipment traditionally is proprietary. So there are vertically integrated solutions where a major vendor might produce its own hardware, its own operating systems and software and implementation of protocols, and then configuration languages for that system, for that product. The result of all of this is that it has become harder to innovate in traditional networks, to build new kinds of networks or new services, or use networks in ways that maybe we didn't expect, or more efficiently. So innovating and changing networks became a process that has been often rather frustrating and time-intensive. So in a traditional network, you might be configuring a router, for example, for BGP routing in this trivially simple configuration file. It can get much more complicated than this. But then you'll have many of these also for many different routers, hundreds, thousands, tens of thousands of network devices, routers, switches, and firewalls throughout the network that will get pushed out to the various devices in the network. Once it reaches the device, then these configurations have to be interpreted by router software and implementation of protocols that run distributed algorithms and arrive at routing solutions that produce the ultimate behavior that's installed in the network hardware. So if you look at this picture, what it's illustrating is that the policy of what we're trying to achieve is baked into the mechanism. Right? So for example, the kind of network routing that I do, whether to achieve low latency or high utilization of the network, those controls are baked into the distributed protocol that are in standardized implementations. Right? And that integration of the policy goal and the mechanism for achieving that goal means that it's hard to innovate. So let's move to software-defined networking, where we want now to build a more programmatic architecture. How are we going to do that? Well, if we think about how traditional software and operating systems are built, it's based on layers and APIs. Okay? So we begin close to the hardware. We want a simple, low-level interface that gives us pretty direct access to what the network switching hardware is doing. Okay? So, an API into the data plane of the network. Then we'll have a logically centralized controller that communicates with these distributed switches and other devices in the network. The goal of the logically centralized controller is that we can express our goal in one location and keep the widely distributed switching gear as simple as possible. Right? So we put the intelligence in a logically centralized location. And then on top of that, once we've got that central controller, we can build software abstractions that help us build different applications. A network operating system, if you will. So these features of a low-level interface, programmatic interface to the data plane, a logically centralized controller that allows us to build abstractions on top of it, are key ideas that come together into this architecture called software-defined networking. Let's look at a simple example from a very early SDN controller called Knox. Okay, so this is how we are programming the network at that central controller. And what we're trying to do here is to identify a user's traffic. So we want a particular user or computer to send traffic through the network, and that traffic through the network is going to be tagged with an identifier, a VLAN, that identifies that user. Okay? So to instruct the network to do this, we're going to match a specific set of packets that are relevant, and we're looking at the location where this traffic comes in from, as well as the MAC address. And we're going to construct an action that should happen, in this case including tagging, adding that VLAN tag to the traffic. And then we're going to install that action on the specified set of packets in a particular switch. Right? So we're basically explicitly telling the switch, if you see this, do that. Okay? Now, this is something that would be pretty difficult in a traditional network, where I've previously done a lookup in some external database to figure out what VLAN ID I want to use for this particular user at this particular moment in real time. And now I'm programming the switches. Right? But here we can do it in a few lines of Python code. So this is an early and pretty low-level way of programming SDNs, but it illustrates some common primitives, a least common denominator, if you will, among SDN controllers. And one that this example is illustrating is the ability to match a group of packets and execute actions, including rewriting fields in the packet and forwarding or perhaps dropping that traffic. In addition, commonly SDN controllers will have some kind of topology discovery, so you can see globally what the network looks like, as well as monitoring, so we can monitor rates of traffic flow and congestion and packet loss and so on in the various switches and routers and other devices in the network. Okay? So there's a lot more ways we can think about SDN, but these are sort of a least common denominator for SDN controllers. The ability to control traffic and discover the topology and monitor behavior in the network. So what we just saw are some of the key ideas of SDN: a programmatic low-level interface to the data plane, centralized control, and higher-level abstractions that make that control easy. Now, all of these ideas have long roots. If we go back into the history of networking, no one of these ideas in isolation is something that's new. So we're not going to be able to cover all of that history, but I want to talk about a few of the threads of evolution of SDN. So one of the important needs that SDN is driving towards is making the network flexible. Okay? And there are a few important ideas that I'd like to mention in past systems that allowed us to make the network more flexible in somewhat related ways. One of those is label switching, or MPLS. Okay? Now, in terms of the mechanism, what MPLS does is actually simpler than an IP longest prefix match forwarding. It does matching labels and executing actions based on those labels. The effect that we get from that is that we can essentially lay down any path that we want in the network for certain classes of traffic. That allows us to go beyond simple shortest path forwarding and do more interesting and complicated things, like good optimization of traffic flow to get high throughput for traffic engineering, or setting up private connections between enterprises and distributed sites. Okay? And that flexibility of programming the network, and in particular oriented towards traffic engineering, is something that made MPLS very successful, and as we'll see, is also an important application for SDN. Now, active networks made networks more flexible in a very explicitly programmatic way by embedding a program within a packet header, or a pointer to the program in the packet header, that the router or switch should execute. Okay? Now, this is a somewhat radical idea of packets carrying code with them. But it illustrates that even at that time there was a recognition that we could do a lot more with networks if we could make them more programmable. Another important thread of ideas is around logically centralized control of networks. And this is something that goes back decades, but I'm going to mention a few projects that are more recent in the sphere of internetworking. One of these that was influential is the routing control platform. So if you look at how routing is done with BGP routing, this is the Global Internet Routing Protocol, even within an enterprise, it's still a distributed system. You still have many exit and entry points where you connect to the outside world, and your global routing flow, even within your enterprise, is controlled in a distributed system. The idea of RCP was to centralize the decisions about routing flow and then push out those decisions to the border routers within the network. The 4D architecture introduced an idea of a logically centralized decision plane that, like SDN, separates those decisions from the data plane actions. And that's very closely related, of course, to the idea of having that explicit API where you're programming the hardware. Okay? Now, an immediate predecessor to SDN was a project called Ethane, which allowed us to program policy for an enterprise, for example, access control, in a centralized way and have it then pushed out to the entire network. Okay, so you would write a policy such as the one illustrated here about how certain groups of users and types of devices can access the network, and then have that single centralized expression of the policy be implemented automatically in a distributed way. Now, the OpenFlow protocol was introduced in 2008, and this is one possibility for how we have that interface to the data plane. So it introduced that explicit idea of the standardized interface to the data plane and with general purpose programmability at the controller. Knox was the first controller for OpenFlow that provided a centralized view of the network and exposed that to multiple applications with database-style access. So the important idea here is that Knox can provide this service of the appearance of centralized control to the applications, where behind the scenes it's doing that work of state collection and state distribution in the distributed system. Okay? Now, since then, there's been an explosion of interest both in academia and in industry in software-defined networking, with essentially every major networking company having some sort of an SDN product. But if we go beyond the marketing, what is it that is the real fundamental technical opportunity here? Well, there are, in fact, real opportunities that are pretty exciting. If we look at having an open interface to the data plane, from the hardware perspective, if we have a standardized API, it can be easier for operators to change hardware in their networks, to use different vendors, and for new vendors to enter the market. From the software perspective, we can finally directly access the device behavior, which exposes a lot more capabilities than we would have in traditional networks. The centralized controller gives us that direct programmatic control, so we can make architecting a network more like good software design. Okay? And then building abstractions in the controller allows us to solve these distributed system problems only once, and then it's just a matter of writing algorithms, right? So whereas in a traditional network, if we want to devise a new way of controlling traffic flow in the network, that involves writing distributed protocols and standardizing. Now we can just write an algorithm like Dijkstra's algorithm, the kind of thing you learn in freshman or sophomore level computer science, and plug it directly into your SDN controller. So we can control networks in a way that's much more like traditional software engineering, with libraries, with languages to help write programs. And if you don't want to write programs, perhaps we can build systems that allow you to express higher level goals, like I want my network to have optimal traffic flow, or this certain kind of access control. So those are real exciting opportunities. But at the same time, there are certainly challenges. Right? So one, of course, is performance and scalability, where we're controlling the network through devices that are going to have to respond quickly with latency concerns, for example, and capacity concerns. And although I've talked about a logically centralized controller, I'm careful to use, when I am careful, I use the word logically centralized because, in fact, we can't have a single centralized controller. Right? All of those distributed system challenges are still present, that are present in a traditional network. Right? The network is still fundamentally a distributed system, which means there are hard problems surrounding resilience, the lack of perfect knowledge of everything that's going on. We never know exactly when an event happens, and consistency issues between the multiple controllers that we will need. Moving beyond purely technical challenges, there are architectural questions that academia and industry are exploring. One is, what should be the protocol to program the data plane? Should it be OpenFlow, and which itself is a standard that's evolving, something that allows more network function virtualization, that is, there's more general purpose compute embedded in the network devices, white box switching or programmable data planes. We're not going to talk about all of these, and certainly it's likely that there will be multiple solutions for different use cases. But this is a space that is actively evolving, as is the space of what are the right higher level control abstractions that run at the centralized controller. Looking at the OpenFlow protocol or even the early Knox example that we saw, that's far too low level for most of what we want. Right? We generally have a goal, something you're trying to get done in the network. I want this part of my network to be properly segmented, or I want traffic to flow through load balancers properly. I want to express that high-level goal without worrying about the low-level details of matching certain fields and packets, right? But what are the right abstractions that can cover a good set of use cases, and whether we need special controllers for special uses? These are questions that are, again, evolving. In the context of those significant challenges, we have, however, seen deployment of software-defined networking. And with those challenges, that really takes a killer app. So what were the early killer apps for SDN? That's an interesting question. And another interesting question is, I haven't said anything about cloud computing so far in this lecture. Where does the cloud come in? Well, it turns out that a couple of the early killer apps for SDN were very relevant to the cloud. One of them is virtualization of multi-tenant data centers, where we have thousands, tens of thousands of tenants for which we're spinning up VMs and virtual networks in real time. Very well suited to a programmatic model. And second, inter-data center traffic engineering, where we're trying to drive our expensive network that connects our cloud sites to the maximum utilization possible, right? Because in the wide area, we want to get every bit of bandwidth that we can in that expensive network. And again, this is something that if we want to get the best possible utilization, we actually need more interesting algorithms that is, again, very well suited to an SDN programmable model of the network. So something that both of these use cases have in common is that they were special purpose deployments targeted towards a specific use case with less diverse hardware and controlled by one entity, which made the deployment easier. And second, they were applications where the existing solutions weren't just a little bit inconvenient, they wouldn't work. They wouldn't have achieved the goal. So what we're going to see in the upcoming lectures is focusing on these particular use cases in the context of cloud computing and looking at case studies for systems that were built to address them. All right, so we have now seen how to build a high-performance data center. So what now? We just spin up some virtual machines, give them IP addresses, and we're done, right? Well, not quite, because we're building a cloud, and the point of the cloud is that it is shared among multiple parties. We get economy of scale, okay? And it turns out that if you want to share the network among multiple tenants, there's a bit more work that we have to do. So what we're going to talk about today are those key needs for building a multi-tenant cloud data center. So we're going to have several key needs that we'll discuss in this lecture. Agility of the network, strength, constitution, dexterity, and charisma. Sorry, that's the wrong list. Agility, location-independent addressing, performance uniformity, security, and preserving semantics of traditional networks. So let's dig into these. Now, most of these stem actually from agility. What do I mean by that? Well, that's a word that's been used to mean using any server for any service at any time. The point of that is that we'll be able to get better economy of scale because we can pack compute in as best we can and get high utilization. If we ever have constraints on what we can put where, it's going to be a lot harder to make full use of all our compute resources. And second, we'll get improved reliability, because if there is a planned outage or an unexpected outage, maintenance, we'll be able to move a service anywhere else so that it can keep running uninterrupted. Now, what do I mean by a service here or a tenant? This can be a customer renting space in a public cloud, or in a private cloud, it's essentially very similar, an application or a service that's running in the private cloud. So we can think of that as an internal customer. And the considerations are pretty similar. So let's look at our picture of traditional data centers. So here's our traditional data center network. We've got these 8 racks. They've each got a top-of-rack switch, and then we have aggregation switches and the routers at the top. All right. Now, we're going to, in a traditional data center, place services in the data center. We will have multiple services, and they are generally siloed, meaning one rack or maybe a part of the cluster is devoted to a specific service. Okay? And what's the problem with that siloing? Well, first, you might have reserved space, but the service at any given moment in time is not using all of it, maybe only a small fraction. So you get poor utilization. And then on the other side, if the service is trying to grow bigger, you have a difficult time expanding. Okay, because you may have to hit a wall or you jump over to another cluster. And it's not as fluid of an expansion as we would like. Remember, we want compute to be as much as we want whenever we want. So what happens then when we try to jump out of the silo? If we want to expand one of these surfaces, the purple service, move it over into that other rack, well, we immediately hit a practical problem here that these racks are generally assigned different IP subnets, okay? Because those subnets are used as topological locators so that we can route, all right? But now we're trying to move some service over there. We're going to have to change its IP address. And we have a hard time changing IP addresses of live running services, okay? So this is one of the key problems. What we want is the ability for the tenant's IP address to be taken anywhere, independent of the location in the data center. And the tenant should not even notice that it has changed location. Now, the next problem is also about something that the tenant might notice if they move. So let's say, again, we put that purple service, part of it, over on this other rack. Processes within the main rack there that are communicating are going to be able to communicate at full line rate, maybe 10 gigabits per second. But if you happen to be communicating between that rack and part of the application that's located elsewhere in the data center, we might have a very large oversubscription ratio, which means that if many hosts are trying to communicate across the core routers in the data center, they'll hit bottlenecks. And perhaps as much as a factor of 100 or greater, if there's a lot of communication between both sides, will be about 100 times lower throughput than communicating within the rack. This is how some traditional data centers have been built, with that much oversubscription at the top. Okay? So this is definitely something that will have a severe effect on application performance. So what we want, the next need for to achieve agility, is performance uniformity. Wherever we put the VMs in the data center, okay, so we've certainly got to be able to handle addressing so we can get the packets there, and then we have to get them there efficiently. So wherever the VMs are, they will see the same performance and latency, throughput and latency, regardless of where we put the VMs. So we're making progress. Now we can have much smaller units of compute that we've divided our services into, and we can put them anywhere in the data center. And they're all over. They're next to each other. They may be on the same physical machine. And in that environment, we have potentially untrusting applications and users sitting right next to each other. Okay? And we're going to have some kind of isolation between those users, because otherwise there can be inbound attacks, whether that's malware or denial of service attacks. We want to protect our tenants in the data center from each other. Okay? And this is true both in the public data center as well as in the private cloud. Because even in the private cloud, we want to minimize the amount of trust we have. And it might be a very large organization with thousands or even 10,000 internal applications. And you don't want them to have to trust each other. Okay? So in either environment, we want security for isolation between the running services. And this has come to be known as what's called microsegmentation. So segmentation is the separation of different regions of a network that's traditionally used in enterprise networks. You might have different departments or buildings on different segments of the network. Microsegmentation refers to a much finer-grained division and control of how data can flow, rather than the granularity of, say, departments, at the granularity of applications, services, tenants. Right? So we will be able to completely isolate if we want, or control just the data flow between pairs of applications or tenants that should be actually allowed. Finally, as we mentioned, we may have thousands of applications, thousands of different applications in a large enterprise. And these applications, they may be legacy applications developed over decades. If we want to support a large number of applications like that, we've got to preserve what their expectations are for what service the network provides. So we've basically got to match the service, the functional service, of a traditional data center. Okay? And what that means is not only layer 3 routing, but we're going to have to support layer 2 services, service discovery, multicast, broadcast. And what this is leading us towards is a virtualization of the network, providing the service that these applications expect in a virtual network that seems to them just like a traditional network all to itself for that one tenant or that one application. And then we're going to have to share these virtual networks in a single data center. So what we'll see next is a case study about how we can achieve that.
So Brighton, what have we learned in this lecture? These problems that we are talking about, segmentation and being able to use resources across multiple racks, these are not entirely new, right, in the cloud setting. Even in the enterprise setting, where you just have different teams in your enterprise running different applications, they have different owners, you need to address some of the same issues. You need to provide isolation across them. You need to be able to use multiple racks. You need to spread applications around. So what's entirely new here?
Well, what's new is that we now have a good way of solving those problems that have existed. So being able to allocate resources much more quickly and a much finer granularity so that we get more efficient use of compute in a shared infrastructure. And then that leads to the need to segment connectivity for security in a much finer granularity with microsegmentation.
Right. And it also seems like here you're changing the granularity of the problem a fair bit, because you have all these tenants with very dynamic needs. You need to run services in your data center that are very finely distributedly coordinated. right? You have to have, we're not talking here just about designing a topology, settling it in one time, or figuring out a routing scheme once and letting it run. We're talking about a continuous process where you're optimizing your use of resources.
That's right, and that distributed coordination or orchestration of the systems that will happen in the cloud behind the scenes from the perspective of the tenant is something that we can address with software-defined networking principles. So we'll see that next time in the case studies of network virtualization systems.
Looking forward to it.
Hi. In the last video, we took a look at some of the key requirements that we need to build a multi-tenant data center. In particular, agility, and to achieve agility, location-independent addressing, performance uniformity, security, and preserving the semantics of traditional layer 2 networks. Today, what we're going to do is talk about a case study of a system called VL2, which was one of the earliest virtualized data center designs that was publicly described in SIGCOMM 2009 from Microsoft Research. This design influenced the architecture of Microsoft Azure, and you can check out a bit more about that in a talk by Albert Greenberg that's listed on the slide here. Now, this is a case study, so we're actually going to see some characteristics that come together from both previous week's ideas of physical topology and routing, as well as what we're focusing on today in this week in network virtualization. So some of those ideas will come together in one system, and that's why this is a pretty nice paper to read. All right, so the paper begins with a measurement study that leads to some motivating characteristics of data centers. So the first is that increasing internal traffic is a bottleneck. So the paper mentions that the traffic volume between servers in the data center, in their measurements of a cluster of about 1,500 servers, is about 4 times larger than the external traffic, either to or from the servers outside the cluster. And also, they found that the traffic patterns within the data center were unpredictable. So what the authors in the paper did was take traffic matrices in 100-second buckets and classify them heuristically in about 40 categories of similar clusters of traffic matrices. And then over time, we're plotting which of these clusters do we see appear in the measurements. And what you can see here is that over time, it's actually changing very rapidly, and there's no apparent pattern to what the particular traffic matrix is. Okay? So the result of these measurements, these characteristics, it leads to points of direction towards a good design, which is to have a non-blocking fabric. And again, this is an idea that we've seen before, where we're able to achieve high throughput for any traffic matrix that we see. Okay? As long as it respects the line card rates, the NIC rates of the servers. Right? Those will be, let's say, 10 gigabits uplink and downlink from each server. And subject to those constraints, the network itself, the fabric joining together all the servers, we don't want that to be a bottleneck. So that's what a non-blocking fabric means. Now, another characteristic that's interesting in this paper is looking at failures in the data center. So they analyzed about 36 million error events from the cluster. And a few things that they found were that 0.4% of those failures were resolved in longer than 1 day. And so they took a while to be fixed. And 0.3% of those failures eliminated all redundancy in a device group. So it was a correlated failure that, for example, could take out all of the uplinks of a switch. So what this is pointing to is that failures, individual failures, can be serious. And it's going to be hard to make an individual device extremely reliable. These numbers look pretty small, but when we're trying to achieve 3, 4, 5 nines of availability, they become significant. So the direction that this points us towards the design is a close topology. So this is a particular kind of non-blocking topology that we can build that is scale out instead of scale up. That is, we're going to have a larger number of components forming the backbone of the network rather than a small number of beefier components. Okay, so putting together these ideas brings us to the VL2 physical topology. So we're moving from this traditional network design over to a close network, which will look pretty familiar. This particular design is a bit different than the fat tree paper that you read because of different line speeds and port counts, configurations of switches. So how do we route in this physical topology? Well, there was another conclusion of the measurements that the traffic is unpredictable, so that means it's difficult to adapt, right? So this leads us to a design that is what's called oblivious. Oblivious routing, meaning that the path along which we send a particular flow does not depend on the current traffic matrix, right? So we're going to be able to locally decide at each switch where this traffic should go without some larger scale global coordination. Now, Valiant load balancing is an idea that comes from a paper by Leslie Valiant for routing on hypercubes. It's a theoretical paper. We're not going to go into the algorithm and proof there, but the key idea is that what you do is you take an arbitrary traffic matrix and you make it look like a completely uniform, even traffic matrix. And the way we do that is by taking the flows and spreading them evenly over all the available paths. Okay? So we can do that by sending the flows to each of the top layer switches. Okay, now, we do want to keep each individual flow on a single path, so we're not going to achieve perfect Valiant load balancing. The flows are going to be a little chunkier rather than having each of them split evenly over all of the possible paths. But this is the intuition, that we want to spread traffic as much as possible. Okay? So what does the implementation of that look like in this particular design? Let's take a look. The first thing we want to do is spread that traffic over the top level switches, which are called intermediate switches in this design. Now, to do that, what VL2 does is it assigns those intermediate switches an anycast address. Okay? The same anycast address for all of the switches. So then a top of rack switch can send to a random one by just using that single address. And if we're using ECMP, we will use a random one of those paths that are shortest. Well, all of the paths are shortest because all of those intermediate switches are the same distance from the top of racks, right? So what ECMP is going to effectively do is give us the full breadth of possible paths to any one of those switches just by naming the single anycast address of all of the intermediates. Okay? Now, we could have named them differently. We could have named the intermediate switches with different IP addresses, but by using a single anycast address, the top of rack switches don't have to know if there are any changes in the membership, like a failure of one of the intermediate switches. Okay, so ECMP lets us select from one of those paths from the universe, and so one will be picked from any particular flow. We send it to that intermediate switch. Now, that outer anycast address is wrapping an inner header that actually has the destination address in this design, so we'll forward it from there onto the destination. Now, it's useful to note here how this compares with the simpler design of just having a single address for each of the destination top of rack switches and using ECMP to go along a random path, shortest path to one of those. How does that compare to this design that has this intermediate step of the anycast address? Well, it has a similar effect that we're going to choose a random path to that destination top of rack switch. Okay, so the paths selected are going to be similar. This design with the anycast address will result in smaller forwarding tables at most of the switches, which may be a consideration for some networks depending on the scale and the hardware used. There's a famous quote that's attributed to David Wheeler: all problems in computer science can be solved by another level of indirection. Okay, so let's apply that idea here. In the context of networking, another level of indirection, like a pointer, well, that's an encapsulated packet, okay? An outer header and an inner header, okay? And if we want to solve the problem of running any service anywhere, that's a trick that will come in very handy. So here's what VL2 does. There's an application, or you can think of it as the tenant layer. Okay? So the application or tenant of the data center is going to see what's called application addresses. These are location independent. Okay? Same address no matter where the VM goes. And they're going to see the illusion of a single big layer 2 switch connecting all of the application's VMs. Now, the physical network, on the other hand, is going to be using a different set of IP addresses called locator addresses. These are going to be tied to the topology in much the same way that IP addresses are usually used, right? Where if we move from this rack to that rack, we can't use the same IP address. But that's useful for the physical topology, for physical routing, because it tells us about location. So we will use those locator addresses within the physical network and just do regular layer 3 routing via OSPF. Could have used BGP there, they used OSPF. Okay? So the application gets what it wants, the physical layer gets what it wants, but in the middle we have to translate between them. And this is the layer of indirection, or we might call it a virtualization layer, which is a word I'm choosing here, not from the paper. What we do in the virtualization layer is that we're going to have to maintain a directory server that maps the application level addresses to their current locators. Okay? And then VL2 has agents that run on the servers that will query the directory server and find that AA to LA mapping. And then when it sends a packet, it will wrap the application address in the outer locator header, which can be used by the physical fabric. All right, let's see how that works in an end-to-end example. Okay? So we're going to start on the bottom left here, where an application is trying to send to this destination, 20.0.0.56. Okay? Now that's an application level address. It could be anywhere in the network. Okay? So this goes to the agent that runs on the same host. Okay? It's going to encapsulate it with the locator. But how do we get the locator? We send that AA up to one of the directory servers, okay, saying where is this application level address? And we're going to get back the locator as a response. Okay? And then we stick that in the encapsulated packet. And if you look at that encapsulated packet there, you can see 3 destinations. The innermost is 20.0.0.56. That's where the application wants to get, the other application somewhere in the data center. Next, that's wrapped in 10.0.0.6, which is the locator of the destination. And finally, we've wrapped it in 10.1.1.1, which is the anycast address of the intermediate switches, which we talked about before. So that's for our ECMP routing, to assist our ECMP routing. Okay, so after we've done these multiple layers of wrapping, we send the packet then out into the fabric, and it's going to be ECMP'd out into one of those intermediate switches. Let's say it's this one. Okay? Now when the intermediate switch receives that, it's going to do one layer of decapsulation, strip off the anycast IP header, revealing the next header inside, which has the destination in terms of the top of rack switch. Okay? So then we send it over there. That top of rack switch is going to, one last time, decapsulate the packet, leaving the AA destination. That is the application level address of the destination, so that it gets sent to the right host. And then the host agent delivers it to the application. So that's the end-to-end walkthrough of how VL2 works. Now, let's take a step back and see, did we actually achieve our goals? Did we achieve agility? Okay, well, one of the things we wanted is location-independent addressing. Did we get that? Yeah. Okay. The application level addresses are completely location-independent. All right? Because we've decoupled identifier and locator, this lets us locate the VMs anywhere we want. And this is a concept that's come up a lot in networking because the IP address its use is overloaded. It's used often both as a identifier and as a locator. So in other words, when you move in traditional networking, your IP address changes, and this can break applications. So we're essentially fixing that by saying, OK, we'll have two different IP address spaces, one for identification and one for location. All right, so good job there. Layer 2 network semantics. Yes, I didn't talk too much in detail about this, but you'll be reading the paper. And that agent that intercepts the packets also handles the appropriate layer 2 broadcast and multicast by translating them in the right way with the information from the directory server and multicast in the IP fabric. Okay, so it does that simulation or emulation, really, of the layer 2 behavior. However, we do have to note that both of these achievements do require this layer 2.5 shim agent running on the host. Okay? But it's not too hard to see how, instead of running that shim agent on the host, the same concept, the same mechanisms can transfer to a virtual switch running in a hypervisor. Next, we wanted performance uniformity. Did we get that? Yes. So the close network is non-blocking. It's not oversubscribed. Wherever you go, you'll be able to get the same throughput to any other location. We get uniform capacity everywhere. And ECMP provides good, though not perfect, load balancing across those paths. However, performance isolation does depend on the tenants backing off to the rate that the destination can receive. Remember, we're always limited by that rate on the end host NIC, and the fabric is guaranteeing that it will never be the bottleneck compared to that NIC. But what if we overload that NIC? Well, then we can get some performance interference. And in your quiz for this week, you'll be trying out a little example of that. So you'll see that a bit more. The paper also does leave open the possibility of some future work, which deals with faster load balancing. It leaves open the chance that, yes, although the traffic matrices are changing pretty quickly in the data center, you might be able to do something that also reacts quickly. And if you read the Conga paper, which was optional reading last week, you saw an example of that with end-to-end across the Tor information about what paths are congested. Finally, we wanted security. We wanted isolation among the different tenants. Okay? Now, VL2 can do a kind of security by having the directory system allow or deny connections. It can choose whether or not to resolve an application address into a locator address when it receives that request. So it's the right sort of direction of an idea. However, this segmentation is not explicitly enforced at the host, at least as described in the paper. Okay, so we'll have to do a bit more enforcement to really get that guaranteed network microsegmentation. All right, now one more question. We started out this week talking about software-defined networking. Where is the software-defined networking in this system? I didn't even mention the acronym once. Well, take a look at the directory servers. These directory servers are providing logically centralized control, right? They orchestrate the locations of applications dynamically. They control the communication policy, what pairs can communicate. Right? So this is very much the centralized control plane idea of SDN. The host agents, on the other hand, provide a certain kind of dynamic programming of the data path. There's not an explicit general purpose API there, but it's performing many of the same functions. So this was an important early paper in cloud data center network design that introduced some important concepts. What did you think of it, Brighton? I agree completely. When I read it, I was beside myself with excitement. But at the same time, we have to say that there are some system details here that are generally not implemented in production today. So what do you think are the enduring takeaways of this paper? Well, I think there are several key points that have endured into modern systems. First, this was an early paper that introduced a scale-out non-blocking close network with ECMP for traffic oblivious routing within that network. And then to achieve network virtualization, it introduced separation of virtual and physical addresses in the data center. And these are orchestrated with a centralized control plane. So those are ideas that we see even in modern designs today. And some of those we'll see refined in the VMware paper on NVP that we're reading next. My thoughts exactly. Hi, okay, so today we're going to look at our second case study on a multi-tenant cloud network virtualization system, which is NVP, the network virtualization platform that was introduced in this paper, Network Virtualization in Multi-Tenant Data Centers, by Teemu Koponen and co-authors in NSDI 2014. And this comes out of a product developed by the Nicira startup that was acquired by VMware. All right, now, we saw last time in VL2 what the system was trying to do was build a virtual layer 2 network. Okay? And we're moving in the same direction now, but there's a couple architectural ideas here that are going to be pretty different in NVP. And one of them is the service that we provide is going to be not just a layer 2 network, but an arbitrary network topology. Okay, so many of those will be a single layer 2 switch that connect all of the virtual machines for that particular tenant. But sometimes you'll want a more complex network topology. For example, some layer 2 switching connected to layer 3 routing, because maybe this application expected to be deployed in an environment where there was a layer 2 broadcast domain and a separate other layer 2 broadcast domain that weren't connected. So the idea is we want to replicate the environment, that arbitrary network environment that a particular application or tenant was expecting, and allow us to move that into the cloud. Okay? So what do we need of the physical network? Well, the physical network might be a close network that we've come to know and love, but actually NVP is not going to depend on what that network looks like. It's just going to expect to see any standard layer 3 network, a bunch of servers with IP addresses. And we're not going to dip into special mechanisms on the top layer switches or decapsulation on particular top of rack switches or use of anycast. We're just going to see a regular layer 3 network, and the virtualization is going to happen in software outside of that. Now, the service and the physical network are brought together with this network hypervisor layer. And here the intuition of this architecture that we're seeing on this slide is an analogy to virtualization of servers, where we can take an arbitrary machine and run it on unmodified hardware, and the virtual machine doesn't even know necessarily where it's running. Okay? And the virtualization layer decouples that virtual and physical environment. Okay? So what NVP is doing is much more explicitly building a network virtualization layer that separates an arbitrary network service from an arbitrary physical network. What is that service that it provides? Let's look in a little bit more detail here. So we might have this virtual network that the tenant wants to build with a layer 2 switch connected to a layer 3 router connected to another layer 2 switch. Okay? What does that mean exactly? So in NVP, that is modeled as a sequence of data path elements that represent those switches. Okay? And these data path elements, each one of them is a open flow forwarding table. That means the table will match on a certain signature of packet headers and take certain resulting actions like dropping the packet, modifying certain fields in the packet, or forwarding the packet on. Okay? So the idea is that we can model the switching and routing gear with the right sequences of the right OpenFlow tables that we set up. Okay? So walking through it, we have a virtual machine, okay, and it's going to send packets through what it thinks is its NIC, okay, that go to the network virtualization layer that realizes that this particular tenant virtual machine is connected to this particular virtual network. And the first hop into that virtual network is this layer 2 switch represented by this logical data path. So the packet is going to make its way through each of the tables. It's going to be checked by the inbound ACL, access control list table, and then will be handed off to the layer 2 forwarding table, the outbound ACL, and then sent out of this virtual network element, the layer 2 switch. And the hypervisor, the network hypervisor, will realize that, all right, that network element is now connected to this logical layer 3 router. The packet again proceeds through these hops, is again mapped by the network hypervisor into the last virtual switch, and there it reaches the end. Now at this point, going through this software data plane, we now have determined what is the output location of this particular packet in the virtual network. We know which virtual port it's going out, in other words, which virtual machine it's destined for. Okay? And at that point, all of this still occurring on the sender side host, we tunnel it to the final destination across the underlying layer 3 network fabric. Okay? So that walkthrough is the network service. So we're a little more explicitly providing two interfaces here. There's a packet abstraction where virtual machines are able to inject traffic into the virtual network. And there's a control abstraction where the tenant was able to define this entire virtual network pipeline, that sequence of OpenFlow flow tables. That's the interface that the tenant is given, at least the lowest level interface, that the tenant is given to be able to program their virtual network. Okay, so how does this get built into the overall system? So we start with our underlying physical fabric. And what NVP sees is a bunch of hosts with IP addresses connected to this fabric. Now, some of those servers are going to be running a particular tenant's virtual machine. All right? And that tenant, let's say, wants this particular control abstraction, this particular virtual network. It decides to construct this layer 2 switch, layer 3 router, and another layer 2 switch. Okay? So using APIs at the network hypervisor controllers, it's going to say, OK, here's the service I want to define. Here's the virtual network I want to define. And the controller will then instantiate that. It will program the underlying software switching data plane, which is at the virtualization layer of each of those servers on which the tenant's VM resides. Okay? And that is the virtual switch that it's actually programmed is called Open vSwitch. And notice that the virtual network, an instance of the virtual network, is present at each one of those servers where the tenant's VM resides. Right? So when the VM injects packets into the virtual network, we are on the local copy at that server processing the packet through the pipeline till we know the destination, and then it gets tunneled with tunnels that we now set up between each of these VM pairs, okay, to the final destination. All right, so that's how the system comes together. Now, building this system did bring several performance challenges, and some of them are at the controller side, because there's a lot of state to compute here, right? We are ultimately computing a full virtual network state and full instance of the virtual network at every host with the tenant's VM. So it can locally do that virtual network processing and decide what the ultimate destination of the packet is. Okay? And also we have to set up tunnels connecting each of the VMs. So if you have n VMs in a particular tenant, each one of them has to connect with n-1 other VMs. So we have on the order of n squared tunnels. Okay? So one part of the solution that NVP adopted is that this total state is not recomputed from scratch at all times. There's going to be changes, but you want to do that incrementally. You want to make incremental changes. And that's done automatically, not by hand, not with a hand constructed state machine, but with a declarative language that NVP developed called nlog to specify the data path and automatically make incremental adaptations. A second part of the solution to the performance challenge is that the controller does not compute the low-level forwarding tables of every instance of the virtual network. Okay? What it does instead is it computes a higher-level representation of that called universal flows. That's an instance that is good enough for any one of the hypervisors hosting that tenant's VM. Okay? And then it's sent out to these physical controllers that more locally compute that universal flow abstraction and translate it down to the exact open flow forwarding table entries at that particular host. Now, there are also performance challenges. After we solve the performance challenges of the controller, there are also performance challenges at each host. Okay? So first, we're processing in software, entirely in software, this data flow pipeline. Okay? And there can be many elements in that pipeline, and we're doing it in the software virtual switch. That can be slow. Okay? So one solution here is that NVP does send the first packet of each flow through this entire pipeline, does the computation. Okay? But subsequent packets of the same flow that will be handled the same way can be cached, so to speak, in the kernel of the operating system. Okay? And now this is done rather than with the complex matching operations that appear in OpenFlow. Once you know the result that should happen to that particular packet, you can cache it with an exact match. Exact match on the packet header in certain fields produces this result. A second challenge here is that tunneling interferes with TCP segmentation offload. We call it TSO, allows the operating system to offload the work of splitting up a data stream into smaller chunks to be sent over the wire with TCP and some of the checksumming and so on, offloading some of that TCP dirty work to the hardware NIC, network interface card. Okay? And if we're tunneling the packet, slapping an IP header on the front, an additional IP header, the NIC doesn't see the TCP header where it expects it to be. So the solution here is an approach called STT, where we add a fake outer TCP header that's there just for the convenience of the NIC. So what we saw this week was one of the first killer apps for software-defined networking. We needed to automate control of a rapidly changing dynamic environment. It wasn't suited to any past solution. So we can see in NVP, I think very strongly, the features of SDN architecture. We have an API to the data plane. We're programming Open vSwitch with the OpenFlow protocol. We have a centralized controller that's orchestrating that programming. And then we have high-level control abstractions, both in terms of the declarative language and also applications that construct certain kinds of virtual networks so that the tenants don't have to program OpenFlow themselves. So we see, the data plane API, we see the centralized controller, we see the high-level control abstractions. Those SDN principles come through very strongly. But next week, we're going to see another example of an SDN system that is also very much SDN, but ends up looking very different. So rather than providing arbitrary virtual networks as a service, it's going to be oriented towards optimization of network performance and utilization. And rather than programming software switches entirely at the edge of the network, we're going to have more direct control of forwarding hardware. And we'll see that as we move next week into looking at the wide area needs of cloud networking.
Hello, today we have with us Rob Sherwood, who is the Chief Technology Officer at Big Switch. He's also leading the Open Network Linux project. He was part of the original software-defined networking team at Stanford, has a PhD from University of Maryland, and in the long past was a network and security admin. Hello, Rob. Welcome.
Hi. Thanks for having me.
Of course. And of course, we also have Brighton, who's joining us remotely today.
Hello there.
All right. So Rob, why don't you give us more background about what you do in your day-to-day life, both as the lead of the Open Network Linux project and at Big Switch?
So let me talk briefly about what Big Switch is. It's a bit of a marketing pitch, but it really is the elevator pitch that I use, and I have pitches to people in an elevator. Kind of the idea is that if you look at who's doing the most interesting things in networking, it's not the traditional network vendors. It's the companies like Google or Facebook or Amazon. You know, they're building their own switches, they're building their own networking stacks, they're doing completely different, new, interesting things in networking. And a lot of that, fascinatingly, is actually not to build better network products for other people. You know, they're not trying to compete with Cisco and Juniper. They've just decided that, you know, the stock networking products that they can buy off the shelf don't work for them. And so what Big Switch is actually trying to do is saying, all right, well, let's see if we can learn from some of the things that they're talking about, some of the things that they're doing, and actually productize that for the people who can't afford to have 250-person development armies working on their network. And so we have two products. They're all based off of merchant silicon with what I will call a bare metal switch. That is a switch where you can put software on it yourself. And Big Switch is a pure software company. We put software on other people's switches, and we use SDN technologies. We use OpenFlow. We use centralized controllers so that you can actually manage collections of little switches like they're one big switch. And that's actually how we get the name of the company. And so, you know, historically, people have paid for these kind of like big chassis-based switches. They paid a huge premium for them, and they've been locked into these vendor proprietary worlds because they don't want to have lots of points of management. Like if you imagine if your entire network consisted of lots of little switches and you wanted to make a change in one part of the network, you want to make a change that affected lots of things. Like so maybe you wanted to add a kind of a global ACL. You'd actually have to log into each of those switches manually, type a series of commands, hope you didn't screw up those commands, and then all those switches and kind of like manually audit that. And there aren't really good automated processes for doing that right now. Like a lot of companies will put together kind of screen scraping technologies or things like that. So basically, imagine you've got this big box. It has slide-in cards. One of those cards is what's called the supervisor card, and that's actually where kind of the brains of that switch is. And then you would have multiple what are called line cards, which are the things that actually have lots of ports. And generally, depending on the switch, you may have independent cards that are called fabric cards, or the fabric might be built into the backplane. But think of that switch as a little private network. And so each of those line cards acts like little switches. And what people have never thought of, but you know, this is how the network runs today, is that supervisor card is effectively a controller. And what happens is you connect those line card switches to the backplane, which maybe transitively connect to the fabric switches, in a class topology. So there's actually, you know, it's entirely possible for the network inside that box to be oversubscribed, to have packet loss problems. And what ends up happening is, you know, very smart people have worked on, you know, how do I engineer the network inside that box to be as unobtrusive as possible, so that you don't have to worry about, I mean, it really is an issue that you get different performance between two ports that are on the same line card versus two ports that are on different line cards, because maybe there's oversubscription across the backplane. But the critical property, the reason why people pay for the big box rather than lots of little switches, because the little switches are actually much less expensive and you can get them from lots of different companies, is actually the single point of control. They want to be able to log into the supervisor, and then basically have the entire rest of the switch abstracted down to one point of control. So you can say, add a route that comes in this interface and goes out this other interface. You don't have to worry about if they're on different line cards or the same line card, or if they cross some sort of weird internal boundary that's an internal function of the engineering. And so people pay a lot of money for that. People pay, vendors build bigger and bigger switches, bigger and bigger routers that internally have all sorts of network-like properties that are abstracted away from you. And even to the point where there's actually out-of-band Ethernet, a control channel built into those big switches. And there's a protocol from the supervisor cards to the line cards, like internal to this out-of-band network. And so it's something that you, the user, don't think about at all because it all just kind of works magically. But if you imagine you add a route, you log in. When you log into this box, you're really logging into a supervisor card. It's a PC. It's running user space software like anything else would have. And if you change an access control list or you add a route, what happens is that supervisor card will go and, using the out-of-band Ethernet channel and using this update protocol, will actually update the forwarding state of all of the line cards and all of the fabrics and all of the things that need to be updated by some internal update algorithm. And so that's how switches work, like big switches work in the network that's already deployed. And so the analogy is that supervisor card really is just a controller, in an open flow sense of things. And these switches, you can think of these line cards, you can think of the line cards as leaf switches in a class topology. And you can think of the fabric backplane as the spine switches. And having a single point of control really is the value that people want, because they don't want to be able to manage. I mean, we're talking upwards of 40 switches, in a rack. That could be a huge number if you had to log into those individually. And what's fascinating is, while people haven't really thought of or really named this out-of-band control plane protocol that in existing switches runs and manages all the forwarding updates, I call that closed flow, because it's exactly the same thing that OpenFlow does, just in a closed proprietary manner.
So the internal network, the physical network of these big switches are, those networks are kind of non-trivial to build to get the illusion that there is no network there, that it's just, all the cards directly connected to each other.
Exactly.
And that's kind of a, it's very similar at a smaller scale, what you have to do within a switch to what modern data centers are moving to now, across racks.
And what gets interesting is you get advances like companies like what Broadcom have done, which is they've actually, if you think of the building block of these bigger switches is like a single packet forwarding chip. Like they've actually, the capacities of a single packet forwarding chip have really kind of gone hockey puck exponential in terms of their actual packet forwarding performance. And they've also pulled a whole bunch of other chips into one single form factor. So you get these system on chip designs where you get PHYs that are in the same package. You get all the packet forwarding. You might get L2 packet forwarding with L3 packet forwarding with MPLS all in the same chip. And so if you think of that fundamental building block, as a network device manufacturer, you're like, well, do I build a 1U pizza box, which is functionally the amount of ports I can get out of one chip, and I connect these 1U pizza boxes together? Or do I build that chip onto a line card, and then another one of those chips onto the fabric backplane, and actually create the big iron chassis version of that, the big switch version of that? And at some point, if you actually follow the traces through the motherboard versus the cables that you'd have through the data center, they actually form the same topology. This is a class topology. And so there really is a direct analogy between these two. It's just historically people have paid more for the big box.
Right. We're trying to, I mean, if you look at data center scale, we're trying to build the whole network to be a switching component as a whole that applications can't notice, ideally.
Exactly. And so if you look at, for example, Facebook's Altoona data center, what they've done is they built a 3-layer class topology. And class topologies have this exponential scale-up metric where when you build them the right way, there's basically no oversubscription, meaning that if you look at the bandwidth you can get between two ports on the same card versus 2 ports on any other two arbitrary ports, that's the same capacity through the back end of the network.
Right, a non-blocking network.
Yeah, non-blocking network. Yeah, and the fact that you can kind of build a network out of smaller boxes like that, but still manage it through a central point of control, I think that is one of the big tenets of what I think of as an SDN design. You have some sort of external controller that manages, in the case of Facebook, for example, hundreds of switches as if they were one big switch. That's kind of the value, because that means that they can have, instead of a team of 30 guys who, if they have to make a global config change, have to log into hundreds of switches, they can log into one controller, make the change, and have the controller transitively and automatically manage that config change.
So what you're saying about the merchant silicon switches, what kind of interfaces do these provide?
These devices are incredibly complex. There's all sorts of pathologies that have only historical value, or they figured out how to wedge the MPLS into the L3 tables because that was how it made sense from a chip layout perspective. I think there's actually very few companies in the world who actually want to program their network directly. And for those companies, we have an open source project, Open Network Linux, but that's a very small minority. Most people want to have effectively a high-level policy language. They can say that these sets of hosts are supposed to talk to these sets of hosts, but not this other set of hosts. And if set A and set B are supposed to talk, I want you to go through one of these 5 firewall instances and load balance it dynamically. I think that's a policy statement that more people want to consume, and they just want the network to do the right thing given a statement like that.
So Rob, you mentioned there's people want to work with higher level abstractions.
Yeah.
So continuing the analogy of large chassis switches with many line cards, kind of providing that more centralized control. What are the differences between those old physically big switches and where people are going with SDN abstractions now for expressing those higher level policies?
So I think the policies are very much the same. I think what's happening is, so the example I always give is like when you log into your bank and you get a pop-up that says like, hey, do you have a student loan? Let's think about this, or do you want to refinance? That's an application that's running in the back end of your bank that's trying to make the bank money. Like anytime you refinance your mortgage, the bank makes money, right? And so what's happening is that's a web application which is on the fly as you log in, doing a complex business analysis of, do you have a mortgage? What's the rate on that? Can they make you a better deal? And doing a presentation in real time of that. Now, in order to make that happen, there's a whole bunch of security stuff that happens because that database has really sensitive information, and there's business logic that happens, and there's all sorts of isolation that happens because there's lots of applications that run in parallel that all make the bank money. That they don't, like if one of them goes rogue or gets compromised, they want isolation. All of those things have just gotten more and more complex. As banks go online, as banks have more applications, as crazy people, the banks come up with new and different ways to make money, to provide value to their customers, that network just gets more complicated. And if it were all one big switch, you would still have a bunch of complex policy programming tasks to do. And so really the value add, you could in theory imagine doing it independent of what the physical box looked like, but the value add of at least a company like Big Switch is that we can automate all of these tasks and provide an easy policy language to say, all right, we're going to tag all of these hosts this way, and they have this role, and they have those hosts gets tagged this way and they have this role, but then when you're talking between these two roles, these are the sets of things that I want to happen or not happen. And historically, people have tried to do this with VLANs, and they've tried to do this IP address ranges, and that works until you run out of VLANs, or you run out of IP address ranges, or your company buys another company that uses that same 10/8 IP address space. and this is not at all unique to banks. Like every company that has a website in this day and age has back-end web applications that they try to do to use improve user experience and performance, and ultimately to make them more money. And so it's really the complexity of trying to run a data center has increased so much that, you know, how do I manage these policies? Worse, how do I debug these policies? Like we've got this cool feature where, and stop me if I'm talking too much about Big Switch, but I think these things are actually, it's important for people to know. But where you can give it 2 points on the network, and we will give you an analysis of both the physical path through the network between these 2 points, as well as the policy path. So, you know, this host can't talk to this other host because you hit line 12 of ACL foo. And, you know, if that's not what you want, then change line 12. And, you know, we use that to build up what I think of like unit tests for the network, which is like, here's a bunch of pairs of hosts that are representative of policy in the network, and here's the expected policy of yes, they should be able to talk, no, they shouldn't, or like they should go through like a NAT process or something like that. And let me rerun that every time you make a configuration change, just like you would have unit tests in a program. It's those types of things that, you know, in theory you could accomplish without SDN, but I don't know how you would do that as a sane person. Like you need an automation. You need automation. You need a controller that pulls together lots of different data sources and makes it readily accessible to start making these queries.
So you mentioned Open Network Linux, right?
So, Open Network Linux is a very fun project that I started. So I mean, Big Switch as a company focuses on the people who want the networking problem to go away. And there's a large fraction of people, and you know, I put myself in this other camp that is like, I love the networking problem. That's the thing I'm actually most passionate about. And you know, the commercial products basically do their best to make people. You could think of it almost like the iPad for networking. Like it's got one button. You push the button, and it does most of the things you need. But it's not the Linux. It's not the thing that actually like exposes all the details to you. Completely separate from that, I have my Open Network Linux project. You guys can check it out on opennetlinux.org. It is a bare bones Linux distribution for these bare metal switches. It's all open source except for the Broadcom SDK bits that we can't open source. But critically, they have open APIs so you can program to them. It solves a bunch of problems that nobody wants to think about. Like, you know, if the fans aren't spinning at the right rate, you can actually burn up the switch. And the switch has a lot more fans, or you know, are the LEDs blinking the right way, and that changes, you know, for every box. And so what Open Network Linux does is provides abstractions so that you, the programmer, don't have to worry about all of these things. You can just worry about, you know, I want to insert this routing rule into the chip, and I want it to go at line rate.
Well, once you have that, when you have, you know, well, first bare metal switches, and then a reasonable operating system, Open Network Linux, to use on them. That, you know, that will give more opportunity for technology that's kind of embedded inside the network, not just a centralized controller of the network, but sort of more intelligence within the network. Is that something that's happening, starting to happen? You think we'll go in that direction?
Definitely, although there's kind of, I think people have this vision of all I need to do is be able to run a user space process on the switch, and then I can have a firewall or something like that. Yeah, there's definitely possibilities along those lines, but there's an important kind of architectural limitation for folks to think about. The way these boxes are designed, it really is very much like a server. You know, it probably runs x86, has a PCI bus. And the chip, you know, for example, the Broadcom chip is a device on the PCI bus. Like if you type LSPCI, you see, okay, you know, there's a Broadcom Trident 2 there. What gets interesting is actually the PCI bus is the biggest bottleneck of the system. Mm-hmm. So like a Broadcom Trident 2 is capable of doing something like 1.4 terabits of traffic in and out of it. And there is what is logically a port that goes out onto the PCI bus, but you're limited there to the PCI bus speeds, and it's not even, you know, a 32-lane PCI 3 interface. I think it's 4-lane PCI 2 or something like that. But net result is you've got like, you know, about a gigabit of traffic that you can get between the switch CPU and the switch packet processor. And so if you think that you're going to deploy the world's next best generation firewall on a kind of low-end data center switch, this is actually going to be a big physical bottleneck for you. Now, that said, there are both designs, and you can actually build them up pretty much yourself, where you actually take front panel ports of the switch and plug them directly into a server. So that's where things start to get interesting. And there's a bunch of interesting designs where you say, all right, well, maybe using DPDK and a fast. Are you guys familiar with DPDK? You know, the brief thing about DPDK is it's a set of libraries from Intel for very fast packet forwarding on commodity servers. And if you believe some of the performance numbers, they've been able to get, numbers I've seen are 6 gigabits of processing per core, scaling linearly. So if you have a 32-core system, you can get close to 200 gigabits per second. And you've got the appropriate Ethernet cards to do this. But what that means practically is, if you want to do really interesting kind of non-ASIC-based packet processing, if you had an entire rack full of servers, you could actually do that at full line rate just by distributing the load across those. And that's where things start to get more interesting. There's designs. There was a paper by a former colleague of mine who's now at AT&T, Vijay Gopalakrishnan, at ONS this year, talking about a router farm, which is the idea of data center switches can't hold big BGP tables. They don't have buffering that you would need for wide area networks. But maybe if you had a whole bunch of servers in front of them to act as very small virtual routers, maybe you could actually build kind of what looks like a farm of routers out of a bunch of data center switches and a lot of data center servers that replace a high-end router, but it's much more programmable, and you get interesting designs like that. Those are things that I find pretty fascinating.
That is pretty cool. So some of what you're discussing also touches on what the Open vSwitch project is trying to accomplish, right? Moving packets quickly in a programmable way.
Yeah.
So what do you see the relationship as?
So, I mean, I would say there are a lot of projects which are trying to do what I would call software-based forwarding. Open vSwitch is probably the most famous. There's a DPDK version of Open vSwitch, so something that leverages those technologies. There are a bunch of companies that are actually trying to have small amounts of hardware offload. There's a bunch of other virtual switches that you can leverage. I look at more the kind of the architectural and hardware limitations of software switching rather than the precise software that's on top. There are notable differences in performance between the different software packages, but not on the scale of difference between software versus dedicated hardware. Like so, just to give you round numbers, if you believe the DPDK numbers, then that is a 32-core server, which is a pretty beefy server, can get about 200 gigabits per second of forwarding performance. If you go to kind of the current latest, greatest network processor and FPGA designs, you can get in the order of 600 or 700 gigabits per second. If you go to the latest ASIC designs, you can get like 3.4 terabits per second. And what you're doing is you're trading off programmability for raw packet forwarding performance. You basically, if you are considering, how do I build an X? It's like, well, okay, I can build it straight from ASIC. Can I build that functionality straight from ASICs? Well, if the ASICs support that functionality, they don't support high-end firewalling functionality. They don't support high-end load balancing functionality.
That also raises an interesting possibility. What if we wanted a bit of both? We want a lot of both performance and programmability. So what if these chips were a little bit programmable? So they're not as generic as FPGAs, but they have some programmability, just the particular things that networking pipelines usually use, right? So do you see that going forward?
Yeah, and I mean, it's one of these things where I think everybody sees value there, but you get into the next level of details. So ASICs are becoming more programmable. There's actually thousands of pages for how to program ASICs. network processors are becoming faster. FPGAs are becoming faster and cheaper. I'm trying to use less memory. x86-based platforms, which are the most programmable, are actually also becoming faster. I mean, it'll be interesting to me to see how long, how these different technologies play out over time. How many use cases where you need the programming capability of an FPGA or an NPU, but you need more performance than you'd get at an x86. Like, there's a small class of solutions that fall into there. Fortunately for those vendors, it's an important class of solutions, but my claim is it's getting smaller, and the question is what will happen over time. The designs that I really like personally are ones where, like I was talking about with the router farm work, or more generally with NFV, where you actually use the high-end data center ASICs as fast interconnects, where they're basically fast and dumb between relatively slow and programmable x86-based processing. And then it's just a matter of how many of these servers do I need to actually keep up with what looks like line rate, and what does that look in terms of the overall cost of the solution, the power envelope of this, because this is not a power optimized solution. Well, and the other thing is, what happens is, if you're going to build 500 of these, whatever the boxes you want to build, if you want to build 500 of these, that's one class of solutions. But if you're going to build 500,000 of them or 5 million of them, maybe you actually spin your own ASIC, right? And that's kind of one of the design trade-offs that people make as well.
Do you think there's a clear killer app for bare metal switching?
So my quip answer to that is, I think the long tail will be the killer app. So let me explain what I mean by that. So anything that's obviously going to make bare metal switching is more of a business change rather than a technology change. So the reality is that every switching company in the world already sells chips made by Broadcom. They sell them in boxes that are probably made by one of a list of 5 different Taiwanese manufacturers, and they put their own software on top. So, like, in the data center, at least, the switches are completely commoditized, and everybody is already building on bare metal switches. They just don't know it. And then the question is just, what are the use cases that people want to target that are not being targeted by the traditional vendors? And the traditional vendors are very smart. They're not dumb. They're going to target whatever is, they're going to target the top end use cases by however they want to figure that out. And they're good at their job. I think we can actually, companies like Big Switch can do a good job breaking into that top end use cases. But really, what happens to the rest of those use cases? In the traditional networking world, basically you're kind of given the middle finger and you're told, okay, you can't do that. Like, if like a random use case that is not going to get covered is, hi, I'm a grad student. I would like to tinker with your switch and see if I can validate if my new routing protocol is better than BGP. That's not a financially viable use case for a large company to pursue. But that can be hit with bare metal, which is say you download Open Network Linux, you download OFDPA, you get this up and running, you run your thing. And at the end of the semester, basically you turn the box over to whomever, and the next guy comes down the pipe. And maybe some point somebody comes up with some crazy new application because he had the chance to tinker around with the hardware. Really, by letting people play with the hardware, the hope is, and I think we're already seeing this, we're going to see the same thing that we had happen with cell phones, that we had happen with PCs, is that you just get this like excess of people who are developing applications for it, and a couple will bubble to the top. I think right now we haven't quite got that network effect going, and we're really starting to get like a very small number of people starting to play with it. It's very much kind of a hobbyist tinkerer community. But I do think that will come, and what will be the killer app over that? I really, that's where I quip. Like, I don't know that it's necessarily going to be any one thing, but it's going to be the ability to do whatever you want.
So going forward, Rob, what do you see as the Rob Sherwood dream for a data center? What does that look like from the virtual machines out to the inter-data center fabric?
So the dream for the data center would basically be all of the middle boxes and all of the complex packet processing functions are basically moved into software. So that includes firewalls, load balancers, NAT devices. If you're in like a mobile carrier world, all of the evolved mobile packet core EPC functions. All like there's a whole bunch of stuff that happens in the carrier world, which is just like you buy a dedicated box to do that. It's like all of that becomes software. Everything has incredibly high bandwidth capacity using kind of merchant silicon technology, including up connect to MPLS through the core. And so you could have something like one of these WAN routers built from software data center components, like I'm talking about. And that will, and critically, it's all managed through probably not a single centralized controller, but a hierarchy of centralized controllers, where this is what computer science teaches us. You solve scaling problems with hierarchies, right? And you would have one, a controller for some unit of compute and storage and network, and then if you wanted to build data centers bigger than that, you would have multiple of these, and if you have too many of these, then you have a controller of controllers, if you will, and that's a system that kind of scales up.
So this is how you solve the problem of scaling to a very big distributed system and making it reliable.
Exactly. And I mean, really what and kind of the insight here is distribute the data plane and centralize the control plane. Although centralize the control plane is a little bit of a misnomer, because what ends up happening, and you get this in our solutions, and this is actually how you, going back to the chassis-based big switch design, there are some packet processing functions that you offload onto the line cards, right?
Mm-hmm.
Like if you ping a router's interface, what's actually happening at the low end there is a packet's coming in the front panel port of the switch. That router interface is actually, it's not a physical thing, it's a logical concept. But that line card has a knowledge of that logical, because maybe you have 5 ports on a VLAN, but they all have access to that router interface, right? They're all on that. So imagine the gateway interface.
We should probably explain the gateway interface a little bit for our students.
So, like, if you're watching this at home, right now your laptop is talking upstream to whatever it is its next hop router, and call that 192.168.1.1, and that box probably has multiple physical ports. Maybe it's think of it as your wireless device. Now that interface 192.168.1.1, if you plug into each of those ports, you can ping that. And so what ends up happening, how that's implemented, particularly if you weren't plugged into a wireless router, if you're plugged into a big switch, is that interface exists logically across all of the line cards where that's programmed, and packets show up on the port. The ASIC that manages that port says, I'm not actually smart enough to generate an ICMP echo. That's a higher level function. So let me punt that packet to the CPU that's local to the line card.
Mm-hmm.
And so there's a CPU local to the line card, and in a line card-based design, it's probably not an x86. It's probably some sort of embedded CPU, but it's a Turing-complete general-purpose CPU. And that says, okay, I got an ICMP echo request for this IP address. Check, yes, that is one of the IP addresses I'm supposed to reply for. Let me generate the ICMP echo response, send it back to the ASIC to push out the reply port. That's how that function works. Now, you could have implemented that by actually sending not to a local CPU on the line card, but actually up to the general CPU on the supervisor card. But that eventually doesn't scale once you get to enough ports. And there's a whole bunch of functions where it just makes sense to distribute that functionality down to the line cards. And so what does this mean in the SDN world? What's the analogy? Well, the analogy is you could actually do lots of processing at the controller. You could actually, via OpenFlow packet in, you could send everything up to the controller, and the controller could handle everything, and you could send it back down, but eventually that doesn't scale. And so what you end up doing is exactly the same design trade-off, which is you say, all right, well, there's a whole bunch of low-level packet forwarding things that I don't necessarily need to handle the controller. They don't actually affect policy. They can actually be offloaded onto individual switches. And at least in our designs, it's things like ICMP handling, it's LACP handling. There's a whole bunch of kind of link layer protocols that don't actually affect the large functioning of the switch. And that's how we get scale, is to offload these functions down to individual switches rather than up into the controller.
Right, right. And there's that kind of hierarchy of control and optimization and in like Google's B4 design, for example,
Exactly.
for their wide area SDN controlled backbone. So that's one reason for reliability, for latency and efficiency. You're going to have multiple controllers.
Yeah.
But let me spin this in another direction to multiple types of controllers. So if looking at sort of where SDN has gone so far, there's maybe 2 or 3 sort of killer apps for SDN that are actually all related to the cloud, and I'd be interested in which ones you'd pick as what are the killer apps, but certainly data center control and wide area networking optimization are 2 that have been used in practice.
Yeah, and I think it's actually useful, at least for the class audience, to separate out where is the technology useful versus what's the thing that makes the easiest business case. And certainly companies like myself are actually trying to target the intersection of that. Mm-hmm. But so the easiest business case is clearly data center. Probably exactly as you said. The second easiest business case is the WAN.
Optimization of traffic for the WAN or other functions?
A whole bunch of things, right? So there's a huge SD-WAN movement, which is trying to, I'm not sure if your students know, but basically what ends up happening is most large companies that have like offices around the world or something like that have basically 2 types of networks. They have a high quality of service, like with service level agreements, VPN network. Think of that as their own internal network, but they're probably leasing the lines. Mm-hmm. And then they have kind of a best effort standard internet network. And the VPN network is pretty expensive for them to use. They really only want to use it for sensitive traffic or maybe internal video conferencing or internal video or internal voice over IP or things like that. And they want to dump other, like if you're surfing YouTube, like imagine you're working at some large bank, but you don't work in the central office, you work in the branch office that's down the street. If you surf YouTube, you really want that traffic to go on the general internet network, but if you're trying to access the company's internal sensitive data, that should go on the physical internal network. There are a growing collection of what companies that sell what they call an SD-WAN solution, which is an intelligent device that would basically sit at the branch point there that decides, even though this traffic is ostensibly destined for the internal network, can I offload it to the general purpose network and do some interesting routing techniques or interesting encoding techniques to effectively get high levels of quality of service over a best effort network.
Got it.
There are people who are doing that. I think that there's actually, in the carrier space, huge space for more intelligent PE routers, so provider edge routers. So if you imagine, from your laptop to your home DSL modem to the DSLAM, the DSL aggregation multiplexer device in your central office, there's then a provider edge router, which is the thing that connects your central office to the backbone of your ISP. That is actually one of the biggest bottlenecks on the internet these days, because that's actually one of the massive points of congestion and oversubscription. That's where all you might have 10,000 people in a metro area connected to the same central office, but then that central office might have 8 by 10 gigs of bandwidth going up. And if each individual subscriber has, say 10 megabit connection, there's a huge oversubscription rate that happens there. And that's fine with statistical multiplexing, but as everybody starts to use Netflix, as everybody starts to use internet more and more, there's less statistical multiplexing.
Mm-hmm.
And so I think that there's an interesting space for optimization there as well.
So do you foresee some of this technology going deeper into the internet as well? So in some sense, the data center acts as a laboratory for testing out these ideas at scale, although it has many, many differences with the internet at large in terms of economic incentives and such. But nevertheless, some of this technology, do you see ISPs, for example, using some of this in their ISP networks, the internal network for an ISP?
Very much so, and really, a couple of a big thing that dominates the business case is how fast do these networks turn over, right? So people add new data centers very quickly. They change out data centers very quickly. On that scale, kind of like the PE routers and the provider routers, actually the ones in the core, those turn over maybe least quickly. And so while I think the technology is directly applicable to that space, it's just the way the business side of that works in terms of how often do they buy new routers, how sensitive are they to new technologies, how much pain do they have there. That will probably, well, I think that's one of the biggest benefits. It will also be probably one of the slowest adoptions.
So then, this is really interesting. We talked about, a few use cases. There's for SDN inside the cloud data center, across the the WAN backbone connecting the cloud data centers, and then in, I guess, enterprise networks going out to the either the public internet or their private network. Do you think these variety of use cases, are there going to be multiple different kinds of controllers that
definitely
are targeted towards these individual use cases, or are we going to have sort of one controller to rule them all?
Well, and if you look at my idea of the controller hierarchy, certainly I think the bottom layer, you'll have lots of different controllers. Now, can you then create a controller of controllers which is capable of managing different types of controllers? And in some cases it actually doesn't even necessarily make sense, right? So not to dwell on Big Switch, but it's the one I know the best. We basically sell 2 different complete controller stacks. And there's a lot of code reuse there, but the idea is one is for managing production data center networks, and the other is for managing monitoring networks, which even if they're in the data center, they're 2 completely different use cases, which are probably run by 2 different teams of people. So there's actually not even an interest in interoperability. In fact, it's the opposite. I want to have my thing and you can have your thing, but you shouldn't be able to touch mine, or vice versa. Interesting technology needs to, if you're actually interested in deploying it and having impact, you need to also take into account the organizational issues, like who would actually deploy this? Are they incentivized to deploy this? Like, do they actually benefit from deploying your thing? As well as the business issues, which is, how can I make the case for someone to deploy this that will save them money or make them more money? Because if they don't, it's not going to get deployed. It doesn't really matter how good of an idea it is. And it took me a while post-grad school to digest that, but I think it's actually pretty important.
Hi, everybody. Today we are here with Martin Casado. Martin runs the networking and security business unit at VMware. And before that, he was a co-founder of Nicira. And before that, a PhD student with Nick McCune at Stanford University. And we're going to be talking about multi-tenant data centers and software-defined networking today. So hello, Martin.
Hello.
Thanks a lot for taking the time to chat.
Yeah, delighted to be here.
So let's start with maybe a little background about you yourself, how you how you got into SDN, the genesis of SDN, since you were one of the ones there at the very beginning.
So I guess the quick sketch is after my undergraduate, I worked for the defense agency. Actually, I worked for DOE, but I worked for the national laboratories, and I moved into the intelligence agencies. So this is after 9/11, and it was pretty clear at the time that market forces didn't really create technologies that were suitable for these environments, right? You're assuming that you're being attacked by nation states with resources of nation states, and so on the compute side, it was pretty. On the compute side, we were able to program operating systems or whatever in order to kind of be more fit for these new for this type of environment. But when it came to the network, we just didn't have a model for changing it. Basically, whatever you got from a vendor is what you could use. And so when I left that and I went to Stanford, we just looked at this problem of like, okay, so how do you change the networking architecture to make it more programmable? And so we did some early work, SANE and ethane. And then that led to OpenFlow, and here we are. So that's kind of the crooked path. So
what would be an example of what you want to program more quickly? Because I mean, if you think about the way the network was originally envisioned, there wasn't much to do, right? You put in your packets and they get delivered, and that's the end of the story.
Yeah, so the original motivation was actually just saying, I want some high-level policy that's going to dictate how things can communicate on the network. So if you take the context of like the intelligence environment that I worked in, so there were these guys that were not technologists that had come up with policies on how they wanted the network to work. They're like, well, this group of people can or cannot access to this type of information from certain locations at certain times of day or whatever. And so there's these policies from like the security wonks and the lawyers and the regulators. These policies were written basically in like, say, email documents or Word documents. And the trick was to get the infrastructure to obey these, right? Now, if you told like a systems person this problem, you're like, I have some way that I as a human speak that I want like an operating system to behave. What they would probably do is create a domain specific language. They'd create a compiler for that language. They'd write declarations for what they wanted to do in that language. And then they would, implement a runtime. And so when we were looking at this problem, like, so we know how we want the network to operate, right? We know who we want to communicate and when and how, but there was no way to like basically, create a high level language and then compile that down so it was enacted throughout the entire network. And in fact, that was, what we first built was a high level language, with a namespace that includes users, that includes data, that includes things like that, and then is enforced throughout the network.
And that was the ethane work that you're referring to?
Yeah, it started at SANE, and then that went to ethane, right? So SANE was, it was kind of first go, and we're like, all we care about is security. So it's like kind of like the most paranoid implementation of a network architecture ever, where even like paths were these onion encrypted source routes. So even if you got, even if you got a hold of one of these things, you didn't know where the packet would go. So we were even hiding topology information. And then ethane was a much more practical, kind of more backwards compatible go at it, which was focused more on manageability than kind of like real paranoid security.
So that was the beginnings, and then so how did the work change while you were doing your PhD and then leading into the startup?
Yeah, so we built the system ethane. We'd actually ran it in the Gates building, which is the computer science building at Stanford. And so we'd kind of rewired the entire Gates building to run across our switches, and we were like writing some high level policy. We took it down like 3 or 4 times because it turns out it's actually really hard to write policies that support the types of communication mechanisms that happen in normal networks, right? I mean, networks are super chatty. They rely on things like broadcast for discovery and so forth. So it took us a while to kind of figure it out, but we got that working. And then that was about the time we're like, we were mostly just focused on how do you have like high level languages drive networking at the time. And we're like, this is actually a fairly general way of building networking or doing networking, which is if you decouple the control planes, which has been suggested many times before, but now you can turn it into a distributed systems problem. So like when you're managing state on the data path, you can have stronger consistency guarantees. You can use higher level languages to do that. And so then we're like, so there's two things you need. You need the ability to talk to switches in a very general manner. So then we created OpenFlow. And that software platform, which before was basically a language compiler, you can generalize to something that you can run multiple applications on top. And we created Nox, which was kind of our first go at a controller. And the idea is, you'd expose, data structures like a graph of the network, and you would have high-level language bindings so that you could run multiple applications that would, control routing or control security or do whatever folks wanted to. And so that was kind of the next step.
Got it. So then that, obviously had a lot of impact, that work, and you felt there was some opportunity to have some commercial impact as well.
Yeah, that's right. I mean, what's so interesting about this whole journey is I think that every step we learn a lot more, and so first we're focused on the protocol, the switch protocol, and we realized, whatever, whether it's OpenFlow or something else, it doesn't really matter. You just need to have these, sets of guarantees on the protocol. You need to make sure that you can keep state consistent. You need to make sure that you can efficiently track changes. Okay, but whatever the wire protocol is doesn't matter as long as everybody implements it. Then we thought, okay, we're going to build, these general purpose controllers, and everybody was super focused on controllers at the time. So there was probably 10 different open source projects on controllers, and everybody had their version of a controller. But a controller doesn't solve any specific problem. It's just a platform, right? So it was clear at the time, that there were networks hadn't really kept pace from demands in industry, especially in these large multi-tenant data centers, which we'll be talking about today. And we can talk more about that. And so we're like, what we're going to do is we're going to solve the operational problem in multi-tenant data centers. So, there's, compute had been virtualized, and that compute had been, gets resold to people, but the network architecture is fairly static. And so even though they can spin up things like VMs in any configuration they want, the network still required manual provisioning and so forth. And so we thought, what we're going to do is we're going to use this SDN approach to virtualize the network so you can make it as consumable and as flexible as compute virtualization. That was the idea. The big the big takeaway that we learned when we were doing that is, we were so focused on the controller, but it turns out actually writing an application is probably, 2 orders of magnitude more work. So just like the protocol itself wasn't super architecturally important. I mean, you got to make sure you got to get a few things right. It turns out the controllers aren't architecturally important either. I mean, whether you use any of the numbers of controller, because the application manages all the state and does all the distributed state management, that's where all of the complexity comes in. And so we started this company, Nicira, and it was to solve this virtual networking problem. We spent pretty much all of our time figuring out how to build the application for these data centers.
So the original design of kind of getting into the technical aspect of what Nicira built. Did you start with sort of okay, we're going to build a data center out of OpenFlow switches and build up from there, or did it start with a software virtual approach?
So yeah, it's a great question. So we actually started from the problem statement on back, and then we took like a number of goes at it, and then we kind of figured it out. So the problem statement was the one that I just said to you, which is more and more data centers look like big computers, right? And those those computers are being carved up and either used by internal developers or used for applications or resold in the public cloud or whatever. And that fungibility of the network as an infrastructure piece didn't exist. So we were able to carve up compute in any way that we wanted to, and even storage to some degree, but like offering networking services and different network service models on the same infrastructure, this still required human beings or buying more gear or whatever it was. And so the problem statement was, let's make the networking have the same operational properties as compute. That was the start. So then we tried a number of goes. A lot of this was based on heritage. So our first go was like, okay, what we're going to do is we're going to reprogram the switches. So we took a go at that for about a year, and we looked at that problem pretty deeply, and we realized that was actually the wrong solution. So there was actually two major trends that caused the big aha behind Nicira. So the first one is, if you looked at the time, and this is now we're talking 10 years ago, right? If you looked at mega data centers, how they were being built, and by mega data I mean the Googles and Facebooks and so forth, they kind of all had opted on their own just to build large L3 ECMP fabrics. That was it.
Mm-hmm.
So you have these, so their physical networks were super simple. They were just L3 fabrics, running OSPF or BGP or whatever, and they would use ECMP to efficiently use all links, and that was it. And so they would set them up, and they wouldn't touch them again. And so, you could see that, that had actually decoupled forwarding from features. So they'd rewritten their applications to do things you normally do in the network. So their applications would do security and do discovery and do fault isolation and so forth. All of that was done in the application.
Mm-hmm.
So you look at that architecture and you're like, it gives you a lot of the same properties of SDN, where you use, high-level languages and software to handle a lot of the features, and then the physical network just provides forwarding. The second thing that we noticed was that at the time, in 2009, the number of virtual ports, these are ports connected to virtual machines, was quickly approaching the number of physical access ports globally. So companies like VMware were becoming the largest networking companies. And so you had these two trends, like big data centers were going to these very simple physical networks where software was providing the function, albeit not in an SDN way, but on an edge way.
Right.
And networking, the access layer to the network, which is architecturally the right place to put functionality, and we can discuss why that is. All of the ports were going into this virtual layer. And so we were like, what would be cool is if you could, so now we've got all these VM connected to virtual ports. How about we use SDN techniques to control these virtual ports and implement all of traditional networking functionality there, L2 and L3 and L4 through 7 services and traditional management interfaces, and do it in a way that you don't have to change your application. You don't have to be a Google. It's like you can use traditional applications and traditional interfaces, but you get all of the operational properties and CapEx properties and OpEx properties of these big data centers. And so that was kind of the major shift that happened about a year into this year, around 2009, that we kind of realized that controlling switches directly was probably the wrong approach.
And did you give up anything by not having access to the hardware in that way?
So for data centers where you have an insertion point at the edge, so it's whatever it is, whether it's in the OS, whether it's in the hypervisor, I don't believe there's anything that you need to do specifically with the hardware that's outside of operations and management. I think that the best technical architectural approach is to push all service model intelligence to the edge.
Mm-hmm.
The physical network should do load balancing. It should be able to isolate elephant and mice flows, but you can do this through normal packet marking so that, for example, heavy hitter flows don't fill up queues and provide latency for the smaller flows. But I actually don't think from a performance standpoint or from a functionality standpoint, you give up anything. In fact, I think you gain a lot, because now functionality has a general purpose processor and it's distributed, so you don't have to do it at an aggregation point like a top of rack switch. The one caveat is operations and management, which is I think you need to be able to talk about the physical and the virtual layer to do things like debugging, trend analysis, and so forth. But I do think horizontal interfaces are the right way to do that, so that you actually have cross-layer visibility, and then you build tools to allow you to debug.
I see. So then the core physical network worries about packet delivery, reliability, and performance, basically.
Yeah, and the way I like to think about it is if you see how chassis have evolved, like if you buy like a networking chassis, you've got line cards and you've got a backplane. For performance reasons, for functionality reasons, often you put the intelligence in the line cards, and the backplane just provides packets reliably with the quality of service that you're asking for, and that's generally the model. So now the intelligence is on the x86 servers, which already have to do tons and tons of stuff anyways, right? I mean, if you think about it, if a compute node sends a packet on the network, I mean, from some high-level language to some high-level language library through some guest operating system to the hypervisor, all of this is part of the communication chain. So you add a little more functionality there, which you can totally attribute to that whole software path anyways. And that all just becomes part of the sending. You only have to do that at 10 gigs or whatever the NIC is on that thing. And then the physical network is just responsible for getting it to the next point. So I think it's a nice division of functionality.
Yeah, that makes sense. And there's, so, digging in a little more though, you mentioned one thing where, okay, what exactly is the interface between the software and the hardware so that the hardware can do its job? And I think one thing you mentioned was, well, maybe you have some kind of marking of packets of their type of sort of the class of flow. Is that right?
Yeah, well, I mean, I think that, if I was to say, okay, so what should the physical network do? What's its job? I would say, okay, it should get a packet between point A and point B in a complex graph, so in whatever topology, as efficiently as possible, and obeying to a requested class of service from the edge, right? So I would say, so what does it need to do? It needs to be able to look at a destination header and send it to the right destination, and it should be able to look at some sort of QoS markings and be able to enforce that class of service or those guarantees. I've found in practice that there's kind of, there generally aren't enough queues to do like object or entity level class of service. Like, if you have like a large public cloud where you have hundreds of thousands of users, it's very unlikely that every user is going to get their own guaranteed bandwidth, because that would require a queue in the hardware per user. So instead, what we see practically are, you have a certain network that is optimized for a certain set of queues that are just dedicated for high throughput flows, and you've got a separate set of queues that are for low latency flows. And if you can identify these at the edge somehow, you get these nice running networks. But that means that the physical network really is just about destination forwarding as far as the interface outside of OAM. So it's just destination forwarding and looking at bits. Now, when it comes to OAM, operations and management, of course, it's a much richer interface.
Got it. Yeah. So right. So then, if at the edge you can mark like your, your in-memory database queries versus your backups and larger flows in those two classes, then you can get essentially almost as well as you can do practically.
Yeah, that's right. And actually, that was, it was obvious there were many benefits for pushing this intelligence into the edge, right? You're not at an aggregation point. You have a general purpose processor. But another one is you actually have deeper semantics because you're co-located in the application now. And this is a perfect example of what you just brought up, which is, I mean, as long as I can remember in networking, we've been trying to guess what a heavy hitter flow is, right? By doing some sort of like stochastic approach or some Bloom filter or some craziness. But you can never really guess using counters whether a flow is a long-lived flow or not, or a heavy hitter flow or not. But once you start pushing intelligence to the edge, you have all the access to all of the state. So, we do tricks today even where you can do things like look into the TCP send buffer. So you're already there. So I can look and I can say how much outstanding data is. And if there's a lot, then you can go ahead and mark the packets as a heavy hitter flow or not. And so not only do you have potentially application semantics, like the application, but you actually have all the system semantics as well. So what the application was requesting for. And then, you can mark that, like, as you said, on the outer packet, and then the physical fabric can enforce that.
How far do you think that should go or needs to go into the application? So, you mentioned you can look into the TCP send buffer. Okay, that's something that the OS can do, or maybe the hypervisor, without the application even being aware. So that's more information than the network has.
Yeah.
You have to go even further into the application?
Yeah, so I think that's a super interesting. Yeah, I think this is a very good question, which is, how much should the network know? And in my opinion, you do want very deep context and semantics, but not for like stuff like efficiency and performance. I think you want it for security. So when it comes to efficiency and performance, honestly, I think that if you look at any application, almost always the problem, I mean, we're networking guys, we like to talk about the network, but like we measure end-to-end packet delays all the time from one VM to another VM. And honestly, like just memory handling in the hypervisor, like buffer copies and stuff, dwarf anything that happens on the network. I do believe that there's a real problem between heavy hitters and non-heavy hitters, but I think that, that is sufficient context for getting good performance. And honestly, if we didn't have to deal with like older versions of TCP, I'm guessing just actually even turning elephants into mice, taking heavy hitters and then chopping them up would be sufficient in almost every case. I mean, again, if we're very honest about end-to-end packet delivery, almost all of the performance issues are on the edge or with storage. This is my experience in practice.
Right. Mm-hmm.
But so on the performance side, I think you're okay without deep semantics. That said, when you're doing things like security, like regulatory compliance, where a regulator comes in and says, in order to handle PII or in order to handle credit card information, you need to have this type of workload separated from that and so forth. Now, to enforce those policies, you do want to have deep insight on what things are being done, because it's part of the namespace of what you're trying to get done. Like, my declaration is these types of people and these types of data, so I have to have that as part of my namespace. But then the discussion is, okay, is this now a networking problem anymore? And I would say, no, if it's on the edge, it becomes a distributed systems problem. But I do think to solve those types of problems, which are often attributed to networking, that you do need to have much deeper insight into the application.
But that security layer you're saying would be a separate layer from virtualization of the multi-tenant data center or even the network itself.
Absolutely, I would say that's a layer above, and it has much deeper semantic access. So if you look at, you should have like a policy layer at the top, and the namespace should surface all the stuff that you want to make declarations over. You want to say stuff like Brighton and stuff like Martine, different types of data. You want to be able to say all of those things, and it's also a cross layer. Like, policy always touches all pieces of infrastructure, compute, networking, and storage. So it's not just a networking thing. So that policy will compile down to abstractions that are decoupled from the physical hardware, VMs, virtual networks, virtual storage units, right? Mm-hmm. So that will compile down to a management layer that works over these abstractions, and then those map down to the actual hardware. I mean, I think that's kind of the stack. And so in the networking piece, for the physical networking, you should still just be moving packets, but there should be a virtual networking layer on the edge that exposes what look like physical networks, but are actually virtual abstractions. And then that should be driven by the policy layer.
Got it. So, so you made a point that was a good one, that, if we look at performance latency specifically, which is something that we're talking about in the class, if you look at where the latency comes from end to end, it's it's not propagation delay through the network, for example, which is, since we're talking about relatively short distances in the data center, speed of light. Right. It might be in some cases congestion, but it's you've always got that latency that you're paying to go up and down the host stacks on both ends.
Yeah. And
arguably, as we make more and more use of software and virtualization at the edge, maybe that problem we're making that problem worse. Are we, and how do we deal with that?
No. Okay, so I think this is actually the question, which is, we have like such a deconstructionist view of everything. We're like I study networking, so I'm just going to focus on the network. And I think having a holistic end-to-end systems view is so important to answering this question. And every time we add a layer, there are implications. So I actually just want to walk through. So let's say one VM sending to another VM something. So what normally happens? Let's say you've got some Python code, and that Python code is talking to some Python library, right? So now you've got that interaction, and the Python library is probably going to the Python interpreter, and that's probably calling some libc user space library, and that's calling the system call in the guest. So now you go to the kernel. In the kernel, so you've got all of this kind of software overhead. Now you're in the kernel, you've got the L2, L3 stacks, you've got all the retransmission timers, you've got all the buffering that's going on there, all of that memory management. That will trap into the hypervisor. And every time you do a domain crossing, you lose your TLB, right? You probably lose some cache locality. I mean, this is like non-trivial stuff. And then, you put the packet, you DMA the packet, and then it goes out. So if you look at that, like, that is a ton of software and a ton of memory handling that's going on. And in fact, the most expensive thing in the case of virtualization is actually that domain crossing between the guest and the hypervisor, because you do lose your TLB and you lose cache locality. Yeah. So for example, if a guest, so if you're like on bare metal, you can send packets at 10 gigs no problem. if you do it, but if you put it in a hypervisor, that number often drops down to, say, 2 gigabits per second. So it turns out the most expensive thing, like I said, is that domain crossing. So if you can somehow reduce that domain crossing, you get a lot more performance. So what is done in kind of modern systems today, so that was, so we were all looking at the network and we thought the network was bad. Then we started profiling it. We realized that domain crossing was very expensive. So if you do optimizations, for example, expose TSO to the virtual driver. So TSO is TCP segmentation offloading. So now you're saying, okay, if you send packets to me, if you send a TCP thing, instead of sending 1,500 bytes, which would be like like an MTU size packet, you can send 32K, these massive frames. And then we'll go ahead and do the segmentation in the NIC, for example. Now you get back to 10 gigs. So if you could reduce the interrupts between those two things by sending bigger frames, all of a sudden you get your performance back. And these days, VMs can send traffic almost as fast as without there being a VM. I mean, you can easily get 10 gigs out of these now, but the way that you got there is you understood what was happening on the edge. I mean, this was really like operating systems and computer architecture work, not networking work to get there. And so, I know that was a long answer. So yes, I do think we're adding a lot of overhead. And yes, I do think we can solve those things, but the way to do it is not make it a networking problem. It's making it a systems, operating systems kind of computer architecture problem.
Right. Yeah, and that's something that is kind of exposing, this one of the broader challenges when we move from sort of a more hardware-oriented world to a more software-oriented world. We have some of these growing pains.
Yeah, and also I would say it's also as the disciplines grow up and we realize that you can't, how interrelated they are, and you have boundaries moving. Like the access layer of the network is now basically an x86 problem. So those of us that have, like you and I went to school in networking, like I remember all my introductory classes, it's like L2 and L3 and TCP sawtooth and all this other stuff. And you realize that even doing switching performance now, you have to understand caching architectures. So there's clearly a blend going on in the discipline in order to provide end-to-end guarantees.
Okay, so so these were some of the challenges the Nasir, the company, and you worked through in order to get to high performance. Now, we've talked a lot about performance, a little bit about security. One of the interesting things I think is in where you started was building a way to build networks in a programmable way. And you started with high-level languages, and Nasira, kind of went towards a controller or an application, I should say, that was targeted towards a particular use case. Where do you think the SDN controller and SDN application space is going or should go in terms of solving actual use cases? Are there going to be controllers for specific problems? Are there going to be general high-level languages? How is that architecture going to shake out, do you think?
Yeah, I mean, this question really points to probably one of the three major insights that I've learned, or things that I've learned or I've noticed over the past 8 years, which is the following. I mean, we got so over-rotated on the controller. Like, we're like, this is, we're going to build this general tool and it'll make everybody's life easier so your mom can use Python to, write, networking apps. And it just turns out that that is so patently false. That, and I'll tell you why. I think that we got to the source of why, which is networking to scale is a distributed problem. It's a distributed systems problem. Right, and so, and in distributed systems, normally you're making trade-offs between state consistency and scalability. I mean, and the only thing that can actually make those trade-offs is the application. Like, it's like I don't know from a controller architecture what you as an application writer, what guarantees you need, what consistency models you need, or so forth. So we ended up building this second version of the second iteration of a controller called Onyx, and there's a paper Onyx. And so Temu and I, so Temu Component and I were working on this controller, and we're like, okay, so Nox was great, but it wasn't really a distributed system. We had very basic notions of distribution. So we're going to build a controller that provides all of the distribution components very generally. And an application can use those. So we'll have different distributed data stores and different distributed coordination mechanisms, like distributed locking and so forth. And that will make it much easier. But once you realize, and so we probably spent, I don't know, maybe 4 man-years building that. But once you realize is any application, I mean, the only way to build something truly general is you expose all of these options to the application. And so you're really pushing the complexity in the application. So now the application has to implement anytime you all of the actual choices, right? I mean, like it'll manage state. It has to choose whether it's eventually consistent or strongly consistent. And it has to do all of these things itself. And so you're just kind of moving the complexity bubble up to the application. And so if I do a comparison, like we built a network virtualization system, that was probably 100 man-years of work versus 4 man-years for the controller. And so I think that the industry is understanding this now, which, I mean, it does help to have a general controller platform, but because so much complexity goes in the application, I think these should be as thin as possible. And we should stop using the analogy to OS platforms because it's a very, very different. I mean, there's a much limited number of applications for a network, right? I mean, think about it. In compute, like, listen, we use the same machines to like solve physics problems, to do work, and to play Pac-Man, right? like compute is anything solving the world's problems. All applications for SDN are just to run a network, right? Like we don't like play Pac-Man on networks, and we don't solve physics problems. They're all for the network. So I think there's a limited domain, and I think each one of those has its own set of trade-offs. So I think we should have very thin controller layers, and then we really should focus on building out correct applications. And we don't need, because there's much less, there's orders of magnitude less applications for the network. I don't think we need to over-rotate on how much duplicate work we do in them, just because they're so distributed by nature.
Got it. Yeah. So okay. So we have a thin controller, and what does thin mean? Does that mean kind of a pretty low-level interface similar to OpenFlow?
Yeah. So what I would do is, so I would, and again, I mean, I think it's probably not super architecturally significant, but I would have a higher level interface to state management on the network. I always view, okay, so OpenFlow is some wire protocol, but you need some higher level state interface. So I like viewing the forwarding state in the network as basically a database. So it's a data state consistency problem. So I think that the controller should be like, okay, here's state, and if you manage this state, it's going to be consistent on the physical network. And you can manage one device, and you can manage across those devices. But any sort of distributed coordination you're doing, any sort of consistency guarantees, that's kind of up to you on how you implement that. And so I think actually like a wrapper over the wire protocol, like the wrapper over OpenFlow or whatever protocol you're using, is probably sufficient. And then you want to use whatever protocol like OpenFlow as efficiently as possible. So for example, if state changes down there, then you get the changes up here. You're pushing it down in an efficient manner. But I do think that just viewing that layer as a state management protocol is probably the right one, and having a high-level protocol-independent interfaces is sufficient. And this is just not a hard thing to do.
So the data that the controller exposes might be pretty low-level forwarding rules, matches and actions, and similar to OpenFlow or MPLS or other. Not that those are directly comparable, but they're dealing with certain kinds of matches and actions and packets. That kind of low level, but you don't want the applications to have to each implement the communication protocol with the switches, so you expose something more like a database of this information. Is that what you're saying?
That's right. I think so. I'd say that the forwarding information still exposed as basic forwarding information, but like the actual, it looks like a kind of a local cache of something that you're doing, and the actual state maintenance is something that's actually provided by the controller layer. Right. The thing that's difficult about, I've found about exposing to applications higher level abstractions, it seems that the way that we describe communication really is best described by action lookup, right? Like, I mean, and maybe if you're writing a new type of application, this isn't the case. But if you're running existing applications, they require L2 broadcast. I mean, that's just kind of an assumption that it's going to be there, right? All the packet headers, which are chiseled into 30 years of operating system stacks, assume IP addresses. It assumes L2 addresses, and so like the addressing structure and the service models are kind of baked in there already. And if you're going to be building a way that these actually work, you're going to be wanting to operate over these types of fields. And I think maybe you can evolve, if you're going to evolve the addressing layer at the edge, and you're going to evolve the basic expectations of the application for the network, like you don't get multicast, you don't get broadcast. If you start evolving that, then I think you can change the forwarding abstractions. But our first attempt was to use a high-level domain-specific language for managing state, and the problem is it just wasn't sufficiently general to manage legacy applications. And if that's the case, you always revert to doing it for it anyways. And so I think for the general purpose case, yes, you should just expose the low-level stuff. Maybe as we evolve applications so that you don't have L2, we can put higher-level abstractions or different addressing architectures that are exposed.
Yeah, and if you look at like Nicira's controller versus say, Google's controller for their wide area backbone, those are both you can call them SDN applications, but they're very different sort of applications and controllers.
Totally, absolutely, and I have always maintained, and I still do, that the problem of the WAN is very different from the problem of the data center. So if you look at the data center, I actually don't think that there's any networking that you want to do. There's no like path selection. I mean, in the data center, bandwidth is really cheap and it's all close together. So any path is almost as good as any other path. So just using simple randomization like ECMP will get very close to optimal, right? I mean, there's even a mathematical result, as on this, is like, ECMP will approximate valiant load balancing. And valiant load balancing, which is basically sending a packet to a random location and then the destination, is a factor of 2 of optimal for any traffic matrix. So I just think that entire problem is solved by the physical network in the data center, of moving a packet between point A and point B efficiently. Now in the core, that's absolutely not the case. So in the core, the choice of a path, the different paths are very, very different. They may cost a lot more money because the bandwidth's expensive, or you may not have a lot of bandwidth on a certain path. So actually intelligently choosing a path rather than just randomly selecting one is a very specific problem, and one in which global optimization actually makes a lot of sense. So I think the controller you would build for that, and certainly the application you would build for that, is very, very different than what you do for the data center. So I think even the idea of having the same controller for like the core and a data center may not make a lot of sense. Now maybe like that thin state management layer you and I spoke about, but nothing more than that. They're just profoundly different problems.
Right. So okay, so we've talked about these different application domains, and Nicira found a impactful application for SDN in the context of cloud networking. So since this is a class on cloud networking, let's focus on the cloud for a little. So there was this need to build virtual networks to support multi-tenancy in the data center. So that was one of the challenges to realize the cloud in an effective way. Where do you think cloud networking is going beyond that? Have we solved the data center problem? Have we solved wide area or other problems? Or where are we headed as the cloud evolves?
So I like to carve it out into 3 types of problems, and just to focus on the data center right now, which is where I focus on. I'm not clear what the problems are in the core. Honestly, it seems to me that the job of the core is to move packets between data centers. But when it comes to the data center, especially modern cloud data centers, here are the 3 problems. The first one's an operational problem, which is the time it takes to configure and provision the network relative to like applications and compute is embarrassing, right? I mean, it takes minutes or seconds to spin up VMs. It takes minutes or seconds to provision and automate the orchestration provisioning of applications. But traditionally, took a long time. So, so the direct impact, say, to business is if I want to get a job done, like deploying an application, onboarding a new employee, onboarding a new customer, whatever it is, spinning up a dev environment, it takes a long time. So if you reduce that time, if you reduce that time, say, to 0, there's value to whoever's trying to get something done, which is, in this case, the business. So I think the first class of problems is basically automating the provisioning and configuration of networking resources. So I think network virtualization does a good job of this, just like compute virtualization. So that's the first problem domain. I think that the problem space is well understood. All of the impact to people adopting this around the operations of this. They have to change their operational runbook. So it's actually, I think that we've moved out of a technical domain now to an organizational domain, and that's where the state of the art is there.
I see.
The second area that problem domain that's very interesting is security. You know, there's this old adage that we've been saying it for decades, but it's true that, you know, the majority of security is implemented at the perimeter, and there's technical reasons for this. So, like, if you look industry-wide, about 80% of security spend is on the perimeter. Yet the perimeter is only some fraction of the bandwidth, right? I mean, even in the most massive data center, you only have 100 gigabits per second going in and out of the perimeter, which you can probably use 2 x86 appliances to manage, right? I mean, it's just not a lot of bandwidth. However, the traffic within the data center is terabits of capacity. I mean, one top of rack switch is probably a terabit, you know, something like that, right? 48 ports down, 10 gigs down, 244 gigs up. I mean, that's a ton of bandwidth. And so if we're going to be putting networking services, in particular security services, on traffic that never leaves the data center, the east-west traffic, you have to handle tens of terabits of traffic in even moderate-sized data centers. And so, you know, that's a very technical problem. So again, you know, if you look at the cloud networking problem, you're saying, okay, I'm basically taking a big data center, I'm carving it up, and I'm allowing you know, people to use this carved up resource, and that often the traffic never leaves. So you now have to put security services on all of that traffic. And again, actually, network virtualization tackles this problem pretty well because it distributes all of these services and it runs it in the edge. There's a lot more work to do there because, as we spoke before, there's a lot of context you can get because you're already there on the application and you're already there on the edge. And people have only been able to distribute a couple of security services because, like, for example, distributed firewalling. And so if you think about it, you're taking something like a firewall or an IDS or you know, an existing security appliance, and you're chopping it up into little pieces and you're running it all at the edge. And this has only been successfully done with firewalling and IDS, to my knowledge. And so I think there's a lot more work to do there. And then the final one is inter-data center type use cases. So, you know, you've got automation, you've got security, and then the inter-data center type use cases is things like HA and DR between data centers. So maybe you want to migrate workloads between data centers for planned maintenance, you know, maybe lightning strikes and takes down a data center, you want another one to pop up. And so now you have to solve, you know, inter-data center connectivity issues. You know, you want to ideally do this without disrupting communication. And that's also kind of, there's a lot of we know how to do this technically, but you know, this is a much more difficult problem when, you know, you've got to have a bunch of different organizations agree to different types of technologies, and there's kind of a massive upgrade one. So if I go across those 3 use cases, I would say, like, automation, we understand the technical problems, I think, as an industry and as a discipline, but there's organizational issues we don't get. And there's a lot of tooling to make this kind of easier that I don't think we're there yet. Security, still tons of technical work to do. And, you know, getting better semantics on that, and just figuring out how to distribute these services. And then on the inter-data center type use cases, I think that, you know, we understand the technologies for these things. I don't think there's deep technical problems there, but, like, figuring out how to, like, roll out in legacy environments is incredibly difficult because people aren't going to just, like, implement Lisp everywhere or whatever your chosen technical solution is.
And do you think that's going to happen? So the second problem, so there's, you know, in the first case, these kind of human organizational problems. In the second case, with the threat surface is changing and broadening even quantitatively, right? You have much more traffic to process.
Yeah.
And you know, but I guess along with that, in the security challenge there's the technical challenge, but there's also this opportunity that you have much more context and information than you previously had only at the edge.
Yeah, absolutely. This is why, you know, I mean, I think that there's actually a ton of good technical work still to do because, you've got a global view, more visibility than you've ever had. You've got, now the ability to consistently manage state. You've got more semantics, just like you've said. And now we actually know how to build separate trust domains on the edge. So like you can have a separate trust domain running there where you can do things like remediation. So you don't have to like send a packet to a firewall to drop it. You can actually drop it within the hypervisor, which is a separate trust domain. And so it just feels like you can take a lot of kind of our understanding of operating systems and building like secure domains and operating systems, a lot of even like say like language constructs, and apply it to the network security problem and enforce it globally. So I just feel like there's so much work that we can do there. Then we're just starting. I mean, really the state of the art today is I've got a fully distributed stateful firewall that runs in every server. So it looks like you've got a terabit firewall, which is great, but like I mean that's actually taking like a very traditional piece of security equipment and distributing it, as opposed to fundamentally evolving it now that you're running an x86. And so I do think there's a lot of great technical work there to do.
Cool. And then the last problem of getting to the wide area, getting, you mentioned, HA, high availability and dynamic relocation, I think you said, of workloads.
Yeah, or disaster recovery. Disaster recovery.
Oh, disaster recovery. Right.
Yeah.
Now, is that something that you think, so these are getting to kind of very large technical challenges. Do you think, how do you think this will play out with, the hyperscale cloud providers providing these services versus, some entities building private clouds and, getting to that level of, very, high availability and being able to do disaster recovery? These are complex services to provide.
Yeah. So, so it seems to me that from a technical component standpoint, we understand what's needed to do things like high availability or disaster recovery between data centers. Like if you take anybody that's studied networking and you're like, okay, you need to make sure that you have you decouple an IP address from the location. They'll say Lisp, or
right.
I mean, we've got so many tools that we can throw at this problem. And we know all of these tools, whether you do something super stupid like I'm going to do /32 source routing. I'm going to advertise every time I move to a new location. To I'm going to use a level of indirection like Lisp or like tunneling or whatever. We know all of these. The problem is like these aren't implemented. This is a global problem. You're like, you have everybody on the internet connecting to a set of data centers, and so you need to affect everybody on the internet. So it becomes an internet upgrade problem, which is in order to do this effectively at the network layer, you're going to have to update all the networking components to do it. And I think that's why these problems are being solved at higher layers now. And I think a very interesting question, it's a little bit different than the question you asked, and we can get back to that question, but the most interesting question I have is, it seems that there's a race between the network layer evolving to solve problems and the applications evolving. And it seems like the applications are winning, right? I mean, if you look at modern applications solve a lot of these problems so that they don't rely on the network to do it, and they don't rely on the infrastructure to do it. So they have their own liveness timers, they have their own HA techniques, they have their, they're generally stateless, they do their own discovery, right? And if all of this functionality moves into the application because it's taking so long for the infrastructure to do it, it may be that the networking problem, just even on the global one, is getting packets between point A and point B, and don't worry about relocating, don't worry about movement. So again, I think to answer your question, my guess, if I was to predict the future, is that cloud applications, software applications that you get as a service are going to actually consume all of these things, and it's not going to be the infrastructure in the long term that provides it. Whether that is run by an enterprise or run by a big cloud service, my expectation is all going to go in the application.
Okay, well, on that prediction of the future, maybe that's a good note to wrap up on, and we'll check back with you in 5 years or so.
Right.
See where that went. So thanks so much for taking the time to chat, Martin.
That's
and you're welcome back anytime.
All right, thanks so much.
Okay, bye-bye.
Using virtually any popular web application today means you're communicating with a server in a data center. However, your connectivity to this service depends on the internet and is a crucial determinant of the application's performance. Data centers also communicate with each other over the internet, for example, for replicating client data across multiple data centers. When we refer to the cloud, wide area connectivity over the internet is as crucial a piece of the picture as data center network infrastructure. So in this lesson, we'll start looking at inter-data center networking, and in later lessons, we'll look at client connectivity as well. What you're looking at here is part of Google's wide area network as of 2011. It has 12 locations spread across 3 different continents. So why does a provider like Google need such an extensive infrastructure with so many locations across a wide expanse of the globe? There are several reasons. One is better data availability. If one of these facilities were to go down, perhaps due to a natural disaster, you could still have the data be available at some other location if it was replicated. That presents a natural advantage to using widely spread facilities. Also, it aids in better load balancing. If you have multiple facilities, you can spread incoming and outgoing traffic over the internet across a wider set of providers over a wide geographic expanse. In the same vein, this can help you mitigate denial of service attacks on a facility. It also helps improve latency to clients. If you're present in multiple parts of the globe, you can reach clients in different locations at smaller distances, thus cutting latency to them. So if Google operates some data centers in Asia, a wide range of clients across Asia can use those instead of having to come all the way to the US data centers. Over time, another aspect of this could become very interesting, which is local data laws. Several jurisdictions might require that companies store data from that country in that jurisdiction itself. This would obviously necessitate the operation of several geo-distributed facilities. Another reason to use multiple sites is the hybrid public-private cloud infrastructure model. Under the right circumstances, this can be quite cost-effective. You can handle average demand for your service from your private infrastructure and then offload peak demand to the public cloud. For all of these reasons, inter-data center connectivity is becoming very important, and providers can move a lot of data between these data centers. Here we'll look at some data from a study from 5 Yahoo data centers from 2011. The study is based on anonymized traces from border routers that connect to these data centers. The details of how the study was carried out are not particularly relevant to our discussion here. We'll focus on this one result. What you're looking at here are 2 plots showing the number of flows between clients and the data centers, and on the right, between the data centers themselves. The 3 lines on each plot are for 3 different data center locations. Notice that the y-axis on these 2 plots are different. In terms of number of flows, the traffic between data centers is 10 to 20% of the traffic from data centers to clients. Now keep in mind that flows between data centers could be very long-lived and carry more bytes than those between clients and data centers. So flow counts don't necessarily give us a good idea of traffic volumes. More likely, this number, 10 to 20%, underestimates the volume of traffic between data centers. Also, the methodology of this study classifies everything that's not Yahoo to Yahoo traffic as Yahoo to client traffic, while in some cases you might have third parties partnering with Yahoo, such as ad networks, in which case you'll count that also as data center to data center traffic. Google's assessment of the volume of this traffic is unambiguous though. Google has noted that it now carries more traffic between its data centers than on its public-facing wide area network. And the traffic between its data centers is growing at a higher rate as well. Now that we've talked about these networks carrying large amounts of data and being very useful, let's talk about what makes them different from the data center networks we've been talking about so far. The goal of these networks is to provide persistent connectivity between a small set of endpoints. In Google's case, that was just 12 different data center sites. Also, these networks are typically dedicated and provide hundreds of gigabits per second of capacity across these sites. If you look at comparisons between networking over the internet in general, for example, end hosts to a service or across arbitrary end hosts on the internet, private data centers, and wide area networks such as these, you'll also find that there's a difference in terms of the flexibility you get in network design. Over the internet, network design is constrained by the coordination required among several parties to make any change. In private data centers, on the other hand, you have complete freedom to implement your own routing, your own topology, your own congestion control protocols, and such. Where does a WAN sit in this design flexibility spectrum? That depends on how much of the WAN you own privately. If you own or lease your own fiber lines, you have the same flexibility as a private data center, perhaps even more because the number of endpoints involved is smaller. So you have creative freedom with design without some of the limitations of the scale that big data center networking brings. On the other hand, if you're dependent on a transit ISP, your freedom in terms of routing or traffic engineering might be somewhat more limited. But usually these facilities will be multi-home, so you'll have multiple transit ISPs, you'll still be able to manipulate routes and do some form of traffic engineering. Also worth noting is that WAN bandwidth is a very expensive resource. Microsoft has noted that the amortized cost for them is hundreds of millions of dollars on these inter-data center networks. In this lesson, we'll focus on traffic engineering in the WAN context, particularly with regards to bandwidth. Latency we'll come to later when we talk about content distribution networks. The traditional approach to traffic engineering in such networks is to use MPLS, which is multi-protocol label switching. So let's see how this works. You have this network here with several different sites spread over the wide area, connected to each other, perhaps over long-distance fiber links. You use a link state protocol, such as OSPF or ISIS, to flood information about the network's topology to all nodes. So at the end of such a protocol, every node has a map of the network. For traffic engineering, what you'd like to do is also spread information about the bandwidth usage on these different links in the network. Given that there's already traffic flowing in this network, some links will have spare capacity and some won't. Both ISIS and OSPF have extensions that allow the flooding of available bandwidth information together with their protocol messages. Knowing the state of the network, when a router receives a new flow setup request, it'll set up a tunnel along the shortest path on which enough capacity is available. It sends protocol messages to routers on the path, setting up this tunnel. Further, MPLS also supports the notion of priorities, whereby if a higher priority flow comes in with a request for a path, lower priority flows might be displaced. These flows might then use higher latency or higher cost paths through the network. After a flow is assigned a tunnel, the routers also update the network state. With the routing state in place, let's see how data packets flow through this network. When a data packet comes into the ingress router, the router looks at the packet's header and decides what label, that is what tunnel, this packet belongs to. Then it encapsulates this packet with that tunnel's label and sends it along the tunnel. The egress router then decapsulates the packet, looks at the packet header again, and sends it to the destination. In this scheme, only the ingress and egress routers read the packet header. Every other router on the path just looks at the assigned label, making forwarding along the path very simple. This is the reason the protocol is called label switched, multi-protocol label switched. Also, MPLS can run over several different protocols as long as the ingress and egress routers understand that protocol and can map that protocol onto labels. You can use that protocol, which is why the name multi-protocol label switching. This approach has two big problems, the first of which is inefficiency in terms of usage of the WAN's expensive bandwidth. Typically, these networks will be provisioned for the peak traffic. As this image shows here, if you have a traffic characteristic over time, the y-axis is the utilization, you'll provision the network for peak traffic. Now, the mean usage of the network might be very small. In this example, it's 2.17 times smaller than the peak. So you're wasting that amount of bandwidth for most of the time. Now, if all this traffic was latency sensitive, you really cannot do much better. You have to provision for the peak because those packets need to get to the destination. However, the observation made in this Microsoft research paper is that most of this traffic is actually background traffic, with some latency sensitive traffic as well. So you can provision for the peak of the latency sensitive traffic and then fill the gaps with the background traffic which is not latency sensitive. So unless you differentiate traffic by service, you cannot do such an optimization. This is not easy to do with the MPLS approach because it does not have a global view of what services are running in the network, what parts of the network they're using, and such. Also, a related point is that regardless of whether there are multiple services or not, MPLS, the routers make local, greedy choices about scheduling flows. So traffic engineering is suboptimal. For these reasons, such networks typically run around 30% utilization to have enough headroom for these inefficiencies, and this is expensive. Another big problem with the MPLS approach is it only provides link-level fairness. So at any link, the flows can share capacity fairly. But this does not mean network-wide fairness. For example, here we have the green flow sharing capacity across that link with a red flow. The blue flow also shares capacity with the red flow. But the blue and green flows both get capacity half the red flow because the red flow uses multiple paths. So we have link-level fairness, but we do not have network-wide fairness. This is something that's hard to achieve unless you have a global view of the network. In the next lesson, we'll talk about how cutting-edge methods from Google and Microsoft address these shortcomings.
Okay, so what Ankit told you about last time was how the traditional approach to traffic engineering in the WAN is rather inflexible in how you arrange and optimize flows across the network. Because you have this, you really need an understanding that goes across the whole network and bring that knowledge together and do some sort of centralized optimization. And in a way that lets you talk about what individual services need.
Great.
What we're going to see in the next few minutes is solutions to this problem from Google and from Microsoft. And both of these, the B4 system and the SWAN system, have a few common themes. First, we've got kind of a challenging problem here that if we want to get very high utilization in the WAN, because there are natural fluctuations over time. So we're going to leverage diversity in the services. Some services need a certain amount of bandwidth at a certain moment of time, and they're inflexible. And some other services you can use to kind of fill in whatever room is left over.
For example, you might have latency-sensitive queries. If I make a Google search and some data center does not have the information to fulfill that query, it might make a backend query to some other facility. And that's a latency-sensitive query.
On
While
the other hand, yes, you may have backup traffic that you want to do on the time scale of hours to days.
Right.
Another theme is that we're going to use a software-defined networking approach where we gather information about the state of the network, make a centralized decision about the flow of traffic, and then push those decisions down to lower layers to actually implement it. But bringing all that information together in one place, you've got to make a relatively complex decision. And you do that traditionally with an optimization technique like linear programming, which is a way to take a set of constraints on required amounts of data flow over parts of a network and come up with an optimal solution. And of course, you can use linear programming for many other optimization applications across computer science and operations research and beyond. But if you just take that big generic hammer and apply it to this situation where we need to make relatively quick decisions, it turns out that it's rather slow.
Right. And part of the complexity comes from the multitude of services with different priorities. If you had just one service, you could run a network flow algorithm and that would be much faster. But that's not the case here.
So we'll have to do something to get us something faster, even if it's perhaps not guaranteed to be exactly optimal. Fourth, we're going to have a dynamic reallocation over bandwidth, of bandwidth. So as the demands on the network change over time, we're going to have to make continual decisions about what traffic is highest priority to move across which links at a given moment. Okay, so that's part of the challenge with linear programming, that we have to make quick decisions.
So these are online algorithms, but they're not online in the same way as things inside the data center might be. For example, Google runs its traffic engineering 500 or so times a day. So it's not as fine-grained as things you might need inside the data center. Traffic between these facilities is relatively stable, it seems.
And finally, a commonality in the architecture here is that we're going to have to implement an enforcement of the flow rates somehow when the traffic enters the network. And we'll do that at the edge rather than at every hop along the path.
Correct.
All right, so let's see a little bit more inside Google's B4.
For one, it was the first highly visible SDN success. That makes it interesting in of itself. Very exciting time for the community. So what we'll do here is look at what happens at one site, one data center. What does it do in this framework? So inside this one site, you have the data center network, and you have cluster border routers. If you recall this image from our topology lesson, you have some switches that are dedicated to external connectivity. In the traditional setting, how you would network these would be you would connect these using eBGP to WAN routers, which would then also interface using iBGP, ISIS to the other data center sites. But now, you don't want to do this all in hardware at the WAN routers. You want finer control over routing. So what you want is to move this to software. So you'll use a software router, which is the Quagga software switch. You'll run it on a server. And that will interface with OpenFlow, which will set up routing rules on those routers. So Quagga runs the routing protocols between the cluster border routers and also the other sites. And then OpenFlow uses the routing information from Quagga and sets up forwarding rules in the WAN routers. The flip side of this is the WAN routers themselves can be very, very simple hardware devices. And we have control over what the forwarding rules are. So far in this picture, we have modified nothing with regards to logic. You can run BGP's default routing algorithms, and nothing has changed. What's the point of all this? The point is now you have software control, and you can interject a TE, a traffic engineering server, which manages what rules exactly are installed. This traffic engineering server interfaces with all the different data center sites, collects the topology information, the available bandwidth information, as well as the information about flow demands between different sites. The traffic engineering server then pushes out the flow allocations to the different data centers. At the data centers, the multiple controllers then enforce those flow allocations on the senders.
So Ankit, I have a question. When you say the TE server pushes out instructions for the flows to the controllers within each data center,
Right.
What instructions about a flow is it pushing out? What does a flow mean? Is that every single TCP connection between servers or something else?
Fair question. If that was the case, this would not be a very scalable solution. You cannot do this at a flow level across these large numbers of data centers. What they do instead is make flow groups out of multiple flows and assign rates for those. And then at the individual sites, those flow groups, the rates for the flow groups are partitioned across the flows that constitute a group. And this is done based on the priority each service has, the bandwidth that it gets assigned. Now that we've looked at an overview of the architecture, let's look at some of the design choices that make this work. For one, the fail-safe choice. As a fallback option, they also keep available the BGP forwarding state. Because each of their switches allows them to have multiple forwarding tables in place at the same time, they can afford to have BGP forwarding tables also in addition to the traffic engineering provided ones as a backup. Now, if the traffic engineering scheme does not work, they can discard those routing tables and use the BGP forwarding state instead. So the BGP routing tables serve as a big red switch.
So if you look at this big red switch feature of the design, it's pretty interesting. Google went to a great deal of effort in many aspects of the design. There's many layers of getting reliability in this rather non-trivial distributed system. And one of them is just switching completely from a very new kind of traffic routing to a much more traditional, tried and true and hardened approach of traditional BGP routing. So that big red switch was a way of getting a greater degree of confidence that you could actually run this system, and if some unexpected problem came up in the new design, just switch back to the old one.
We should note that this fallback was in the context of a very early stage architecture, when it made sense to not rely on this new combination of several different pieces. Among these new pieces was custom hardware. So Google made their own custom, cheap, and simple switches to operate this network. Part of the rationale for this was the timeline. In 2011, there were not many software-defined networking-enabled switches on the market. So Google built their own using cheap commodity equipment. This should be a callback to our earlier lesson on topology, where we looked at closed networks. Here, what you're looking at is a two-stage closed topology with a spine and several leaf switches. With this approach, they built 128-port 10 gigabit switches in 2011. There are several interesting things about this hardware architecture. For one, they're foregoing the expensive proprietary equipment that WAN operators traditionally use. With that goes away big forwarding tables and deep buffers. So they have to use edge-based rate limiting because they no longer have deep buffers. Also, given the number of locations in this architecture is small, 12 data centers are being connected, they don't necessarily need the big forwarding tables. So they can make do with small forwarding tables. Also, keeping the switches simple makes them highly available. On these switches also runs an embedded chip running Linux, which is what interfaces with the OpenFlow controller. Most of these smarts then reside in the software. The switches are simple, and the software, which is the OpenFlow control logic, at each site replicated for fault tolerance using Paxos. Further, for scalability of the system, they use a hierarchy of controllers. The software solution achieves nearly 100% utilization and solves the traffic engineering problem in 0.3 seconds. This is achievable only because of the several tricks they use for scaling the system up. For one, they use a hierarchy of controllers. This is what this looks like. So at the top level, you have the global controller, which is talking to an SDN gateway. The gateway can be thought of as a supercontroller that talks to the controllers at all these different data center sites. Each site might itself have multiple controllers because of the scale of these networks. This hierarchy of controllers simplifies things from the global perspective. Other scaling tricks in use are the aggregation of both flows and links. As we discussed earlier, traffic engineering at this global scale is not at the level of individual flows, but of flow groups. That also helps scaling. Further, each pair of sites is not connected by just one link. These are massive capacity links that are formed from a trunk of several parallel high-capacity links. All of these are aggregated and exposed to the traffic engineering layer as one logical link. It is up to the individual sites to then partition traffic, multiplex and demultiplex traffic across this set of links.
Now, Microsoft has also publicly disclosed a design for optimizing wide area traffic flow in their WAN. And although there are differences in goals and design in many aspects, there are also similarities, some of which we mentioned, and different features. One particular interesting feature we'd like to mention in this design is a way to make changes to the traffic flow without causing congestion. So if you look at this example here, let's say we're in a network on the left, and we have these two flows, the blue one and the green one, and that are each using, in this simple example, 100% of the bandwidth of the links that they flow across. If we want to move from the scenario on the left to the scenario on the right, if you do that in any naive way, because you can't control exactly when every packet will flow across every link, there's going to be some period of time where, due to timing uncertainty, you have both of the flows sharing to some extent one of the links. And you can think of different ways to do this, but you're always going to run into some link that may get used by both flows at the same time. So if you take a look at this design for SWAN, there's an approach to making those updates with a certain amount of spare capacity so that you can avoid congestion. So that's an interesting approach that takes the optimization one step further, so that you're providing a pretty strong guarantee on lack of congestion even while the network data flow is changing. So Ankit, why do you think this kind of optimization hasn't been done for WANs before?
Good question. Partly because ISPs have been doing WAN engineering for a while, but they have not had access to the same tools. SDN is a rather new paradigm, and it does enable some of what these guys are doing. So I think that's a very big, important new driver that has changed the game. People are starting to think of centralized control as something that's practically doable.
And also, it's possible now with a large cloud provider like Google or Microsoft, because you have control over the infrastructure. You have a big driver, an economic driver of economy of scale to make any optimization you can. And you have visibility into those applications, so you can do the kind of optimization trade-offs between higher priority and lower priority flows.
So that about the service is a very good point. ISPs have only minor visibility into traffic, while Google, for example, can look at different TCP flows and tell which one is latency sensitive, because they are running those applications. So that gives them flexibility to do manipulations with that traffic in any way they please. As we've discussed earlier, the cloud computing model depends not only on big data centers, but also internet connectivity between these data centers and between the end users and the data centers. In this lesson, we'll focus on one aspect of the latter, making cloud services more reliable and faster for end users using content distribution networks, that is CDNs. Let's say you're running a cloud service out of just one data center. This may be good enough for a small population of users located nearby, but what if clients all over the globe were to access this service? This approach provides no opportunity for load balancing and tolerating failures at this site. Further, the faraway clients experience very high latencies. If a single network round-trip time is 300 milliseconds, a rich service making several of these round trips will provide a very poor user experience. And users care about low latencies. Google, for example, has noted that an additional delay of 400 milliseconds on their search page load time translates to fewer searches by users. So 0.4 seconds translates to 0.74% fewer searches. Now that number might seem small, but for a company the scale of Google, that is a sizable chunk of revenue. Also, this reflects that users consciously or subconsciously care about small latencies. Besides the latency aspect, providing service from one site also means moving huge volumes of data across the globe, particularly for applications like streaming movies. This can create huge demand for long-haul bandwidth, which is expensive. But doesn't caching solve these problems? Let's review how caching works. A client makes a service request. The response may be cached at a cache middle box that the ISP deploys. If another client requests the same data, and it's present in the cache, this client can simply get the data from the cache. There are several reasons this approach does not go far enough. First, the volume and diversity of content, which, together with the long-tail distribution of popular content, makes caching extremely difficult to benefit from beyond a certain point. But even more crucially, significant amounts of content today are dynamic, either changing over time, like the news, or personalized based on user interests. The increasing trend of encryption also reduces the utility of caches. Data encrypted with session keys specific to users cannot be cached. CDNs address these problems, and as a result are on track to be carrying a majority of the internet's traffic soon. Cisco, for example, estimates that 62% of all traffic over the internet will cross CDNs by 2019, up from 39% in 2014. So in this lesson, we'll examine how this important piece of internet infrastructure works. How do CDNs work? I'll first provide a brief overview of the pieces that comprise the solution and then delve into the details. First, the content servers are spread across several locations. These servers actually run a service, which means they can serve dynamic data over encrypted connections, unlike a cache, which is limited to serving static content. Second, the content or service needs to be replicated at these locations. The data needs to be kept fresh, and the service provider may want to gather analytics. Further, client interactions may require getting data from other CDN nodes or from the origin server, as is often the case. All of this requires high-capacity networking between the various CDN nodes and the origin. Now, one may simply use standard internet transit through an ISP or private connectivity over fiber that one leases or owns. Some of what we discussed in our WAN connectivity lesson applies here, but in this lesson, the detail I'll provide will be more focused on latency. Lastly, once the service is replicated, how do clients learn where to get the data from? Some mechanism is needed to direct clients to an appropriate server or CDN site, based on metrics like latency to improve client performance, or perhaps load at different CDN locations to improve load balancing across the CDN infrastructure. It's worth mentioning that while large providers like Google might operate their own CDN infrastructure, most web services will depend on a CDN provider, like Akamai, Limelight, or Level 3. Let's look at each of the three aspects we listed here in more depth. So where does one put the content servers? The placement decision is not necessarily about geographic distance, but about network distance, which is partly why co-location facilities and internet exchange points are great choices. An internet exchange point, or an IXP, is essentially a data center where ISPs connect with each other. This, for example, is the London Internet Exchange. It's one of the largest IXPs in the world. It's much like the Heathrow Airport of the internet, moving around 2 terabytes per second on average. Such facilities hold lots of network equipment like this. These are switch racks inside the world's largest IXP by traffic volume, located in Germany. Housing your servers inside such a facility if you can afford it and server space is available, or in a data center hosted by an ISP connected directly to such a facility, provides good connectivity to every part of the globe. But why would an ISP host CDN infrastructure for a web provider or for a CDN provider? Well, for the ISP, this provides two benefits. One, they do not have to carry that much long-haul traffic anymore because a lot of content will be served from the CDN nodes inside the ISP's own infrastructure. Second, it also improves the quality of service for the ISP's own users. Although, at times I have great difficulty believing that this is a concern for ISPs. Here, you're looking at one such CDN location. I pulled these images from a Nanog talk by Dave Temkin at Netflix. Nanog is a network operators group which often gives a cool peek into network operations. Netflix equipment is connected to tens of large facilities, including both the London and Frankfurt ones we just looked at. And the numbers will only increase as the service expands. These servers replicate Netflix content and stream video to end users. Netflix uses custom-built boxes optimized to deliver video to clients at small power and space footprints. That said, different applications have different priorities. For Netflix, tens of locations that deliver video streams are fine because latency is not the biggest determinant of performance. A small startup delay in video streaming is typically deemed acceptable because of buffering. For a latency-sensitive web application, however, you might need a much larger set of locations to be able to reach clients at lower latencies. In fact, Akamai claims to run 170,000 plus servers in over 100 countries inside more than 1,300 networks around the world. As we noted earlier, CDNs move around a lot of data and need to do it at low latency and high reliability. How does one network these locations to each other? We've already discussed briefly the physical interconnection aspects, but what I want to focus on here is the interesting opportunities for networking this setting provides at the routing and transport layers. At both layers, I'll discuss one technique that's in use in such networks today. Let's start with routing. Unlike routing inside data centers, internet routing is driven by lots of independent players motivated by economics. This can lead to routes which are suboptimal in terms of performance. An ISP might pick a next hop based not on which path has lower latency, but on which path is cheaper. Or sometimes, internet routing can suffer from configuration errors and faults and anomalies which might take a while to be corrected. Here you're seeing a real trace route from Taipei to Putian in China. The IPs are obscured here so you don't hammer the same addresses with your probes. The end-to-end latency here is 290 milliseconds round trip, while the shortest distance round trip on Earth's surface between these locations is around 500 kilometers, which would be just 2.5 milliseconds at the speed of light in fiber. Sure, fiber isn't laid along the shortest path between these two locations, but that does not explain the 100 times larger latency. Examining this trace revealed that this path runs through San Jose in the US. That's 21,000 kilometers. Now this instance is particularly extreme and probably a transient anomaly, but internet routes can be suboptimal quite often. Situations of the type on this slide present themselves frequently. Here, the latencies are such that the direct route's latency from A to B, that is LAB, is larger than the sum of latencies over an indirect path through X, that is LAX plus LXB. This is called a triangle inequality violation. If the internet were doing shortest path routing, we would not see such situations, at least at times when the routes aren't transient. The name triangle inequality violation comes from the property of a triangle, where the sum of the lengths of any two sides must exceed the length of the third side. So how do we obtain more control over routing to avoid such scenarios and obtain better performance? The answer is overlay routing. If we have networked equipment inside these networks, we can simply have packets at A destined for B go to X, and for X to forward them onwards. At its simplest, these could just be servers moving packets via tunneling, as shown here. So packets from A travel to X, X decapsulates the packets and forwards them on via standard routing to B. Thus, even if the AXB path is not available over the internet's BGP routing, nothing stops us from doing this at a higher layer. A 1999 study evaluated how much such routing could potentially improve latency. This is based on traceroute measurements between end hosts. The measurements were collected over default routes on the internet and then compared against the best alternate routes that could be stitched together passing through other end hosts in a manner similar to what I just described earlier. Now this measurement dates back to 1999 and is somewhat biased towards university-based clients as well as public traceroute servers, which may not quite be representative of end hosts on the internet. I wish there was newer and more extensive data available, but we'll have to make do. For 30 to 35% of the host pairs in this measurement, routes with latency lower than the default path exist. In a significant fraction of these cases, improvements of more than 20 milliseconds are possible. The paper also includes similar analysis for loss rates. While these measurements are old, this technique is used today in Akamai's network. Let's review how one would make this work. One could send active probes, that is measurement packets, between these locations and collect measurements, or just passively monitor the data traffic that is already moving between these devices. And this will help us keep track of performance metrics across these locations. Let's say this map shows the collected pairwise measurements. So the latency between San Francisco in the US and this location in Europe is 160 milliseconds as we measure it over the path on the internet. For scalability, if the network is large, one may not collect all pairwise measurements, but rather organize things into some hierarchy. One may also use passive measurement data to avoid overloading the system with too many measurement probes. With these pairwise measurements in hand, one can run a link state protocol on top of this overlay if one wishes to let individual sites make decisions, or collect this information centrally and push out the overlay routes to the CDN nodes. One point of note here is that there might be other considerations than latency or loss, such as the cost of bandwidth along different paths. Next, let's look at an improvement in the transport layer. In this example, we have an end user who needs to get some data from the CDN, but that data access requires connecting to the origin servers. Now, doing the entire transaction with the origin server can be quite expensive if the latency between the end user and the origin is large. For example, this path might have 400 milliseconds of latency. So you're doing the TCP handshake, sending the SYN, getting the SYN ACK, and that takes 400 milliseconds. After the connection is established, you'll enter TCP slow start. You'll send your request, and the server will send you some packets. After you send the acknowledgements, the server will send you more packets, and so on. As you can see, all of these round trips here are quite long, 400 milliseconds each. This is quite inefficient and expensive. Another way of doing this is for the CDN nodes to maintain persistent connections over TCP to each other. In this scenario, the client still does the handshake, but only with the nearby CDN node, from where the CDN servers take over, use the persistent connection to simply send the request and get the response. So the client tries a TCP handshake with the nearby CDN node, sends its request to the node. That node uses the persistent TCP connection to make this request to the origin server or other CDN nodes, gets the response. Because it does not need the TCP slow start, the TCP connection is persistent and the window size is already large, and then forwards that data to the client, perhaps over slow start. But keep in mind that the round trips here are all smaller, except for the one transaction between the CDN node and the origin server. Everything else is taking place between the CDN node and the end client. The latency on that connection is much smaller than the 400 milliseconds we saw. So this way of doing it incurs much lower latency. This is an even bigger advantage for connections that are encrypted with SSL, because that requires additional round trips to set up the encryption. Lastly, let's discuss how clients learn where to get the content from. Here is a map of latencies to Wikimedia's 3 CDN locations in Amsterdam, Ashburn, and San Francisco. So 2 of them are in the US and 1 in Europe. Each bubble is a client measurement of latency. A bubble is colored yellow if the Amsterdam location is the one that has lowest latency for that client. It's colored green if it's the Ashburn location that has the lowest latency, and blue if it's San Francisco. Bubbles corresponding to clients with the lowest latency from any location exceeding 150 milliseconds have a red outline. So for those clients, all 3 locations exceed 150 milliseconds. Clearly, with all 3 locations of the CDN quite far north of the equator, clients in South America, Australia, Southeast Asia, and South Africa suffer in terms of latency. In terms of decisions about where to send clients, what this map says is, with just 3 locations, if you're optimizing only for latency, you want all the yellow-colored locations to go to Amsterdam, all the green-colored locations to go to Ashburn, and all the blue-colored locations to go to San Francisco. But keep in mind that there might be other concerns like load balancing and cost of bandwidth. Regardless of the parameters used to make the decision, we are only discussing the policy aspect here. What we haven't gotten to is how these policy decisions would be enforced. What is the mechanism that CDNs use to direct different clients to different locations? Let's talk about that. This starts with the HTML page itself. The client requests the landing page HTML from the origin web server. For a simple web server, the resources will usually be served from the same domain. In this example, bigpicture.jpg comes from abc.com. But for web services using CDNs, instead of abc.com, the picture may be served from cdnurl.abc.com. So the URLs need to be rewritten in the HTML itself by the web server. And this does not have to be a dynamic process. This is the HTML page that the web server serves to every client. The rest is taken care of by manipulating DNS. Next, the client's browser will attempt to resolve cdn.abc.com. The client's browser's DNS request goes to the ISP's DNS resolver, which further queries the top-level domain resolver. The top-level resolver's response is another domain name. This is called a CNAME, that is a canonical name or an alias. The local DNS resolver then reaches the CDN resolver to resolve this name. Now, the CDN resolver can respond with an IP address for a CDN server close to the local DNS server which made the query. This decision may be based on IP geolocation for that resolver. It's also possible that the CDN resolver itself issues a CNAME response, which corresponds to a regional resolver for the CDN closer to the client. But the broad idea here is that the DNS resolution is specific to the client's location. Of course, the resolver may consider other factors like load balancing across locations in its name resolution. If the CDN site located closest to the client is suffering from high load, the CDN may choose to direct it to the next closest site, perhaps. Finally, at the CDN's cluster, a load balancer can send the client's data request to the appropriate server. The name resolution from the CDN's resolver to an IP address has a very short time to live in the DNS cache. This ensures that different clients get different responses and not the same cache response over a long period of time. Now a question arises. What if the client isn't using their ISP's local resolver? What if they're using some service like OpenDNS or other public DNS servers? That will mean that the client could be contacting a DNS server that's not close to them, which will throw off the CDN's estimate of where the request is coming from. This can have an adverse impact on the performance. We'll now discuss a completely different mechanism based on manipulating internet routing instead of domain name resolution. Just like the Stack Overflow query, you may also have wondered how some IP addresses, like Google's 8.8.8.8, can be reached at low latencies from places that are far from each other. For instance, the latency for this address may be 10 milliseconds over pings from both Sydney, Australia, as well as New York. Feel free to try this and discuss in the course forums. If this were one physical server, this would not be possible. Sydney and New York are separated by at least 160 milliseconds, even if a fiber line ran directly between them along the shortest possible path. The way this works is by using anycast routing. The key idea of anycast routing is to have different clients go to different physical servers which use the same address. How is this accomplished? By announcing the same IP prefix in BGP from different locations. If the same BGP prefix is announced from different locations across the internet, different ISPs will end up with different choices for next hops to that prefix. What this ensures is that clients at those ISPs will use that particular announcement to reach a server, and these servers are now globally scattered. Now this avoids the problem that the DNS-based approach runs into, that is guessing the client's location, because the guessing is no longer necessary. That BGP prioritizes shorter paths means that different clients will choose CDN locations closer to themselves. This approach does have its own drawbacks though. For one, it's difficult to dynamically pick different locations based on the load observed at different sites or the performance differences if something has changed, because BGP announcements will take a while to propagate, and granular fine control using BGP announcements is rather more difficult than with DNS. Another disadvantage is that route flaps, that is BGP dynamics, can cause different packets for the same connection to go to different places. That wraps up our overview of how CDN infrastructure works. This is an important piece of infrastructure and will soon come to move most of the internet's traffic.
Okay, Ankit, so I learned a couple things from that. We've got content distribution networks, CDNs, that are actually carrying a significant fraction of the internet's traffic. And what they give the cloud is kind of a way to reach out to the world, to be close to the world.
Right.
Physically close to end users, so you get low latency. Because
Absolutely.
Otherwise you're fundamentally limited by the speed of light and performance irregularities and performance problems of the wide area internet if you're only located in those big hyperscale clouds.
True. But also, CDNs do reduce physical distance and thus latency and sidestep some of the wide area networking issues. But they also lower latency by using transport layer techniques and routing techniques based on performance that they observe. And this is true for not just applications that have content that is cacheable close to the edge, but also works for content that needs to be fetched, for example, from other CDN nodes or from the origin or the content publisher.
Right. And that's interesting, actually, because a lot of those optimizations are possible in the CDN context because you have this large-scale infrastructure, global infrastructure, that's managed and owned and architected by one entity. So if you want to implement your new overlay routing protocol or your new version of TCP that maintains persistent connections then you can go ahead and do that. It's actually kind of similar to in data centers, we've seen new protocols and optimizations within the data center where there's also one operator.
Absolutely. It does come down to flexibility. And in fact, one of the interesting things about all this is here decisions are being made in response to measurements that are being collected. So you're monitoring performance and making decisions based on that, for example, with the overlay routing, right? This is not something that's available in the internet's protocols. BGP might use things like path length, but that's not necessarily representative of latency performance.
Right. AS level, autonomous system level path length in the internet's global routing protocol.
Absolutely.
Is not a great predictor of latency down to the millisecond. Right. So, along those lines, something that's interesting to think about is what happens if you take this CDN and now you give it not only the ownership of the wide area endpoints, the servers that are running the CDN, but also the network backbone, the core backbone connecting them.
Right.
Kind of similar to some of the hyperscale cloud providers have that infrastructure themselves connecting their data centers. Now, if you had that in a CDN environment, maybe there are further optimizations you could do in the wide area.
Absolutely. I think it's very interesting. The flexibility really opens up a whole set of possibilities. If you own the infrastructure, there's so much more you can do.
We'll see you next time.
With the consolidation of compute and storage in massive data center facilities, we also need to talk about how to provide connectivity over the internet to these facilities. In this lesson, we'll discuss end-user connectivity to these facilities over the internet. This topic sits at the edge of our course's material, so we'll only scratch the surface here, focusing more on the problem than on the solutions. But it's important enough to deserve an entire course on its own. Different internet applications place different requirements on the network. Applications like file sharing and video streaming are not particularly latency sensitive, but benefit from high bandwidth. For web browsing, the benefits of increasing bandwidth diminish after hitting a few megabits per second, depending on the particular web page in question. And latency quickly becomes the bottleneck. For several other applications, like multiplayer gaming, remote surgery, remote virtual reality, online music collaboration, all of these depend on extremely low latency, but also high bandwidth. We often hear about the majority of internet traffic being video, and how that dominance is only growing. Cisco estimates that 80% of all consumer internet traffic will be video in 2019. Now, given that video streaming can tolerate several seconds of delay, is it all about the bandwidth then? 80% of traffic, that's most of it. Does it all just come down to providing high bandwidth connectivity? Not quite. For one, 80% of traffic is not the same as 80% of value. Value across different applications is really hard to quantify, but there are certainly a lot of high-value internet businesses whose value does not stem from video streaming. And a lot of these depend heavily on low latency. How much do these depend on low latency? One experiment for putting value on latency comes from Google. The experiment entailed adding artificial delays on the server side to Google web search results for a certain set of select clients. And these were compared against a control group in terms of the volume of searches they made on the Google search engine. The results from that experiment are shown here in this plot. On the x-axis is time week by week from the start of the experiment. On the y-axis is the reduction in searches for this test group compared to the control group of users for whom no delay was added. The two trend lines here in red and black are different delay values added to the search results for these users. So 200 milliseconds for some users and 400 milliseconds for some other users. With 400 milliseconds of delay being added, by week 6, users see a drop of about 0.74% in their search volume. This directly translates to revenue for Google, and for a company Google size, this is a significant chunk of value. More importantly, it also illustrates how user experience depends crucially on low latencies. So just 400 milliseconds translated to a drop in user search traffic. To drive home further the value of latency and to draw its contrast from bandwidth, let's do a somewhat extreme but fun exercise. The distance from New York to San Francisco is roughly 4,000 kilometers one way. At a carrier pigeon's breakneck speed, well, for the pigeon's sake, let's say it's not breakneck. At a carrier pigeon speed of 80 kilometers per hour, it would take 50 hours to cover this distance. Let's strap today's highest capacity USB thumb drive, 1 terabyte, to our pigeon. Now this translates to a bandwidth of 44 megabits per second. That's pretty good. That's actually better than the average US consumer bandwidth. In fact, several times better than that. But the round-trip latency is about 100 hours. So clearly this is not acceptable for most internet applications. So bandwidth is great, but we also need low latency. It's worth pausing here to consider for a moment that just about a century back, pigeons were among the fastest means of communication. So we have come a long way since. So bandwidth does matter, but even for applications like Ultra HD video, we'll only need something like 15 megabits per second. Also, ISPs are competing heavily on bandwidth. Latency, in the meanwhile, also matters for many applications and is quickly on the way to being the bottleneck for these, including web browsing. And latency is typically a harder problem to solve. This has been noted in a variety of contexts. The key is that for bandwidth, let's say you have technology A and you're getting bandwidth X. You can just replicate technology A, draw a parallel infrastructure with technology A itself, and you'll get 2x bandwidth. The same is not true for latency. You need some new techniques to get lower latency. Latency is also fundamentally bounded by the speed of light. New York to Delhi round trip is going to take at least 80 milliseconds no matter how good we make our networking technology. Now, one way of getting around this problem is to use content distribution networks. Content distribution networks work by moving content closer to users, thereby sidestepping some of the issue with distance. Now, this helps in many scenarios, and another lesson in this course discusses the solution in detail. But not every service is hosted by a CDN. And for things like multiplayer gaming, where users may be separated geographically, a CDN will not help very much. So we need the network itself to provide low latency. And this is quite complementary to CDNs actually. CDNs themselves will also benefit from a low latency internet. So let's look at a toy experiment to see what latencies on internet today look like. I use the Linux wget command to fetch this popular website, just the index.html of the landing page. So it's a very small amount of data, 20 kilobytes being fetched here. This took 430 milliseconds. I obscured the URL so you all don't hammer their servers. Next, I pinged the server hosting this website, which took 55 milliseconds. I also geolocated the server to Portland in the US, which is less than 6,000 kilometers from my location in Champaign. This would merely be 19 milliseconds at the speed of light in vacuum, c. So in this case, the internet is 23 times slower than it could be. And clearly, for 20 kilobytes, we are not bandwidth constrained. It's worth noting that the speed of light in fiber is actually closer to 2/3 of c than c. This is just a physical media property of glass. But that's not fundamental. In fact, today there are networks that are operating, that are niche networks in certain markets, that do work at c, nearly c. So we really should be using that c baseline as a comparison for how well today's internet is doing. Now let's broaden this experiment a little bit. Here, I'll show you results from nearly 3 million fetches of popular web pages from clients distributed across the globe. In each case, we are getting only the HTML of the landing page. So again, just tens of kilobytes of data, usually. On the x-axis of this plot is latency inflation compared with the speed of light latency to each web server's location. So that's the 23x number in the previous example. So that's what's on the x-axis. On the y-axis is the CDF across the page fetches. So across these nearly 3 million page fetches, the median inflation in latency comes to about 35 times. That is, the internet is about 35 times slower than a hypothetical speed of light internet. Note the logarithmic x-axis here. In a significant fraction of the cases, the inflation is over 100 times. Now this is a large slowdown. Where does this latency come from? Let me tell you a bit more about the experimental setup we use to gather these measurements so we can find out where this latency comes from. I used 186 clients, which are located at universities across the globe, as part of a global test bed called Planet Lab. From each client, I fetched, using the Linux curl command, thousands of web pages. And again, we are only fetching the index.html for the landing page. From curl, I also gathered data about the time to resolve the DNS, the time to establish the TCP connection, and the time for TCP to transfer the data for the web page. Let's look at how latency breaks down across these different components. We'll focus here on the median numbers, although the tails are also interesting. In the median, DNS took 7.4 times longer than the C latency. Note that for some fraction of pages, around 10%, DNS was faster than C latency. This is simply because the DNS server may be located closer than the actual web server, and we are using the latter as the baseline. The TCP handshake, considering only the time between the sending of the SYN from the client and receiving the SYN ACK back at the client, is 3.4 times inflated in the median. This can also be thought of as an estimate for the round-trip time from the client to the server. The time between sending the ACK together with the client's GET request to receiving the first byte from the server is labeled here as the request response time and is 6.6 times inflated in the median. This time includes the server's processing time as well. Now, using the TCP handshake as an estimate of the RTT, this means that the server's processing time is quite similar to the RTT. That's about a tenth of the total fetch time in the median. For these fetches, the server's processing time is thus a small fraction of the total page time. Lastly, TCP using its multiple round trips moves the data to the client, being 10.2x inflated in the median. Note that the medians of these latency numbers will not add up. That is to be expected. Because all of these are tail-heavy distributions, we cannot expect that the medians will add up. The median total time will be larger than the sum of the medians of these individual components. Given the value of the problem, a lot of ways are being explored to reduce latency on the internet, both at academia and in the industry. One such project is Google's Quick, which aims to get rid of the TCP handshake overhead as well as the TLS setup overhead, among other things. Now, how do we get rid of the TCP handshake overhead? To do so, we first need to understand why we use the handshake at all, what's its purpose, and then perhaps we can achieve the same function in some other way. The handshake helps prevent denial of service attacks of a certain kind. Before the handshake is complete, the server does not expend many resources on the client's request. It requires the client to receive its SYN ACK and to respond with an ACK before it will process the GET request. So the TCP handshake prevents attacks based on address spoofing. So if a malicious client spoofs an IP address and sends a server a request, the server will not spend resources on that request before requiring this client to acknowledge its ACK, its SYN ACK in the TCP protocol. So the client has to be able to receive the server's message and send a reply back together with the GET request. This ensures that spoofing the address will not be successful. So now, how do we get rid of the handshake without breaking this useful property? Quick's way of getting rid of the TCP handshake involves use of what is called a TCP cookie. Here, the first time a client connects to a server, the interaction is as with the TCP protocol. You require a handshake. But in this interaction, the server also gives the client a cryptographic certificate certifying that the client does in fact correspond to this address. In future connections to the server, the client can present this cookie and the server will process its request. So it can just send this cookie together with its GET request, and the server will process that request and send back data. Quick is a work in progress, but Google's already testing it live on users. In fact, chances are if you're using the Chrome browser, you have already used Quick. There is, of course, lots of other work on improving protocols for lower latency on the internet. But let's look back at that breakdown of latency in the internet across these different protocol factors. So again, let me remind you that the numbers in the medians here will not add up. It is tempting to conclude from this breakdown that the TCP transfer time and DNS resolution are the biggest problems. But it's important to remember that latency at the lowest layers affects all of these protocols. So here we are talking about the network's round trip itself. What would the effect be if all the bare metal latencies on the internet were speed of light? To get one estimate, we can transform all these numbers by dividing them by 3.4x, which is the inflation in the handshake here, that is 3.4 times. Doing so gives us these numbers, which are significantly smaller. In fact, the reduction in the total time is smaller than the reduction we would have achieved if we had made any of the other protocol factors optimal. So for example, if TCP transfer time was 1x, we would not reduce the total time by as much as in this scenario. So really, we have to be careful when assigning blame for high latency on the internet. It's both protocols as well as the physical infrastructure and routing. Now, why are bare metal latencies on the internet this large? Well, for one, the internet is not using shortest path routing. The internet routing protocols depend on policy between independent players. These are economic considerations. It's not just shortest path routing. Further, even if the internet was using shortest path routing, the shortest path between even pairs of routers is not along the shortest path on the Earth's surface. The fiber does not run necessarily along the shortest possible path because of geographic constraints, lakes, oceans, rights of way, and so on. An additional factor is that the speed of light in fiber is 2/3 the speed of light in vacuum. All of these factors mean that the bare metal latencies are significantly larger than what we would see on a hypothetical speed of light internet. One caveat about these measurements: I collected these measurements from nodes that are located at universities across the globe, and these are usually better connected than end user locations. This means that these measurements are not necessarily representative of the typical end user performance. One way you can help us correct this is by running the measurement tools that are packaged with the programming assignment setup that we have given you. The data you collect will be shared with the class, and it will be an interesting latency atlas of the internet for all of us to see. The summary here is that both the internet's protocols and its physical infrastructure are responsible for high latencies on the internet today. Latencies of high value, and progress is being made on all fronts to tackle these problems. Some of the work on this subject is linked on the course webpage.
Well, Ankit, it seems like the real driving force here is that when we consolidate, as we are to get economy of scale in big data centers in the cloud, when we consolidate, then this basically leads directly to a wide area networking performance challenge.
Absolutely.
Right? So
yeah.
we think of the cloud as just the big warehouse data center sometimes, but actually it's putting a lot of demands on the wide area network, so that becomes a key part of the whole picture as well.
Right.
So that means bandwidth, which is improving, but also latency, which is a harder thing.
And there's something fundamental about latency, right? There's a fundamental bottleneck, physics. Between New Delhi and New York, even in the very best case, the latency is going to be at least around 80 milliseconds round trip. There's no getting around that. Now, CDNs help with that, yes. So, well, there is some getting around that. CDNs help, but they don't help in all cases, right? If you're playing multiplayer online games, a CDN won't help performance very much.
So I guess we've seen several proposals that are being pushed forward now to try to deal with that latency problem. So there's Speedy from Google at the HTTP level, and also Quick upcoming at the transport layer.
Right.
To try to improve performance, especially latency.
It's interesting because one of the things that's moving things forward is Google's ownership of both ends to a significant extent, right? They have the most popular browser, which is Chrome, and they have control over some of the most popular services. So this means they can implement application layer techniques and things at transport layer quite easily. They're actively testing these things out on users now, right? As we saw, Quick is, you've probably tested Quick if you're using their browser.
Right.
So that control really, again, we see the amount of control someone has on the ends or the network really changes the game in terms of what you can do with technology.
So check out on the course website our measurement tools that we're providing. And if you're willing, then run them to help build a latency picture of the internet. This is going to help further research on the topic of internet latency, but it's also going to give us an interesting view of the internet and latency to cloud services that we'll all learn a lot from, I think.
And we'll share that view with you. Very exciting stuff.
OK, can't wait.
Throughout the course, we have discussed a number of ways to improve network performance. Networks are complex systems, and the industry and the research community are continually working to push networks farther. Nevertheless, when problems arise, applications must learn to cope with the network's variable performance. In this lesson, we'll discuss some ways in which applications can do that, particularly deal with network performance variations. In a seminal paper dating back to 1981, Salzer, Reed, and Clark made the end-to-end argument. Their point is best illustrated with an example. Consider an application whose task is to provide reliable end-to-end transfer of data between 2 points separated by a network. Now, there are many sources of error possible. For example, the network's links or the routing devices may drop or corrupt the data packets. Or perhaps the end host systems could introduce errors. One can try and eliminate all possible sources of error by careful engineering, but this would be impossible and could still leave out errors that were previously unknown. As a result, the responsibility for making sure the data is correctly transferred ultimately lies with the application itself. The application itself could check whether the data is correctly transferred, for example, by a checksum. This is quite easy to do, and if the checksum fails, the application can do a retry over the network. Of course, this is not to say that the network should be designed to be lousy. The more reliable the network is, the less likely it is that the end-to-end check by the application fails and that a retry is required at all. But ultimately, the responsibility for making sure the data is correctly delivered lies with the application. To quote Salzer, Reed, and Clark, the end-to-end check of the file transfer application must still be implemented, no matter how reliable the communication system becomes. They also describe in this paper an instructive incident to drive this point home. An MIT networked system used hop-by-hop checksums to ensure correct delivery of data across a network. It turned out that within one network gateway, the task of copying data from the input buffers to the output buffers was not performed correctly in some instances. As a result, the end-to-end data delivery was corrupted, even though there were checks at every hop. In this case, the ultimate end-to-end check was required, manual comparison and correction of the data that was transferred over this connection, which was, needless to say, quite tedious. The lesson here is that ultimately, applications have to deal with network conditions to suit their objectives. Now, certain network functions are desired by a large class of applications, so we build them into lower layers. For example, TCP takes care of reliable in-order packet delivery. This is something a lot of applications require, so we build it into TCP. In this case, applications are delegating trust to TCP, and TCP is handling reliable in-order packet delivery. But for more niche application objectives, beyond what standard protocols can be engineered to provide, applications need to step in. What we'll discuss in this lesson is a sampling of techniques applications use to achieve their objectives. We'll talk about how applications can deal with latency in the tail, how TCP in-cache can be handled, although with some compromises, at the application layer, and how video streaming deals with variations in network capacity. We've talked about tail latencies earlier in the course. Pieces of candy. Now, if I were to pick a piece from this box randomly, I'm highly likely to end up with candy. No teeth broken. Some data center applications exhibit traffic patterns which require lots of parallel requests, thus running into problems with such latency variation. For example, with Bing, a search query might be farmed out to several thousand servers. Or with Facebook, a popular page might require 500 or more object fetches from Memcache. If you're making such large numbers of requests, and the result depends on waiting for the last response, performance can be quite poor due to the variability in network latencies. Many different factors can contribute to the variation in latency that causes such problems: the shared environment in the cloud, different load on the servers, errors, network congestion, and loss. Given that it's hard to control all of these, perhaps applications should deal with this variation with their own mechanisms. One way of dealing with this problem is to settle for incomplete responses, so you don't wait for all the responses to arrive before sending out the search query response to the user, for example. Now this might mean a compromise in response quality. So if you're not waiting for all the servers to respond with their part of the answer, you might skip some search responses, as an example again. Of course, this is a rather last resort method of mitigating the problem. Another way of dealing with latency variations is implemented in the Cassandra data store. For read operations, Cassandra implements what is called rapid read protection. To quote, "Rapid read protection allows the coordinator to monitor the outstanding requests and send redundant requests to other replicas when the original is slower than expected." Let's look into what this means and how this works. In Cassandra, the client may request a read from a coordinator, which looks at load at different replicas that can fulfill the request, and then pick the least loaded one. Now, if this replica is slow to respond for some reason, the read latency suffers. The rapid read protection mechanism simply has the coordinator monitor the outstanding requests, and if the requests take too long, issue redundant requests. A similar approach has also been used in Google's Big Table. The rough idea is the same as what I described in Cassandra. In addition, the Big Table mechanism has a request cancellation feature, where after the arrival of the first response, if you have issued a redundant query, the other query can be cancelled. This mitigates the cost of the additional work that has to be done to answer queries. You can find the details in Google's Jeff Dean's talk, which we have linked to on the course page. But Dean showed results from requesting 1,000 keys spread across 100 tables in Big Table. The latency is measured as the time until the arrival of the last response. Issuing backup requests to a replica substantially reduced tail latency in these numbers. The backup after 10 milliseconds scheme requests a key that did not arrive within 10 milliseconds from a replica. As soon as the key arrives, if a redundant request is outstanding, it is cancelled. This gives a latency reduction, in this case, from almost a second in the 99.9th percentile, that's the no backups result there. This gives a reduction from that almost 1 second latency to 50 milliseconds. And because of the cancellation mechanism, this incurs only a 5% extra key request load. So in this case, a very simple application layer mechanism achieves a vast improvement with very little cost. Note that if the requests you are making manipulate system state in any way, you might need to do more work with the backup requests. For example, if you're flipping a bit in the database, issuing redundant requests can have unintended consequences. But even in the simpler case, why does this technique work, and what are its costs in general? Let's look at an example. Here, the server response time is 10 milliseconds for 99% of the requests, but 1% of the requests require 1 second to complete. So the probability of the request being slow is 0.01. Now say we are making a redundant request with every request, regardless of how long it takes. What's the likelihood that both requests are slow? If we assume that request latencies are not correlated, that is, each request independently has a probability 0.01 of being slow, then we simply get a product of these probabilities. That is a 1 in 10,000 chance of the request being slow. This is the general intuition for why this technique works. Now replicating every request can be costly if you're making a large number of requests. So let's look at that case. Now let's say our job consists of 100 requests, all issued at once, and we consider the job done when all responses arrive. What is the likelihood that it takes 1 second to finish this job? Now the job will be slow if at least one request out of the 100 takes 1 second. What's the likelihood of that? You can compute the probability quite easily to be 0.63. Obviously, this is horrible. Almost 2/3 of the cases, your job does not finish in 10 milliseconds. It takes a second. But let's investigate this a bit more. What's the probability that 2 or more requests out of these 100 are slow? That's 0.26. We can keep doing this to see a quickly shrinking probability. The point of this is that even though the job is slow, it's actually a very small fraction of requests that are causing it to be slow. If we could make this small fraction of requests to be fast, the job itself would be faster as well. What if we were replicating any requests that were outstanding after 10 milliseconds? In this example, there's only a 0.003% chance, that's on the last row there, that we'd replicate 5 or more requests in this scenario. So that's the number of requests that's outstanding after 10 milliseconds. Further, the chance that all of these up to 5 requests are answered in 10 milliseconds is quite high, roughly 95%. So this method leaves only around a 5% chance that our job does not finish in 20 milliseconds. Now we can keep doing this further. We can look at what the probability is for the job to be not finished in 30 milliseconds, 40 milliseconds, and so on. And the numbers shrink quite rapidly. This is a massive improvement over the job taking 1 second to finish. This is the general idea behind this approach. You can replicate a rather small fraction of requests and speed up the job substantially. A key point here is that requests are assumed independent. This is not necessarily the case. For example, if you sent the replicated request to the same server, and the server is what's slowing down things, if the server is suffering from high load, and that's what's causing requests on that server to be slow, you cannot expect the redundant request to be any faster. However, this could still help if it was actually the network that dropped the request due to some transient congestion, and it was not actually the server's fault. In that case, sending the request even to the same server will work. But in general, if requests share server or network bottlenecks, then independence is not a well-founded assumption. This may be the case particularly for systems running at high load. But if you're querying a different replica in a system that's not congested, independence is a reasonable assumption to make. Nevertheless, this example gives us the intuition behind this method. What about the costs? First, there is the client-side cost of making redundant requests. This will typically be quite small. The bottleneck will usually not be at the clients. Second, the redundant requests generate additional network traffic. Third, the servers have to handle the increased workload. So when is this technique a win overall? If your system is running at high load, redundant requests can increase the average latency. However, in data centers, the network and services often run at low utilization, and this technique can be quite useful in such environments. Further, if one is using the request cancellation mechanism for outstanding requests after one response arrives, the overhead can be quite low, as we just saw. Thus, the costs are often quite small and worth incurring. Next, let's talk about TCP incast. We've discussed incast in our lesson on congestion control, but briefly, incast is a situation where a large number of senders send data to a network port, which overwhelms the buffer, leading to high packet loss and latency. Further, if some TCP flows lose many packets, they can time out, and TCP throughput can collapse. In our congestion control lesson, we saw how DC-TCP helps address this problem. But what can one achieve at the application layer? One way of reducing the likelihood of incast scenarios is to limit the size of responses that each worker is allowed to send. So you send out a search query, for example, to 1,000 servers. If all of their responses are small, perhaps you can fit them in the switch buffer. Of course, this is a rather severe limitation on the application and is not really a general purpose solution. Another way is to accept that some of the several responses requested may be dropped in the occasional incast scenario, and restructure the application to deliver partial results. Again, this is a rather undesirable non-solution. A more workable approach is to deliberately space out the application's requests and responses. The application can add small delays between successive requests, and thus the responses themselves can be expected to be somewhat spaced out in their arrival times on the switch buffer, thereby making incast less likely. This technique has been used in some systems. Of course, the downside is that adding these deliberate delays slows down the average response time. So you're sacrificing the average to improve the tail cases. The DC-TCP paper itself notes the use of this technique in production data centers. This plot shows the impact of disabling this technique. referred to as request jittering in the paper. Each line on the plot is a different latency percentile. The lowest, in blue, under 10 milliseconds, is the median latency, and the largest, on top, is the 99.9th percentile latency. After request jittering is turned off, the 99.9th percentile doubles, while the lower percentiles decrease. This illustrates the compromise this approach presents, sacrificing some performance in the common cases for a decrease in the likelihood of incast scenarios. Facebook has also reported the use of a technique that's similar in a sense in its memcached deployment. Their mechanism involves controlling the number of outstanding requests that a memcached client sends using a sliding window in a manner similar to how TCP controls the flow of packets for a single connection. So a client maintains a window of outstanding requests for which this client is awaiting memcached responses. When some responses arrive, the window advances and grows in size. But when some responses time out, the window shrinks. This is essentially another layer of flow control on top of TCPs. The rate limiting works across different connections, unlike TCPs. So TCP rate limiting works within the connection across different packets. Here, rate limiting is being applied across different memcached requests. When the window is too small, requests wait too long to be scheduled on the client itself. When it's too large, there's a risk of incast because you're sending out a large volume of requests and all the responses might come in simultaneously. The paper includes measurements of the impact of window size. In this plot, the window size is on the x-axis and the time requests wait at a client before being scheduled is on the y-axis. This data was gathered from multiple racks in one front-end cluster in Facebook's network. When the window is too small, requests wait too long to be scheduled, and when it's too large, it causes incast and slower processing of requests, leading to a buildup of requests at the client. There's a sweet spot in the middle that minimizes wait time. That closes our discussion of application layer mitigation of incast. But it's also worth noting that this paper highlights another interesting choice to extract higher performance. That's the use of UDP for GET requests where occasional failures are acceptable. Now UDP does not provide reliable delivery like TCP, so this does mean a small failure rate, in this case 0.25%. But the upside is lower latency because you don't need connection establishment or slow start, unlike TCP. Also, being connectionless, UDP does not require the server to maintain any state. This means that per connection, the server requires fewer resources, leading to higher system scalability. For things that change the data state, they still use TCP for reliability. The last application layer technique we'll discuss is rate adaptation in video streaming. The goal here is to provide the best video streaming experience in the face of variable network bandwidth. Obviously, we'd like the highest possible video resolution, so you'd prefer the picture on the right to the picture on the left. But at the same time, you'd like to avoid waiting for buffering. Buffering does help a lot. It can mask variations in the network's performance. In fact, even interactive applications like Skype use buffering on the order of 100 milliseconds or so. For streaming video applications, several seconds of buffering is seen as acceptable because these aren't interactive. You can fill up the buffer in the beginning, start playing smoothly, and then the buffer covers up variations in the network's bandwidth. So as the available bandwidth reduces, the buffer drains a little bit, and as the bandwidth increases, the buffer fills up again, and hopefully you don't see the buffer empty, and the stream plays smoothly. But if the buffer does empty out, you have a pause in the playback, and that hampers the video experience. The common approach to solving this problem is as follows. Video is encoded in multiple bit rates, for example, from low resolution standard definition, or SD, through various rates up to 1024 HD, or higher. The video player at the client estimates the network connection's available bandwidth. It then picks a video rate that's slightly less than the available bandwidth. So the rate of incoming data over the network exceeds the rate of the data playing out from the buffer onto the client's screen. That's simple enough, right? Let's look closer at how this is supposed to play out. You're looking at the video buffer at the client device here. We'll see how the video bitrate is supposed to vary with the network's capacity. One can think of the buffer as a set of 1-second chunks. The 1-second chunks at high bit rates, like HD, are obviously a larger number of bytes and use more room in the buffer, and are thus shown as taller here. The chunk at the head of the buffer is playing out to the screen, and a new chunk is downloading into the buffer. The plot above the buffer is shown as a track of the network's bandwidth. Bandwidth is measured over download of chunks. If a chunk is 2 megabits, and it took 1 second to download, the bandwidth is measured as 2 megabits per second. This measured bandwidth may be used as an estimate of the future network capacity. If the estimated capacity is less than the video bitrate, we need to request the next chunk at lower quality or bitrate. An easy way to think about this is if you're taking more than 1 second to download the chunk that plays for 1 second, then you need to view the video at lower quality if you want to prevent rebuffering. And of course, if the capacity estimate is higher than the video rate, we may be able to jump to a higher quality video chunk. This technique is called adaptive bitrate streaming. One cool thing to notice is that all the logic for the bitrate adaptation resides on the client side, so the CDN server side can actually be quite simple. This works reasonably well, and at least until recently, some variant of this was Netflix's default approach. But there is room for improvement. The problem is that capacity estimation is hard to get right. If your estimate is too conservative, you're unnecessarily viewing the stream at lower quality, which is undesirable. If your estimate is too aggressive, you request higher quality chunks, and the buffer drains out because of the time it takes to get those chunks, and this causes the video to pause. This pause is called a rebuffer. We'll refer to this term rebuffer or rebuffering often in the following discussion. The difficulty of estimating network capacity is reflected in this plot. It shows for one Netflix video player trace the average throughput over chunk downloads, that's on the y-axis, over time on the x-axis. Notice how the average throughput varies in a wide range. 10% of sessions in a random sample of 300,000 Netflix sessions show high variability in network capacity. This variability means that the capacity estimation is often off the mark. 20 to 30% of all rebuffers seen in this dataset were found to be avoidable. That is, switching to a lower quality video stream would have avoided the need to pause. Of course, if the network's capacity is lower than the lowest video bitrate, then there is no avoiding rebuffering. You will see frequent rebuffering in that case. This paper from Stanford and Netflix researchers also proposes a method of improving upon the capacity estimation based approach. The key idea of this work is this. It's the buffer's occupancy that we care most about. Can we make decisions based on the buffer occupancy alone? The answer is, for the most part. If the buffer is nearly full, we can use a larger bitrate, that is higher video quality. If the buffer is nearly empty, we need to be using a lower bitrate, that is lower video quality if we want to avoid rebuffering. This intuition can be captured formally as a function that maps buffer occupancy to the next video chunk's bitrate. If the buffer occupancy is high, we can use the highest video quality. If it's low, we must request lowest video quality for the next chunk. This ensures that as long as the network's capacity exceeds the lowest video bitrate, the video stream will not suffer from a rebuffer. Between these extremes, the chunk rate is a non-decreasing function of buffer occupancy. It's not necessarily linear though, that's just the example here. We'll omit details of the function explored in this paper, but nevertheless, one problem remains. What about the startup phase? When the stream has just started, the buffer occupancy gives us very little information. How do we make decisions then? A simple form of capacity estimation is indeed useful in this startup phase. Note that reality is a bit more complex than what we discussed here. For example, video encoding rates aren't continuous but rather discrete, so you might have just a few options between the lowest bitrate and the highest HD bitrate. So you need to figure out how to discretize the rate function. The paper does address these issues in case you're interested. How well does this approach work? The paper includes real-world results from a massive experiment. The data was gathered over 500,000 users of Netflix browser-based player over a weekend in September 2013. Each group in their A/B tests played roughly 120,000 hours of video. Let's look at the two primary quantities of interest, the number of rebuffers and the video quality. The x-axis of this plot is time in GMT. The yellow bands represent peak Netflix hours in the US. The y-axis is the number of rebuffers normalized to the number of rebuffers in the control algorithm. So the control algorithm is what this work is comparing against, and that's Netflix capacity estimation-based approach in deployment at the time of these experiments. The lower bound curve shows the best possible result for rebuffers. That is, if the video were played at the lowest quality throughout, what would the number of rebuffers be? From the lower bound result, we can gather that there's roughly 20 to 30% room for improvement in the best case. The buffer adaptation algorithm, marked BBA, achieves performance quite similar to the lower bound, especially in the peak hours. It achieves 10 to 20% fewer rebuffers than the control algorithm. Further, the buffer-based algorithm, unlike the lower bound in this scenario, does not compromise on video quality. This is what the other result we'll discuss shows. Here, the y-axis is the video rate difference between the default control algorithm and BBA. BBA achieves higher video rate throughout. Lastly, it's useful to remind ourselves that this algorithm is deployed in the browser-based player on top of standard protocols. In such applications where there's enough value, there's a strong argument for the application to take on some of the tasks that the general purpose network isn't necessarily adept at.
Hi, today we are happy to be sitting down with Bruce Maggs. Bruce is the Pelham Wilder Chair of Computer Science at Duke University, and he's also Vice President for Research at Akamai.
Thanks, guys.
So what kind of content is Akamai serving? Who's using Akamai?
Well, there's a very diverse set of customers who use Akamai. There are tens of thousands of different websites that use Akamai to assist in delivering their content. There are a few major categories. So one category you've probably all heard about is video. So the largest source of bytes delivered is video. So movies would be a good example of that. We have some customers that use Akamai to deliver movies. There's also live video events where there's action that's being captured in real time and immediately sent out over the internet, and occasionally those events can be very, very large. Another big category of bytes served is software downloads. And software downloads are sometimes served when a user is explicitly clicking on a button on a web page to download something, but oftentimes they're taking place in the background, and it's just some kind of software update program that goes and makes requests to Akamai to fetch the latest version without the user necessarily being involved. And these two categories of traffic are what we would call latency insensitive categories, where there may be bulk data, but there's some tolerance for a little delay at the beginning, whether it's a delay in a few seconds of buffering before the movie starts, or maybe if a software download's going on in the background, the user is not going to know whether it started 1 second earlier or later. There's an entirely different category, which is the latency sensitive traffic, and maybe the most important example here is e-commerce websites where the content provider is offering a product offering a service, selling something online, and they want to have snappy performance. And there have been a number of studies that show that even small reductions in latency and the time it takes to get a response when you interact with a website can greatly improve the experience for end users and measurably increase, say, sales. So that's one of the reasons why we fought so hard to get our servers deployed as close to the end users as possible. Although I will say that another reason for having this very widespread deployment is that for certain categories of traffic like video or software downloads where you have to serve a lot of bytes, you also need to find a lot of bandwidth on the internet, and that's another reason for a broad deployment. I'm going to just give you one more category, although I could probably go on and on, but increasingly websites who are subject to periodic attacks of various sorts use the CDN as a front end to provide the scale to thwart denial of service attacks and to implement various kinds of sanity checks on user inputs to shield the content provider's back-end servers from malicious traffic. And examples in this category would be things like banks and government websites.
Mm-hmm. Exactly.
So you mentioned these two categories in particular, and the third for denial of service. But with regards to streaming movies and software downloads being one category and latency-sensitive traffic like serving websites being another category, how do the needs of these two kinds of applications differ? What do they want from Akamai? Do you do different things for them? What changes?
Well, I think if you look at the primary needs in the case of the latency sensitive traffic, it's important that the user gets a response as quickly as possible. And that means if we can, we want to cache a copy of whatever object the end users are going to require as close to the end user as possible.
So you care about seconds, hundreds of milliseconds, tens of milliseconds, milliseconds, individual milliseconds?
Probably not individual milliseconds, but certainly hundreds of milliseconds and maybe tens of milliseconds. You know, you want to see, it's sort of on that scale. You want to shave 100 milliseconds off the page, or maybe off each object on the page. That kind of scale. The video traffic is a little different. There, you really want to provide once you've sort of determined the capacity of the channel between the end user and the internet, you just want to make sure you can sustain steady delivery of video at whatever was the suitable encoding bit rate for that video.
Mm-hmm.
Now, one thing I hadn't mentioned was that there are also tricks that can be used to reduce latency, even in the case where the object to be served isn't cacheable. And I know that sounds contradictory or perhaps hard to see how a CDN could do that, but if you'd like, I could also talk a little bit about overlay networks.
Absolutely, yes. So there are multiple techniques, I presume, that go into making things work for objects that are not cacheable. We can discuss all of them, as many of them as you can tell us about. Overlay routing, or perhaps connection proxying for TCP, anything.
Yeah, so those two are they're very closely related, and I don't know if the class knows a lot about the details of the TCP protocol, so I'm going to review something very quickly, and that is that when a client wants to make a connection to a server, say a web browser connecting to a web server, the client initiates a request to open up a TCP connection between the client and the server. And at the beginning, there's something called the TCP three-way handshake, where the client sends a packet we call a SYN packet. The server sends a SYN-ACK, and then the client sends back an ACK. And at that point, both parties can start sending data, but also TCP has built into it sort of a period of time where the two try to figure out how fast can they send data without actually causing congestion. And it takes a little while for them to ramp up their speed to that sort of ideal rate.
Right.
And all of this adds latency. And so one question is there any way to speed up the initial part of a TCP connection? One thing you can do is move the server closer to the browser. And the reason that helps is that the reason this initial phase in TCP is slow is that there are many round trips going back and forth. And if you reduce the latency, those round trips happen more quickly. So one technique that Akamai employs and provides as a service for many content providers is that we act as their front end. So even for content that's not cacheable, the end user's browser will contact a hopefully nearby Akamai server, will launch a new TCP connection with that server over a low latency interaction. Meanwhile, the Akamai server will have already opened up and maintained for some time a persistent TCP connection back to the content provider, which might be a much greater distance and much higher latency, but the initial TCP phase has already been completed, and so the end user doesn't see any penalty for that. So that's I guess what Ankit called TCP proxying, where we have the ability to sort of serve as a benevolent man in the middle, who helps terminate the TCP connection more quickly, and then passes everything through.
So each Akamai user-facing server will then have a persistent connection to all of the content providers, or those are sort of cached in some way?
No, well, not all content providers use this technique, but and it may be that unless there have been connections from other users through that server to a content provider before, it may not have set up the connection yet. And furthermore, within any one data center, Akamai kind of partitions which servers are acting on behalf of which content providers. So it wouldn't really be an all-to-all where every Akamai server is connected to every content provider. That wouldn't be efficient.
So each server will, at a particular site, one server will kind of specialize in a certain subset of the content, and another server might specialize in another subset, and probably needs to be overlapping in some way.
That's possible, but I think a better way to think of it is, let's say we have a cluster with 64 servers somewhere. Okay, so we use a technique called consistent hashing to map the different content providers' content onto the different servers. So any one server may be serving content for potentially hundreds or thousands of different content providers.
Right.
But if you look at any one content provider, within a cluster, they might be 1 or 2 or 4, depending on how popular that content provider's content is, 1 or 2 or 4 servers that are helping serve the content for that content provider. Now, it is also possible that we might take a content provider's content, different parts of the page, and split it across different servers. But actually, we typically, unless there's a really good reason to do that, probably want an individual content provider to be served out of one server, the whole page, or have several servers that are each capable of serving the whole page and all the objects, rather than splitting it across servers.
Yeah, makes sense.
Now, Ankit, you asked about TCP proxying. You also mentioned something called overlay.
Right.
And what I've described, TCP proxying, is you can kind of view that as an overlay network, in the sense that instead of having the browser connect directly to the content provider and using whatever path is selected by the the internet routing protocols, we've introduced an intermediate point, which is the CDN's front-end server that's now proxying the TCP connection. So that's a kind of simple example of an overlay. There's another example that Akamai uses between our server, our cache, which I've called the front-end server, and the content provider's backend. So I said that we maintain a persistent TCP connection back to the content provider. In many cases, that's true. But we also may try to find a better connection than the one that is the default path provided by the internet routing protocols. We will also look for one-hop paths that go through another Akamai server located somewhere else, which is then, let's say, proxying the TCP connection. It's actually proxying an HTTP connection from our server back to the content provider. And we'll explore both the direct path as well as several one-hop intermediate paths and look for the best one. Best meaning lowest latency or lowest packet loss or best bandwidth, depending on the application.
Right. And by one hop, you mean one hop on the overlay. So the path to this intermediary might be several network hops, but this is one hop in the overlay sense.
Yeah, that's right. It could be actually 10 router hops.
Right.
But when I say one hop is you go through one additional Akamai server. You could imagine having overlay paths that go through more, but as far as I know, we don't do that.
But then the object that the user wants would be downloaded from the original content server to maybe an intermediate Akamai server. That's over one HTTP connection. And then that intermediate server streams the same object over another HTTP connection back to the first Akamai server that was originally hit by the web client. Is that right?
Yeah, so there's sort of a series of connections. And as I mentioned earlier, for the direct connection from the Akamai server back to the content provider, we'll have set up a persistent TCP connection, actually a persistent HTTP connection. We'll also do that between lots of pairs of Akamai servers so that if you decide you want to pull something over an overlay connection, TCP is already set up and ready to go, and you can just start pulling the data.
Mm-hmm. So Bruce, is there any advantage to doing this at lower layers? For example, the way I understood this is the intermediate node in this overlay will terminate the front end's HTTP connection and start another HTTP connection, right? So this is at the application layer. So is there any advantage you see in the future, for example, for doing software routing? So you do the overlay at the routing layer and you're routing in software.
Well, I think there might be additional performance gains that you could achieve if you had even finer grained control of the network. But as a company, Akamai has tried to stay out of managing layers below the transport layer, so that we don't operate our own backbone. You may have heard that companies like Google or Microsoft, in addition to the many other things they do, they run their own network backbones. We don't do that. So Akamai does have routers here and there, but they're mostly used just so that we can peer with other networks and make connections to other networks with servers that are sitting right next to the router. So our use of lower level technology is it's very limited, and we almost never, if not possibly never, are actually doing routing. And so we've just avoided that because it's it would require a whole new branch of expertise that we would need. And so far, I don't think our service has suffered from not doing it that way.
But you're doing overlay routing, and that overlay routing, it also, it gives you more direct control that you can, control downloads directly informed by measurements.
That's right. In some sense, we are still designing our own routing algorithms, and we're using our own policies, and we're incorporating things that traditional internet routing algorithms don't incorporate when we make decisions. For example, we do continuous performance measurements and make decisions about what overlay paths to use or which end users to serve out of which servers based on those performance metrics. But we're doing that all at the application layer. None of that is happening down at the network layer or below.
Right. So with thousands or tens of thousands of potential intermediate points, even if you're just doing one hop overlay routing, that's a big infrastructure. There's a lot of possible paths to explore, a lot of measurements that you could be taking about the network performance as it changes over time.
Well, we don't really do all of them. I think, for example, we have servers all over the world. And if, let's say we have an Akamai server in Frankfurt, Germany, and we have a content provider in Paris, France. And we want to know, is there any path that's better than the direct path provided by the internet? Well, we are not going to explore a one-hop overlay path where the intermediate hop is in the United States. We just know that in advance that doesn't make any sense. You wouldn't want to route the traffic across an ocean and back. We're not going to look at hops in India or hops in Japan. So there's a great culling and sort of some sanity checks that go on when you prepare your list of potential candidates that might be used for the overlay. And furthermore, we collect history over time. So we've seen in the past which intermediate hops have succeeded in providing better performance. And so probably the number of eligible hops might be on the order of a few dozen, not thousands like you could conceive of if every single server location that we maintain could be a candidate.
So then when the request comes in, because you have this history, do you already know when the request comes in, you generally already know what the best path is going to be, or are there additional probes that happen at that time?
That's a good question. So on the one hand, I think that after you've done this for a while, you should hesitate to ever say, I already know what the best anything is, okay? Because you never really know. And the internet changes very rapidly, and you just hope that you make a good decision as often as possible. But having said that, one of the things we're trying to do is reduce latency. So the idea of waiting until you get the request and then doing a bunch of measurements, that won't work. And furthermore, because the conditions can change pretty quickly on the internet, the routing paths can change, or even more quickly, the congestion may come or go. You have to do kind of fairly continuous measurements on a periodic scale on the order of minutes or less, so that you can look back and say, hey, I just did a measurement and this path seemed good, but this one seemed poor. And so that's what we're doing for the overlay network. For example, between various pairs of Akamai servers, or maybe say server locations, there's a continuous sort of sending packets back and forth, seeing what happens, so that you have some way of gauging whether the performance is good between that pair and whether that's a link you might want to use as part of an overlay routing path.
How big are the differences in performance if you pick, sort of the default internet path that's what most of us are doing, versus a path that you've had some amount of control over because of the overlay routing?
Well, there's no simple answer to that. In some cases, it's the difference between the packets not getting through at all and the packets getting through. And that's the case where you really want to be sure you pick the right one. Other times it might be a difference of, shaving off a little latency or getting a little more bandwidth, and it's not as pronounced. But really what you want to avoid is cases where you can't even provide the service using the default path.
And that would be because of some routing anomaly or a spike in congestion, or
yeah, those would be two good examples.
All right.
So between Akamai servers is one thing, right? There's a small number of, in comparison to the internet at large, there's a relatively small number of endpoints that you're considering for the overlay. What about when you're talking about routes to IP prefixes? Do you also do the same sort of exercise there? And if so, how do you scale that?
Yeah, that's a good question. So it's much more difficult problem. What you're asking about is, how do we figure out, when we get a request for an end user for content, which of our servers we should send the request to? And again, depending on what type of content is, our goal may be, well, we've just got to have the lowest latency performance, or we know we need to provide steady throughput for a video. What's more complicated here, as you said, is there are many more locations of users around the world than our roughly 2,500 locations of servers. And another complication is that we only control one end, the server side. We don't control the client side. So we have to do something different. We can't just do continuous probing between every client and a set of candidate Akamai servers. We don't do that. Instead, what we do is we try to build out a map of the internet that captures both its topology, but also its performance in real time. And at a very high level, it works something like this. We collect every day all of the requests that are made for service to Akamai. And in particular, we collect the DNS resolution requests that are sent to us. So for example, we might have a customer, we'll just call them xyz.com. And I've just made that up. So if there is a real xyz.com, it's a coincidence. And they've decided they're going to use Akamai to deliver some of their content. And they created a domain called ak.xyz.com. And whenever they have a URL that uses that domain name, ak.xyz.com, that's a URL where the request is going to come to Akamai, and we'll look at the rest of the URL, and we'll hand over an object. Well, what happens is when the browser goes to that web page, either goes to a URL that starts with ak.xyz.com or downloads a page that has some embedded objects whose URLs start with that domain. We'll receive a request from whatever resolving name server or local name server the browser's using. It'll come into Akamai and it'll say, hey, can you resolve this name, ak.xyz.com? Mm-hmm. That's where we have to make a decision about where we want to serve this user. Now, we may not know precisely which client is making the request. We'll see the network address, the IP address of the local resolving name server. More and more, we may see something called the EDNS0 extension, which the local name server may provide to us, which is the /24 prefix that the user's in. And based on that, we want to decide where to serve the user. Sometimes it's really easy. It could be a no-brainer. So, for example, if Akamai had servers at the University of Illinois, and you guys in your office go to a website that's using Akamai services, and you're using a campus name server, we're going to get that request and say, oh, we're already on the campus. We'll serve them from the servers there, okay? And that's what we like best. We like it to be an easy decision. And maybe half the traffic is served from those sort of no-brainer decisions where we've got a partnership with some organization. And it's sort of, unless there's a catastrophe, we always do the same thing because it's always the right choice. But we can't do that everywhere. So we also have a lot of servers in large commercial co-location centers where we're just one of many tenants, and we potentially could serve users from a lot of different places out of that co-location center. And the question is, given all the users and all of these co-location centers, which ones should we serve from where? So I'm giving you a little background. Now I'm going to try to say how we do it. So we collect the DNS requests that we receive over the course of a day, and we sort them. We actually we sort them and we extract, roughly speaking, the top 300,000 name servers that sent us requests in the previous day, the ones that sent the most requests. And this will be like 99 or maybe even more, 99.5% of the requests. I don't remember the exact numbers, but this is the idea, that we get a few 100,000 name servers that are responsible for sending us most of the requests. Then what we do is, for each of those name servers, we use a utility, maybe the class has heard of, called traceroute, to map out the path from maybe a few dozen Akamai servers to that name server. And we look at these paths from all these different Akamai server locations, and we find out, where do they intersect? You know, where's the common point, so that all servers, any one of our servers, if we tried to send traffic to that name server, would have to go through this point. And we call that a core point. We identify a few tens of thousands of core points around the internet, and we associate with each core point the name servers that are behind it, you know, on the other side of the core point from the Akamai servers. Mm-hmm. And then throughout the day, each core point gets pinged, perhaps from a few dozen or more Akamai server locations, to see what's our path like right now from these server locations to that core point. And we assume that any requests that we get from the name server should be optimized according to the best path to the core point that name server is behind. And here I'm assuming that, you know, the name server is a good proxy for the end users. That when we get a request from a name server, if we optimize what we think would be best for the name server, that it's also best for the end users.
So you're using the name query performance optimization to decide how to ultimately deliver the web objects then?
Yeah, I think that's fair to say. We in the earliest days, before the EDNS0 extension, where the name server can now actually tell us something about the client, we used to only have the name server's IP address. And so the only thing we could do is, you know, just hope that the name server was a good representative. The path to the name server was a good representative path for the path to the actual clients that were using the name server.
So is EDNS widely deployed now? I mean, it seems nice. It gives you more. You don't have to use this proxy. It's an overloaded term here in this conversation, but proxy for the actual client, the name server. That's what you had to use. But now you can see the actual client prefix, IP prefix, if the EDNS error is there. So is it widely deployed now?
I think it's widely deployed in the sense that there are certain very heavily used name services, like Google's name service, that does deploy it, and we do accept the EDNS0 prefix from Google, and we act on it. In terms of percentage of local name servers that are sending us EDNS0, it's still pretty small, but it's growing, and it's something that we're encouraging, because it's better for Akamai to know who the actual clients are, so that we can make a decision that's really based on the client rather than the client's name server. And this is especially important for clients that are using name servers that are not near to them in the network.
Mm-hmm. Right, like OpenDNS and Google DNS possibly.
Right.
So coming back to that discussion about core points, if we were to summarize that, would it be fair to say that you're trying to trim this map of 300,000 prefixes to a more manageable 10 or 20,000 or something on that order, by ignoring the path behind the core point, right? So you're trying to measure performance to the core point and making the assumption that behind the core point, the path is the same, so there's not much advantage to collecting the measurement there.
Well, that's almost right, but it's so you're absolutely right. We're looking for these places where users are hanging on to the edge of the internet, and we don't want to have to map out to every user, and we can't either. If you started doing performance measurements to home users, it would cause a lot of uproar. Okay, it's intrusive. It might cost them money. You can't really do that. But the point about why we stop at the core point, it's not so much that we assume the rest of the path is the same. It's that the core point is chosen so that all of our paths intersect there anyway. So it wouldn't matter which server we chose. We couldn't have any impact on what happened afterwards.
I see. Yeah.
So measuring beyond that point, it doesn't provide any useful information.
You know, all these users are sort of behind the same, you know, exit number on the highway, and so you're measuring the performance on the highway to each exit in a sense.
Right, and from that point forward, the route's the same anyway, and we can't do anything about it. We can only choose the exit.
Right.
Cool. All right.
Well, there's an elephant not in the room, Bruce, that I want to ask you about. The elephant not in the room being the hyperscale cloud data centers that you know, have not been part of this discussion at all. And this is actually a course on cloud networking. So why are we talking to you? Is Akamai a cloud service?
You've got two questions there. Why are you talking to me? First, I may be the only one who was willing to talk.
We'll have to see.
You know, that's sort of like, you know, why are you looking for your wedding ring over here when you know you dropped it over there? Well, this is where the light's better. But is Akamai a cloud service? That's I think the answer is yes. In some ways, we're a unique cloud service because we have a very widespread deployment. Rather than establishing a presence where we have a small number of data centers, maybe a few dozen with thousands or tens of thousands of machines in each one, we have thousands of locations, but on average only, well, we could do the numbers, but I don't know, 100 machines in each location, maybe a little less than that. So our deployment is a little bit different than the mega data center type of cloud services that people might be familiar with. But on the other hand, it is a cloud service in the sense that we offer to the content providers a service which is, we'll help deliver your content, we'll provide the infrastructure, you don't have to worry about the details of where it's happening or how we get it done too much, and it's just something you outsource. And in that sense, I think it is a cloud service. Another distinction is that we're a cloud service where our customers are the content providers, not the end users. The end users don't pay us directly. Okay? It's the content providers who pay us to help them provide better services to their end users. So it's a little different than, say, other cloud services. For example, if I'm at home and I do a Google search, I think I would say I'm taking advantage of a cloud service. They're providing me with search results, and it's done somewhere in the cloud. But I'm an end user. Or if I use Dropbox to store my files, that's a cloud service. I'm an end user. But Akamai's customers aren't the end users. We interact with them, but the customers are actually the content providers.
Fair enough. So the role you have at Akamai does give you some freedom to think about the future. So one question about the future is, do you think that the hyperscale cloud providers will move into more of the kind of role that Akamai has, that instead of a small number of very large data centers, a large number of more geographically distributed small data centers? Do you think that's a direction that other cloud providers will go?
Or from your perspective, do you foresee moving into providing general purpose compute at your locations?
Well, let's tackle the first question. I think it's already happening, right? There are other companies like Google who has done the same sort of thing. Originally, because of the great demand for YouTube video, Google not only has built their own backbone, but has also established servers inside of many other networks that they can serve their YouTube videos from. And their deployment has grown very rapidly over the last 3 years, to the point where at least it's on sort of the same scale as Akamai's. Maybe not quite as diverse, but it's fair to say it's on sort of the same scale. And they're also using those servers now as a front end for other content besides YouTube, such as for the search page. Microsoft is moving in the same direction. Bing is moving in the same direction. All three of these are cases where we have customers or former customers of Akamai that are so big and have such tremendous content demands that they have decided that they want to do some of this themselves. They see the value in this kind of broad deployment. So that happens. There is some movement towards doing that. And it makes sense. Others may do it too. As far as Akamai offering sort of a general purpose computing platform, it's hard for me to predict the future, but my understanding, and I'm not an official spokesman about corporate strategy, but my understanding is right now we're really looking at trying to satisfy the needs of our particular customer base, which are content providers. Our customers are not the general public who want to rent resources from us on a small scale to do their processing or their storage. And so, although in the past, as far back as like 1999, we did have an offering where we could provide a virtual machine to whoever wanted it. We discontinued that, and I don't know about plans to go back in that direction. But again, I'm not necessarily privy to all strategic decisions that the company might make.
Cool. Any final questions from Bruce?
I think we are close to time, but Bruce, do you have any interesting or exciting war story or final thoughts that you would like to share?
I do have some. I do have a few war stories.
Okay.
I have to do this very quickly though. So let me just tell you a very short one. When I was head of engineering, one day we got a frantic message from the network operations center that one of our servers was reporting an incident in which it was receiving properly authenticated messages, but the format was bad, and so it was throwing up errors. And our immediate concern was that somebody had gotten a hold of a private key of ours that could be used to sign messages, and was now crafting control messages and trying to send them around to different Akamai servers, perhaps in an effort to hijack the system. And they were not quite right. The format wasn't quite right, but it was really close. And we didn't know how much time we had before this party, lighted on the correct format and then actually started to impact what the system was doing. Well, this was the early days, so with a few engineers, we stayed up 2 nights in a row trying to sort this out. And then we finally realized it was just a server of ours that had fallen off the rolls several months earlier and hadn't got any software updates. And it was dutifully trying to rejoin the home system, like V'ger in the first Star Trek movie. It just wanted to come home. and we mistook it for an attacker. And it got me to thinking that we don't really have any idea how many other servers have been abandoned out there. I mean, once you start deploying tens or hundreds of thousands of servers, it's not just us. I'm sure Google and others have servers all over that are just there like, what happened? Why am I not connected anymore? But then the most embarrassing thing was after a little postmortem, we realized it had been sending these messages for 3 months, and the alerts had been firing for 3 months, and just nobody noticed it before. I could go on and on with these kind of stories. They're fun. There's a little lesson in each one, I think. Something there about it's a little brittle to just have a static configuration file that has a list of all your servers in it, and if there's ever a deletion from that file, you've got a server that's going to not get its software updates. That's not a good design, and that's something we learned from that incident.
Yes. Yeah. That's kind of a similar growth we ran into in the 1980s in terms of having fixed everything in the world.
Right. It seems much better to build in mechanisms for dynamic configuration when possible.
Cool. All right, so I guess we'll about have to wrap it up there.
Sounds good, yeah. Bruce,
Okay.
Thank you so much for taking the time to talk to us, and this was very informative.
Thanks, guys. Thanks for inviting me, and I hope all the students in the class are enjoying their time, and I think they should be lucky that they've got such interesting instructors to teach this course.
Thank you.
Thanks a lot, Bruce. Thanks for your time.
Hi, I'm Roy Rapoport. I manage the Insight Engineering and Product Network Engineering groups at Netflix. I've been managing the Insight Engineering for about 2.5 years here. I've been at Netflix for a little more than 6 years, which in Netflix terms is actually pretty ancient. It's my 4th job at Netflix in these 6 years. I think I'm on manager number 9. I joined Netflix on the IT side of the house back when we were running physical data centers, and my background, generally speaking, is in IT and operations.
Cool. So Roy, you mentioned that you've been at Netflix for a while and you started out working with inside their data centers. How has that transition worked out? So why did you move in the first place, and how did that happen?
Well, so if you think back to 2009 when I joined the company, we were starting to launch our streaming service, and we had great hopes for it. But prior to the streaming service, we were running the DVD business, which we still have. It's our legacy business. The DVD business was US only, and had some characteristics that were very different from where we saw streaming going. So for one thing, again, it was US only, and expanding a physical media business into international territories is actually a pretty big hurdle. So we didn't really expect to do that, I think. The other thing is latency was less of an issue. So if you think about it, if you're working with our site to figure out what you want to have sent to you, you were creating a queue of DVD discs. And if the site was not available to you at all, that's fine. We would still send you the DVD disc. And the DVD disc would take a day to get to you, and then you watch it for however long you want to watch it. And then you send it back, and it takes a day to get back to us. So the typical sort of really transactional latency for what it was that we're actually delivering you was measured in days.
Right.
It's a little different with streaming. So with streaming, one, we knew that the barrier to serving international territories was going to be really very low. Two, we thought that we could expand our customer base much faster. And three, if you're streaming, you actually need to get access to the website in order to get what it is that you're paying for. If our website is down, you're not just like not managing your queue, you're not actually getting the service you want from us. So availability becomes a lot more important. So really what we're talking about is availability, expandability, both in terms of sort of customers and load, but also in terms of regional expansion. Building data centers is tough. There are a few companies out there who do that really, really well, Google and Facebook. But I would argue that unless you're the size of Google and Facebook and a few others, chances are you probably don't want to have to get better at that than you absolutely have to. And we saw moving to the cloud as a really nice opportunity to be able to scale to other countries and regions in a much more lightweight and agile way than building data centers and having to figure out remote data centers was going to be. So those factors ended up driving the decision to migrate to the public cloud rather than continue to manage our own infrastructure.
I see. And how easy was this transition? What did it entail when you moved from your own data center to the cloud?
I've occasionally been accused of being overly precise, so I would say that it's important to distinguish how easy it can be from how easy it was for us.
Right.
One thing that a lot of companies do as an ad hoc way to deal with this is to try to basically sort of forklift their infrastructure to the cloud. And while I think that creates potentially significant ongoing management issues once you've moved into the cloud, it probably creates an easier cloud transition than what we did, which was to really rebuild our entire operating stack to be cloud native. So for example, in our data centers, we had maybe 5 or 6 or so different applications responsible for managing streaming. And those applications were all very large, very monolithic. They all did a bunch of different things. When we moved to the cloud, we rewrote our entire ecosystem to be much more of a service-oriented architecture environment with hundreds of different applications responsible for ongoing streaming. And each of those applications, of course, is much smaller than the previous large monolithic applications. So it took a while. You know, it took a year or two to get to the point where we said we were 100% streaming from the cloud, and we're just about recently finished the cleanup for sort of the last vestiges of data center dependencies.
Ah, really? So just about finished cleaning up means about a 5-year span.
Yeah, I mean, the thing is basically, I think as is the case for a lot of projects like this, the first 90% gets done in the first 10% of time, and the last 10% of the deliverables end up taking more time. Long tail is a problem for almost every project I've seen.
So in the process of that transition, of course, there's a lot of software engineering work to be done. But you probably also ran into some challenges that were specific to what you were trying to do in the cloud. Performance or other issues. What was the most interesting challenges that you ran into?
You know, it's really interesting how assumptions have to be challenged when you move to the cloud. Back when I was in sysadmin on the data center side, I was working with our streaming infrastructure people who about on a weekly basis, actually, I would sit down with them on Friday because we would call this weekend readiness because the weekends are our busiest time. And we would look at every single streaming server we had, which started off with about 40, and then we ended up with about 60. And we would look at was any of them different from the other ones in really trivial ways. So they would occasionally flag the fact that one server would have, let's say, 3% better throughput than the other servers. And they'd ask questions like, why is that? Because obviously they should be the same. And we'd look into that and be like, oh, that server is on hardware that has, 6-month newer CPUs. And seriously, guys, do we really need to worry about 3% better? But when you have 40 to 60 servers and you have a homogeneous environment, it's tempting and intuitively sort of naively simple to think that they should all be the same, and you should be able to look at all of those servers and figure out what's going on. That same application today has something in the order of about between 1,000 and 1,500 servers. And those 1,000 to 1,500 servers, the specific servers that are serving that function today are not by and large, the servers that were serving that function last week, because the average lifespan of an instance in our environment today is something on the order of 2 to 3 days. So I'm sure other people have talked before about the whole pet versus cattle paradigm. But when you've got thousands and thousands and thousands of servers, you stop being able to scale up your ability to look at each one of them. And you stop caring. And so your goal then is to figure out sort of what the aggregate performance of your systems is. And at the same time, how do you build systems, detection and orchestration and remediation systems that can actually identify the underperforming part of your ecosystem, even when it's a very small part of your ecosystem? And then what do you do about that? Now, in that case, actually, the cloud makes it easier, right? If you notice that there's a server that's not performing well for you, well, easy enough, throw it back and run it.
You mentioned reliability as one of the key concerns to move to the cloud. Can you talk a little bit about what was the decision process there in selecting locations, in selecting providers? Some enterprises have gone with either multiple data centers, certainly, or maybe even multiple cloud providers for reliability reasons. Did you consider those trade-offs?
Yes. We looked into multiple cloud providers. The problem is, in order to deploy into the cloud, at least back in 2009, you had to have some pretty reasonable orchestration systems, and you had to have some pretty good understanding of the actual specific cloud environment you were going into. The age of orchestration systems that were cloud independent was only starting, and we didn't see any good commercial offering there, so we were going to have to build our own. So going into multiple cloud providers was going to be a significant investment, and we wanted to sort of hold off on that and push it off as long as we could. Separately from that, of course, we can talk about why we haven't done that now that it's 5 years later. As for multiple data centers, that was pretty important to us, but we're in the Amazon cloud. Amazon's infrastructure basically has, at a high level, the concept of a region, which is a geographically located place. So for example, one of their first regions was what they call US East 1, which is somewhere on the southeast side of the United States. I don't remember off the top of my head if they publicly say where. Actually, they say it's Virginia, don't they?
Yeah, I think so. I think that.
Okay. So basically, US East 1 is an AWS region in Virginia. Now, every region is made up of availability zones, which at a high level you can think of as a data center that is somewhat geographically and from a network and power perspective, separated from the other availability zones. So US East 1 has several availability zones, each of which should, in theory, not be able to actually take down any of the other availability zones. You decide which availability zone you want to deploy into, and we typically follow a 3 AZ or availability zone model, where every one of our applications gets deployed into those 3 AZs, and therefore we can tolerate the failure of any one availability zone pretty easily. So with Amazon's availability zone model, that actually does give us data center redundancy in a way that, frankly, we didn't have before. And for a while, we chose to basically look at that and not necessarily develop regional failover capabilities or regional redundancy. And so, for example, we were originally serving North America, actually the Americas in general, out of US East 1. When we expanded to Europe, we expanded to EU West 1, which is out in Dublin, and that worked reasonably well for us for a long time. In 2012, toward the end of 2012, right around December 24th, 2012, we decided that regional failover and regional redundancy would be a good thing. And so we started working on that capability and brought it up online in the next 6 to 9 months. So now we serve the US out of both US East 1 in Virginia and US West 2 in Oregon, and have the ability to fail over between. And December 24th, 2012 was when Amazon had a pretty significant regional outage in US East 1, and that's when we decided that we wanted to have a little better uptime.
I see. And also, we haven't really talked about Amazon's wide area infrastructure. So far, we're talking about mainly a cloud deployment inside the data center. So you have multiple locations across the globe from where you distribute this video content, right? How do you choose locations for that?
The last figures I heard showed us taking up something like 37% of internet bandwidth, which is kind of a lot. We use our own in-house content distribution network called OpenConnect to serve that. So there's a group here responsible for actually deploying little OpenConnect points of presence POP POPs and OpenConnect cache appliances across the world. So they've got thousands of cache appliances that they deploy into both large ISPs and internet exchanges to enable our customers to get great bandwidth for their streaming wherever they are.
Cool. And how is the work divided then between OpenConnect and a smaller number of more centralized data centers?
Well, so the way it works is you or your students are somewhat likely to be Netflix customers. If you're not, I encourage you to try. It's a pretty good service. So when your device wants to talk to us, so when your device logs in, it talks to the cloud. When your device presents you with a list of recommendations, it talks to the cloud. Everything you do in terms of a human being interacting with their device and their device interacting with us typically goes to the cloud and to the sort of, think of it as a command and control systems. As soon as you hit play, the last thing that essentially happens is you get a license from us because of our relationship with the studios, we have to provide our video at the DRM. You get a license from us and you get a list of where your device can find the videos. And that list essentially points at OpenConnect appliances. And let's say it's a movie, it's a 2-hour movie, and it's a movie that you really like, so you're actually going to watch the whole thing through. At that point, you start actually streaming the movie from the OpenConnect appliances, and you don't really interact with the cloud for any sort of meaningful way, other than sending us a heartbeat every minute or so. And then, of course, if you hit pause or play, you'll know about that, and you might interact with us again.
We were talking earlier about availability in the cloud and such. So you worked a lot on making services reliable and dealing with failures. Can you tell us more about that?
Sure. We've publicly talked about what we call the chaos efforts within Netflix. We, generally speaking, have come to believe that the way to make your environment more reliable is by introducing more failure. Because when you do that, you basically you sort of inoculate your environment to failure. This started early in our cloud journey with the introduction of Chaos Monkey. So Chaos Monkey was a relatively trivial system we built that did something very, very simple. On a daily basis, it finds every application in our environment and kills at least one instance serving that application in our production environment. The idea is that eventually you're going to lose a server, and you might as well make sure that you're inoculated against that by making sure you lose a server every day. Because if you lose a server, once every month or two, there might be a temptation to say, well, yeah, that's unfortunate, and every time I have to bring up a server, it's a big deal, but I only have to do that every month or two, so I can deal with that manually. If you're guaranteed to lose a server every day, chances are you're going to build your application to be automatically resilient to that. Amusingly, and this is, I think, worth making an explicit point about, this was not in response to thinking that AWS was going to be a particularly less reliable environment for us. It's actually the opposite of that. If AWS was such an unreliable environment that we were losing instances left and right, we would not have had to write Chaos Monkey.
Right.
Sadly, or perhaps the opposite of sadly, AWS is reliable enough that left to their own devices, people could afford to get lazy. And in fact, I've talked to a whole bunch of other smaller companies just starting to run their infrastructure in the cloud who basically say, yes, everything is manual, but the good news is it gets killed so rarely that we'll just deal with it at 2 o'clock in the morning if we need to. So that was the first step. But server redundancy is relatively easy. That's a problem that, generally speaking, has been solved in the data center a long time ago. It just basically means that you want to make as many of your applications stateless as possible, and then sort of localize the hard work of figuring out how to make stateful services survive failure to a very small subset of your systems. But once you've done that, you've got to look at the other more complex problem, which is, as I mentioned, we have hundreds of applications that are responsible for making sure that you can stream. Those inter-application dependencies essentially create a potential environment where, if you're not careful, what you've done is you've created a monolithic app that's very hard to debug, and where basically any one application having either a failure or even just a slowdown can create a wildfire effect as the impact from its failure propagates upstream. So for that, you really need to firewall bad performance. And you really need to firewall service failures as close to the location of the failure so it doesn't spread. We've done a bunch of work as part of our ecosystem and platform to make it so when services talk to each other, they have reasonable fallbacks, and they have the ability to sort of tolerate gracefully the failure of the service they're talking to. We released that as an open source library called Hystrix, Hystrix. And the way Hystrix works is relatively simple. If I'm a service who talks to you, and we know that the question I'm going to ask you is, for example, hey, listen, what's your favorite food? Well, if you know that that's a question I'm going to ask you, you could say, hey, listen, if you ask me what my favorite food is and I'm not around to answer that, just assume it's M&Ms. So by having that default, it basically means that, if I ask you a question and you're not responding really quickly, as quickly as I need you to, I can just say, okay, great, I'll go with M&Ms. In a more, in a less abstract way for Netflix, that means that, for example, if I ask, what are the best recommendations for Jane, our user, and our recommendation system can't actually respond quickly enough, well, maybe there are some generic recommendations we can come up with that could get updated even maybe on a daily basis for a larger audience. And definitely those are not the best recommendations for Jane, but they're better than having a black screen or the Netflix service is not available right now, try again later. And then once you've got that system, you test the heck out of it. So just as we introduce chaos monkey failures across hundreds of applications on a daily basis, we introduce these sort of application failures consistently across our environment and collect information as to what happens to streaming when you fail a given application. Separately from that, and that's sort of like on a very much like on the application infrastructure level, we talked about regional failures. We currently serve US out of 2 regions, and we make sure that we can easily fail between them on approximately a monthly basis. It ends up being sometimes a little more frequently than on a monthly basis, but certainly I don't think there's a month that has passed in the last year or so that we haven't essentially failed over all of the Americas traffic to one region, then to the other region, then equalized again. Any failure response mechanism you have is worthless unless you test it rigorously and ongoingly.
So do you also do a similar thing for networking, where you try to fail connectivity between different services, or at the higher scale, perhaps bring down a location that serves content, things along those lines?
Yeah, so connectivity between applications within a given region or AZ is something we test. We don't try to test specifically the networking layer because the networking layer is proxied nicely by an application failure. In other words, in order to not have a service be able to talk to another service, that other service needs to fail or the network needs to fail. And to be perfectly honest, between just you and me and the hundreds or thousands of students who might be seeing this, we far more often have inter-application connectivity problems that are due to software bugs on our service layer than we do due to networking issues due to Amazon. The vast majority of our failures really are self-induced rather than Amazon-induced. So we focus on the likelihood of failure. And again, it doesn't matter whether the problem is that a router is misbehaving or an application is misbehaving. Either way, you can't talk to something, so let's make sure we test that and make sure that we're resilient to that. Does that make sense?
You test both failure of components. You also test degradation of certain components.
Right, yes. So failure is actually a lot less interesting than degradation.
Right.
Because failure, so listen, if you're RESTful, right, so you're just making HTTP call, and you've got service A talking to service B, then in some respects, the best failure mode is service B just basically no longer listens on port 80.
And immediately it's not going to answer.
Yeah, it's a fast failure.
Yeah.
The worst thing is, if you've got a call that's supposed to take, let's say, 20 milliseconds, and it just hangs. And of course, it's not that call that hangs. It's the next 1,000 calls that hang and completely trash your thread pool. That's what Hystrix is built for, because Hystrix is built to support either a failure mode where you're not listening, or a failure mode where you're returning a bunch of errors, or a failure mode where you're just slow. And that's what we actually test. When we test for either one of these failure modes. And slowdown is definitely the thing we're worried about the most. So that making sure that slow failures turn into fast failures is really important to us.
So how do you do that? How do you turn them into fast failures?
So the nice thing about Hystrix is it basically has a timeout. So Hystrix basically says not just, hey, if you get a failure or you can't even talk, give back this cached response. Hystrix says if you get a failure or you don't get a response within a very small number of milliseconds, then return the cached value and forget about that particular call. We've built, my own team, the real-time analytics part of my team, has actually looked at call history for any given one of these circuits and ongoingly can provide automated recommendations for the timeout values. So for example, if you've made 10 million calls to a given interface on a given system, and the median response time is, let's say, 10 milliseconds, and the 99th percentile is 20 milliseconds, then you know what? Setting your timeout at, let's say, 22 or 23 milliseconds is pretty reasonable. The vast majority of the time, you're not going to time out for no good reason. But if it starts going to 30 milliseconds, then you'll see that circuit thrown open.
Right.
And that's how we basically turn slow failures into fast failures.
So that seems like a really nice pattern to be able to, to fail over to a cached value. But it might be dependent on the particular application whether that makes sense to be able to do that. Are there cases where that's hard and you really need an answer, and then what do you do?
Yeah, there are definitely cases. So in our environment, there are definitely cases where that's hard. But let me actually illustrate this with an example not in our environment. I do online banking. And when I log into my bank site and I want to know how much money I've got, I don't actually want it to give me like some sort of useful cached value. I actually kind of want to know exactly how much it is. In fact,
what you have, maybe the cached value, default cached value is pretty good.
Yeah, and in fact, if it can't give me the actual right now number, I'd rather you just told me to come back later.
Yeah.
The good news is we are not in banking. And so in many different cases in our environment, that's an easy thing to do. We don't even actually need to validate that you're an active user to be able to stream, because you know what? If we turned off your account a few hours ago, and now you're trying to stream some movie, what is the actual harm if our subscriber information system is down in letting you stream? It's non-existent. So in many of those cases, as you noted, we can actually serve pretty reasonable fallbacks, but there are cases where that's not going to work. If you want to log into your account to actually manage your account and, for example, give us a different credit card number, that's the kind of operation, for example, that we can't really actually do reasonable cache values on. So yeah, there's a small subset of systems here that actually can't be served with cache values. But we try very hard to make sure that it's a small number of systems. We identify them explicitly. And if you're one of the owners of those small number of systems, that creates an additional operating load on you, because you have to operate at a much higher level of reliability than another system.
So Roy, could you talk a little bit about how network performance impacts you either at the edge servers or in the cloud?
Between us and the user, the end result for that is one of two things. Less harmfully, it can mean that, for example, when you're interacting with our application, it can feel a little slow or sluggish. That's actually less of an issue because it pretty much doesn't really take a lot of bandwidth or high latency to be able to, for example, scroll suggestions. What's much more significant is the bandwidth you're going to get for streaming. So when you hit play, what happens then? We've done some great work with adaptive streaming. So what that actually means is that we can actually start you off very quickly with a relatively low bandwidth stream. And then as we discover the capabilities of your connection, we can seamlessly increase the bit rate of your stream. And then potentially if we see slowdowns, we can actually seamlessly downgrade the bit rate of your stream. We can also switch between cache locations automatically and seamlessly if we see that, for example, you've got a problem talking to a given cache. But in the end, that's sort of dealing with all of the potential network problems on our end. If you've got a, let's say 2 megabit DSL connection, then, well, you're never going to exceed a 2 megabit, stream. And if your ISP is doing something to degrade your streaming connection, then there's not much we can do about that. The one thing we've been able to do is to at least make it more visible to people. So we have been publishing for the last, I want to say about a year or so ago, an ISP speed report.
So one thing you mentioned was variability across time. The performance you can get can change. Can you say something about how dynamic is it? Is it easy to figure out the right rate over time? And where does that variability come from, if you know?
Well, the variability can come from any number of different things. If I'm at home, for example, and for example, I look at my home, right? So if my spouse is watching Netflix and I'm doing a video call with somebody, that could have an impact. If I'm downloading some sort of huge file or a BitTorrenting, obviously that can affect things. So even at the sort of most localized environment, we can do things that can impact sort of the total available bandwidth. Irrespective of that, if you just go up one stream, then in most sort of residential cable installations, for example, a given neighborhood or part of a neighborhood are sharing some bandwidth amongst themselves. So if I'm watching Netflix and somebody else decides to do something that's bandwidth intensive, that can affect me, etc. That's the answer to sort of what can affect the over the ongoing available bandwidth for streaming. And by the way, it can even it might not even be bandwidth, right? I mean, if I'm streaming something and then I run a large compilation job on my laptop, that might slow down my laptop and allow my laptop to stream less quickly. So I don't know that there's really a good answer for what's the right bit rate over time. I think what we end up looking at tactically, it's what's the right bit rate right now. Right now and for the next few seconds, what can you stream at, and do we need to basically downgrade, or can you potentially do an upgrade? But over time, as we collect this information, we can also find, relative sort of directions in which the trend is going. So imagine if there was a cell provider let's call them, Celco, because I want to avoid using real provider names here. And we know that streaming on Celco has consistently sort of had a time-weighted bit rate of, let's say, 160, actually, let's call it 350 kilobits. Well, it turns out the 350 kilobits is actually the top bit rate we have for cell phone streaming. Well, if you're spending a lot of your time at 350, we might be interested in figuring out what would happen if we had, let's say, a 700 kilobit rate. Because 700 kilobits at twice the rate could actually be a noticeably better picture. So we might release a 700 kilobit encoding and see if suddenly Celco customers are getting the 700 kilobit.
So you're making decisions basically online at the time scale of seconds, a few seconds, seeing what's currently working. Is there also a predictive aspect in some sense? I mean, you have a lot of information available, a huge amount of information of what has worked in the past, what's worked for me, what's worked for similar customers in this area. Is there an opportunity and do you use it to do some sort of prediction of what will work well?
Sure. I mean, we do that all the time. And sometimes it can look relatively, mundane and trivial. So one of the things I mentioned in the beginning is we start off streaming with a relatively low bit rate. We do that because if you think about it, when you start streaming, you're trading off quality for how quickly something starts.
Mm-hmm.
And we know that there's a connection. There's a direct connection between how quickly you start seeing something moving on your screen and how likely you are to actually, get engaged. If we say, hey, great, listen, we think that eventually you'll be able to watch something at 8 megabits, but we're going to have to spend the next 30 seconds sort of buffering that, then what that basically means is that we're saying, great, so you hit play and then you wait 30 seconds. You know what? Chances are, if you need to wait for 30 seconds, what you're actually going to do is you're in a switch, and then we're going to lose you.
Mm-hmm.
You're more likely to stay around if it takes us a second or two to start, even if the first sort of screen, which is, let's be honest, a black screen, is terribly pixelated. So we play around with that all the time to figure out what works better for our customers. We have a culture that is deeply committed to A/B testing. So when we have hypotheses about what works better or worse for our customers, it's relatively easy to test that, and we don't tend to operate on untested hypotheses.
Do you do a similar exercise? Given your large footprint, you're in a pretty good position to say, okay, these customers in this neighborhood see this bandwidth on average, and this is how it varies over the day usually. So do you maintain that kind of sort of weather map for bandwidth?
We have all of that information. It's not clear to me whether or not that's something that we pay a lot of sort of operational attention to. We do want to be aware when customers on a given provider, for example, have problems streaming, and we've gotten better at noticing these sort of problems. But that's for the definition of problem. That's not just, oh, they seem to be streaming at a slightly lower bandwidth. It's more, oh, wow, holy cow, nobody from Celco seems to be able to stream. Let's figure that out.
I see. Yeah.
It's also worth noting that one of the advantages we have in running our own CDN is that we can be ruthlessly focused on serving our use cases and our needs.
So Roy, we've been talking about your deployment on Amazon. How's that been evolving over time? Things have been changing, right? They're deploying VPC now. Can you tell us more about this?
When we got into the cloud,
Mm-hmm.
Amazon was supporting what they called EC2 Classic as a networking model. EC2 Classic basically meant that every instance got both a private IP address and a public IP address. And the only thing stopping access from the outside world was essentially security groups. Mm-hmm. This was a highly unmanaged environment from our perspective, because it meant that they're running their own DHCP servers, and you had no control of creating different networks. In the new world, And Amazon released VPC, Virtual Private Cloud, maybe around 2011, if I recall correctly, and it's now become the default way to deploy systems. One of the interesting things, and this goes into maybe your question about where the cloud is going, is that deploying in Amazon and managing your environment at Amazon, at least, has become a lot more like managing your own data center in the old days from a networking perspective. So whereas in our data center we had a 10/8 and we allocated it appropriately and had test networks and prod networks and several different networks focusing on whatever it was that they're doing, when we moved to the cloud, we lost that ability. So we were in an undifferentiated network environment from a numbering perspective. And now that we're moving to VPC and most other people are actually deploying directly into VPC, we're sort of getting that back. And we're getting better control over things like routing, better control over things like subnets and access between systems and subnets in a way that actually feels a lot more natural for any of us who were operating in the data center before. That's the big project we're working on right now from a networking perspective, the migration into VPC. For people who have a smaller footprint or started in the last 2 or 3 years, potentially that's not an issue because they would have started originally in VPC. We didn't. And we're finding all the interesting and delightful ways in which we made some assumptions at the time that we're having to rethink. So from a networking perspective, the VPC environment is particularly interesting and can feel a lot more like something you have control over than the classic environment within Amazon. At least for us, tactically, that's what we're focusing on over the next year or so.
In the case of your Netflix's use of VPC in particular, are the you mentioned that you're moving to VPC and it's becoming more like a traditional data center.
Yeah.
So what a traditional data center, there's a pretty broad set of network engineering tasks you have to do there. Some of them clearly don't apply, like purchasing the physical hardware. But there's routing, there's route optimization, there's access control and network segmentation. What is the, what kinds of engineering, I guess, do you do in the virtual network in the cloud?
I would say you do most of what you just talked about, other than buying hardware. But even then, I'll tell you, when you get to our size, you end up doing a surprising amount of capacity management, even in the cloud. And you end up, because of the way cloud pricing works, at least in Amazon, where you can essentially buy reserved capacity, you end up following many of the same sort of models.
No, that's interesting. Yeah.
Really, from our perspective, the biggest difference is not so much whether or not we plan our growth and sizing and make purchases. It's the lag time between when we make purchases and when capacity is available to us, which used to be potentially weeks and is now potentially minutes.
Mm-hmm.
But for us, moving to VPC is partially driven by, frankly, the fact that Amazon's next generation network stack is in VPC, and we see better performance in VPC, and also because that's the direction Amazon is going. So new regions are typically VPC only. So we are doing this in order to be able to essentially continue to operate in Amazon's most advanced environment rather than the sort of more classic environment.
Mm-hmm.
But other than hardware purchasing, network engineering ends up being relatively similar in the cloud, which is actually an interesting opportunity for failure, because the cloud gives you an opportunity to do something better, which is to essentially automate all of these things. So it gives network engineers the ability to actually think about their environment really as a software-defined network and to be able to automate all aspects of management and provisioning. But I think that's an area where, frankly, network engineers are traditionally sort of not necessarily interested. So I found network engineers, in my experience, and having been a network engineer for some time, to be somewhat conservative in many cases. This has not been the area where we've seen the most advance around automation. That's more been on the application side and the system side. Mm-hmm. So we now have the opportunity for next generation of network engineering in the cloud that actually gives you the ability to control things like you were in the data center, but also the ability to automate things like you should. And hopefully people will take that opportunity and run with it rather than continue to be as manual as they were in the data center.
Mm-hmm. So what sorts of tasks would be automated?
Well, for example, if you look at creating networks, right? You can create networks automatically now via APIs, because again, every aspect of network engineering in the cloud is API driven. So whether it's changing security groups or changing networks or provisioning load balancers or moving instances around, all of that stuff is automatable. The sky's the limit, really, in terms of building your system to be less human driven.
So thanks so much for your time. This is a really informative chat.
Thanks, guys. Have a great day.
Okay.
You do. That was our conversation with Roy Rapoport from Netflix, who told us about why Netflix moved from their own data center to using Amazon's offering in the cloud, and how that usage is evolving over time as they get more and more flexibility with managing the network, which brings more traditional tasks that data center operators have to deal with, such as routing, congestion control. All of that stuff has to be now taken care of by these application deployments.
And in that environment, I guess there's also more of a push towards some of the ideas in software-defined networking, since when you're operating in a cloud environment, everything is controlled by APIs. So that approach of more programmable network engineering may be a direction that the industry goes for those virtual networks in the cloud.
Right.
So then I guess we also heard a bit about the performance challenges that a large service like Netflix deals with. First, both inside the cloud, where you might have performance variability or failures that are the common case by design. And your application has to deal with that, perhaps by using default answers that you can supply much more quickly than you would be able to if you needed to wait for all of your hundreds or thousands of queries to assemble a response to actually completely finish. And then that's inside the cloud, but as you move out to delivering the content to the client, then there's a different set of performance challenges.
Right.
In the last video, we learned how to start our mini data center, and we saw how our video streaming application was affected by congestion from other tenants. In this assignment, we'll act as a network operator and quantify the problem by implementing a traffic monitor. We'll write a small amount of code in this assignment to piece together a traffic monitor. In doing so, we'll be able to collect statistics about the amount of traffic each host sends and receives. We use the same topology and host applications as the previous assignment. We'll do this using the OpenFlow protocol, which gives our SDN controller the ability to program switches. A lot of this code is provided for you, but understanding how it works at a high level may be helpful. A controller will send an OpenFlow message to each edge switch asking for port statistics. Each switch collects information about the number of packets or bytes sent and received from each port, the number of dropped packets, and several other statistics. After receiving a statistics request, each switch sends a reply to the controller with the stats for each port. It's important to remember each statistic applies to only one port on the switch, and each port connects to another switch or host. So let's see this in action. First, I'll demonstrate the system as you'll see it before you implement your solution. Then I'll show you how to verify your code is working as expected. Just like the first assignment, we'll start 2 terminals or 2 tabs. In the first terminal, move to the directory CloudNet MOOC, and we'll start our network emulator using the command sudo mdc and pass the parameter vid. You'll be prompted for the sudo password, which is mooc, lowercase mooc. So this starts the mini network emulator with the topologies and applications I described in the previous video. In the second terminal or tab, move to the directory CloudNet MOOC, mini DC controller, and then you'll want to start our SDN controller REU with the command REU-manager and pass controller.py. Now go back to the first terminal and press enter.
So a Chrome browser should pop up and the video should start playing. Like we saw in the first assignment, the video quality is poor. We can downsize the browser since we don't need it right now. Now open a new Chrome instance from the desktop, not from the one playing the video stream, since this is in a sandboxed environment in our emulator. And bring up our cloud dashboard by going to localhost or 127.0.0.1. In the top section, these two tables describe the types of tenants in our data center and the applications running on each host. Video streaming, as you can see on the left, is a tenant with two hosts, and these two hosts are running a PHP server and a Chrome instance. Now, if we scroll down a bit more, we can see there are several empty charts. These will display data collected from our traffic monitor. If coded correctly, you should see a line chart on the left too, and a pie chart on the right. Now, we'll shut down our emulator and examine the code you'll need to add. So type in exit into our emulator and stop our controller by pressing Control-C. Now let's look at the code you'll need to add. Open a terminal and cd to the directory cloudnetmook mini-dc controller. You can either do this in a terminal or in the file manager. And you'll want to open the file bwmon.py. I'm going to use Emacs to do this. But to keep the VM size small, we've only installed the graphical editor mousepad. So you can install your preferred editor using the command sudo apt-get install Emacs, Vim, or Nano. So if you scroll to the end of the file, you'll see this function stats reply handler. This is a function that is called each time the controller receives a statistics reply from a switch. The first thing to note is the variable name, which takes the responding switch's ID, called the data path ID or DPID, and converts it to the representation we saw on our topology diagram. So the variable name will be something like S101 or S102. This next section of code is extracting the number of drop packets from the stats reply. So the reply consists of a list of statistics grouped by port, as I described earlier. So this block of code enumerates each item in body with the current item name stat. This code then sums all the drop packets from each port and then passes the result to our bandwidth statistics module. Now this will provide a helpful template for the code you need to add. So your code should pass to the bwstats module the number of transmitted and received bytes for each host. So in the comments, I provided a description of this function. You'll also need to determine what host is associated with the port for that statistic. So you can use the object self.topo.ports to determine which host is associated with that port. So this is a two-level dictionary that takes the responding switch's name and a port number and returns either a host name, such as H1 or H2, or a switch name, such as S101 or S102, depending on which node is associated with that port. You can also reference the documentation at the top of this file for useful properties and functions in the topology class. One helpful hint is that there are virtual ports built into each switch for actions like sending a packet to the controller or flooding, which sends a packet out all ports. We only care about statistics from ports that are connected to a host. Your code shouldn't be very long. My solution is only 5 lines. Now you can check if your code is working properly by starting up the system again. In the first terminal, cd to cloudnetmook, and start our emulator with the command sudo mdc vid. And it prompted for the sudo password. Remember, it's mook, M-O-O-C, all lowercase. And then we'll start our RU controller by going to the directory cloudnetmook mini-dc controller and starting the controller with the command RU manager and controller.py. Now we'll start our emulator. And our Chrome browser will pop up. So we'll bring up our dashboard now to see the statistics that should be reported. So open a new Chrome instance from the desktop. Remember, not from the one running the video streaming, since that's in the sandbox, and go to localhost or 127.0.0.1. And we should see now that our graphs actually have data. So let's look at the two pie graphs on the right. At the top, we can see the number of bytes sent by each host. On the bottom, we can see the percentage of total traffic sent by each tenant. So if we look at the bottom one, we can see that the traffic on the network is dominated by VLAN 1. And if we look at our chart on the top, we can see that VLAN 1 is our iPerf tenants. This means that our video application is using only a very small share of the available network bandwidth. And since our video streaming application is adaptive and playing in poor quality, we can conclude that there's a lot of congestion on the network or a very small amount of bandwidth available to the video streaming tenant. So now let's close our emulator by typing exit and stopping our controller by issuing the command Control-C. This concludes the walkthrough for assignment 2. In the next video, we'll learn how to improve our routing policy to achieve higher quality video streaming. In the last assignment, we implemented a traffic monitor to collect statistics about each host's bandwidth usage. We saw on our dashboard how one tenant consumed almost all the available bandwidth in the network. As a result, the video quality in another tenant's application suffered. This is partly due to the nature of our applications. Our video stream is adaptive, so when it competes with other flows, the quality is scaled down. It's also a result of the protocol these applications are using. All our iPerf flows are using UDP, so they don't compete fairly with the video stream. Remember from our previous assignments, our naive routing policy will send all traffic through one core switch. As a result, the switch S104 becomes a bottleneck in our network. In this assignment, we'll improve this policy by utilizing all core switches. We'll keep it simple by pre-assigning tenants to each core switch, so you won't need to worry about having to figure out how to balance tenants across the core switches. Specifically, we'll write a small amount of code to generate rules for the edge switches. These rules will route traffic to the core switch based on the packet's destination host and which tenant that host belongs to. We'll use the same topology as before. Switches will be named the same and ports will be numbered the same. We'll statically assign each core switch to handle a different tenant. Here, we've assigned core switch S104 to handle all traffic for VLAN 0, which is our video streaming tenant. And S105 will handle traffic for VLAN 1, which is our iPerf tenant. So our routing policy will look like this. Switch S102 and S103 will forward all packets to S104 that are destined for the video streaming hosts. And switches S101, S102, and S103 will forward all traffic to S105 for iPerf traffic. So the global policy will look like this. This will be done programmatically, but you'll only need to write a very small amount of code to do this. So let's look exactly at what you'll need to write. So I'll start by walking you through the relevant code and then show you how the system should behave if your code works properly. So our setup will be exactly the same as the previous assignment. So let's look at the code you'll need to write. So we'll edit the file policy under the directory cloud.mook minidc controller. So if we open the file policy.py, so we'll edit the file policy.py. If you look at the top of this file, you'll see a description of useful classes and functions that you might need for this assignment. So the first is core switch class, which stores information about the core switches, specifically the name its DPID, and a list of the pre-assigned VLANs that that switch will handle. In the edge class, we have the name and DPID properties. And we also have a list called neighbors, which is the hosts attached to that switch. In the host class, we have name, which is its name, like H6, the MAC address, switch, which is which switch the host is connected to, and VLANs, which is a list of the VLANs with which that host is associated. And finally, we have a topology class. So this has a list of hosts, switches, core switches, and edge switches, and a dictionary of VLANs with the key VLAN number and what hosts are part of that VLAN. The ports dictionary we saw in the last assignment, which takes a switch name as the first key and a number as the second key, and returns the host or switch connected to the port on that switch. For this assignment, you might also find the function getVLANCore useful, which takes a VLAN ID and returns the pre-assigned core switch for that VLAN. In this assignment, you'll edit the class static policy, specifically the build function. But first, let's look at the current policy that our system is using, which is the class default policy. You can use this class as a rough template for your solution. So let's look specifically at the function build, which builds the routing table for our policy. So remember, with this policy, all traffic from edge switches is sent through one core switch. So we can see we start by creating an empty routing table, which is a dictionary. And our routing table is structured as a dictionary where each key is a switch, either a core switch or edge switch, and the value is a list of rules. So we can see here that we then take one core switch from the list of core switches in our topology and its DPID. Then we initialize our routing table with an entry for only that core switch using its DPID. The first block of code creates rules for core switches to send packets from a core switch down to an edge switch. So in each core switch, we install a rule that says if a packet's destination matches some host MAC address, forward it out some port. So which port do we forward it out? We forward it out the port connected to the edge switch for that destination host. So let's look at a quick example before further exploring this code. So suppose we're creating a rule for the core switch S104. If we see a packet destined for host H1, we want to forward it closer to host H1. We do this by sending it out a port that connects the core switch to H1's edge switch, which is S102. So with our destination H1, we'll send it out the port connected to switch S102, which we can see is port 2. OK, now let's look at the second block of code, which installs rules in the edge switches. There'll be two types of rules in an edge switch. The first says that if a destination is a host connected to that switch, it forwards it out the port for that host. So this is what we call a neighboring host. Otherwise, we send it out a port to a core switch. Now in our naive policy, remember we send all traffic to one core switch. So here in the else block, we can see that we determine the out port for a non-neighboring host using the topo.ports dictionary again. We pass it the name of the edge switch where the packet is currently located and the core name, which remember earlier was the single core that we're using in our naive policy. And the ordering matters in this topo.ports object. So if we want to look up the out port on switch S104 for switch S102, we'd type something like topo.ports S104 and then S102.
If we wanted the output on switch S102, we'd reverse it. So S102 would be first, and S104 would be second. So now, your solution will be to implement a block of code just like this second block. But we want to use all core switches. So if we look at the comment for the block that you need to add in the class static policy, we've given you a hint to use the function getVLANCore. So this will return the core switch statically assigned to a given VLAN ID. And remember, the documentation at the top of the file will describe how to find a host's VLAN ID. Now, to verify your routing policy works, let's start up our system. So start 2 terminals, one for the network emulator and one for the controller. And we'll use the vid parameter just as before. And remember, the sudo password is lowercase mooc. And now open a Chrome browser from the desktop. Remember not to open one from the Chrome instance running the video streaming application, as this is in the sandbox. And bring up our dashboard. To load the new policy, select the static radio button and press Update Policy. Then go back to the video streaming application and restart the page. So after a few seconds, we should notice that our video starts to play in high quality. You might need to wait 5 or 10 or 15 seconds before it switches. And you can see the aspect ratio changes and the quality is higher. Let's also look at our traffic monitor data. We can see now that our hosts for the video streaming application are higher. You can see the spike here, where it started playing in high definition. So this means that we're moving toward a fairer routing policy. This concludes the walkthrough for assignment 3. In the next video, we'll learn how to improve our routing policy to handle a larger topology with more tenants. In the last assignment, we improved our routing policy by isolating the 2 tenants across different core switches. In this video, we'll learn how to further improve our routing policy to account for a larger number of tenants than core switches and a skew in the traffic demands of tenants. Specifically, instead of assigning tenants to each core switch, we'll try to balance the load on each core. So with our resulting policy, each core switch should handle a relatively similar amount of traffic, regardless of what tenant the traffic is sent to or from. We'll scale out our topology for this assignment and use 5 different tenants. In place of video streaming, we'll use a memcached application. So memcached is a distributed cache that stores objects in memory. We'll look at finer grained statistics about the network's performance by looking at the page load time, which consists of several memcached requests. We'll continue to use iperf, but we'll also introduce several inactive tenants. So these tenants will not generate any traffic, but will reserve hosts for them. This will simulate a real data center where we don't know the real-time demands of each tenant and instead have to dynamically adapt our routing policy to account for varying demands. Further complicating our data center will be the placement of these tenants. Each edge switch will be connected to 1 host from each tenant. So our topology will look like this. There will be 3 core switches and 4 edge switches. Each edge switch will be connected to 5 hosts, each of which is associated with a different tenant. So we can see here there's a host for memcached, iperf, and inactive tenants connected to each edge switch. Our memcached tenant
will consist of one client and 3 servers. The client will simulate a page load consisting of multiple objects by retrieving one object from each of the 3 Memcached servers in parallel. The page will be considered fully loaded when all the objects have been retrieved, so the slowest response time will determine the page load time. Now, due to a poor pre-assignment of tenants to core switches, our routing policy from the last assignment will assign all the active tenants to core switch S105. And essentially, our new routing policy will produce the same routes as our naive policy, since all the traffic will again be routed through a single core switch. So just as before, S105 becomes a bottleneck in our network. So let's see this in action. So as usual, we'll start 2 terminals, or 2 tabs, one for the network emulator and one for the controller. This time, we'll pass the parameter ADP instead of vid. And if prompted for the sudo password, remember it's lowercase mooc. And then we'll start our controller. In the same way we did before. And hit enter to start our emulator. And pull up our dashboard by opening a Chrome instance and going to 127.0.0.1. And if we scroll all the way to the bottom, we can see a line chart plotting the median and 95th percentile of our Memcached requests. So this is plotting the requests averaged over 20 trials. So our Memcached client is loading 20 pages, each consisting of 3 objects, and then reporting these results. So we can see the median response time is around 20 seconds, and the 95th percentile is around 25. So now let's load our policy from the previous assignment by clicking the static radio button, clicking the update policy button. So if we scroll down again to our line chart, we can see there's a spike where from the policy taking effect. But otherwise, there's not much improvement in the 95th percentile or median response times. So now let's see the changes that we have to make in order to improve our routing policy. Like our last assignment, we're going to add code to the file policy. So cd to the directory cloudnetmook minidc controller and open the file policy.py. So remember, we've only installed the editor mousepad, but you can install your favorite text editor using the command sudo apt-get install. So if we scroll down about 1/3 of the way, we can see there's a class adaptive policy. You'll add your code to the min utilization function in this class. So this function should enumerate all the switches in the dictionary self.utilization and return the switch with the lowest utilization. So self.utilization is a dictionary keyed on the switch name, such as S101, and the value is the total traffic load on that switch. So that's all this function needs to do, find the minimally used switch in self-utilization. So you replace this return function with your block of code. But let's also look at how this function is used in the context of our policy. So this function below, redistribute, starts by creating a list called stats. And then it enumerates all the hosts in our bandwidth monitor and adds to the stats list a tuple consisting of that host's transmitted bytes and the host name. Then we sort our list from largest to smallest using the first element in our tuple, which is that host's bandwidth usage. Next,
we reset the utilization for all our cores. Finally, we enumerate each tuple in our list stats, and the current element is saved in the variable stat. So we store the host name, which remember is the second element in our tuple, in the variable host. And then we invoke the min utilization function that you'll write to find the least utilized switch. Then we save the assignment for that host, so we can later construct the forwarding rules using that assignment. So the code to construct the forwarding rules is provided for you. We then update the utilization for that core with the host bandwidth usage. So now let's see how our system should behave once you've implemented your solution correctly. So let's start up our system again. Remember to use the parameter ADP this time instead of vid. And open up a Chrome browser and navigate to our dashboard. So remember from before, we saw that our response times had a median of around 20 to 25 milliseconds and a 95th percentile around 30. And if we load our previous policy, we saw that it had very little effect on the median and 95th percentile. So I'll let a few points load. Now let's load our new policy by selecting the adaptive radio button and clicking Update Policy. And we can see there's an improvement in both the median and 95th percentile for the response times for our Memcached client. So our median drops to around 12 milliseconds, and our 95th percentile is much closer to the median. So this concludes the video walkthrough for assignment 4.
Hi, I'm Indy Gupta, and I'm a professor here at the University of Illinois. Those of you who have taken the Cloud Computing Concepts course, or courses rather, parts 1 and 2, would recognize me. I was the instructor in that course. And with me here, I have Reza.
Hi, I'm Reza Farivar. I'm a senior software development engineer at Yahoo. I'm also an adjunct faculty at the University of Illinois. Those of you who took my Cloud Computing Applications course, remember my face.
So we are here to talk to you about the capstone course for this cloud specialization. And I'm going to tell you a little bit about the goals of the course, and we will tell you about why the capstone is structured the way it is. So today in cloud computing in industry, there is a wide variety of systems. There is a diversity of systems. And when you want to write code for storing large data sets or processing large data sets, you have a lot of choice. And some of these choices are more complex than others. Some choices involve working with multiple systems and integrating them and worrying about whether or not this wholly integrated system or system of systems is going to work at all or not, while other choices involve writing code in more contained stacks. So for the first, think of an example like Hadoop working with HDFS or Cassandra, and for the second, think of an example like writing code in Spark for Spark batch processing or for Spark streaming. So we're going to give you a feel for both these kinds of programming, as well as for storing data and for processing data, both batch processing as well as stream processing. And while doing this, you'll get to use real data sets, and we'll make available to you real data sets from the Amazon Web Services free data sets, as well as you'll be using the cycles on Amazon Web Services as well.
So I'd like to expand a little bit in one of the concepts that Professor Gupta mentioned here. Right? We have a lot of open source big data systems out there. In some sectors, you have the dominant standards. For example, for batch processing, pretty much the standard of industry is Hadoop. There are then other systems that you have so many different systems that it's actually hard to choose by. For example, databases, right, or key value stores. You have something in the order of 250, I think the last I checked, different systems. So it's actually not quite easy to pick which one is the best and what they offer. And then there are some domains like the new ones, streaming systems. There's still a lot of competition and there's no clear winner at the moment. Right. So I think by taking a couple of these different systems, and we're trying to give you suggestions on which systems to use, these are pretty much either the dominant industry standard or what we think could have a good potential.
Right, and there is, like Reza mentioned, there is a lot of choice out there in terms of what you can use in order to write your programs. And one of the goals of this capstone is to give you a feel for the complexities involved in making each one of those choices. And this is a very fast-moving area. You know, systems are coming out all the time, and each system has a different model than the others. And systems are being improved all the time. So if you look at, for instance, a particular system like Cassandra, its next version is going to be very different from its previous version. So this means that as programmers in the cloud space, we need to be very adaptive and adapt to systems as they're changing and as they're evolving. And part of that is experiencing the current complexity, and that's what this capstone provides to you.
And speaking of complexity, another very important part of dealing with the complexity of these systems is trying to figure out how to set them up correctly, how to feed information from one of them to another environment correctly. In your previous courses, you've seen we gave you MPs, machine problems, right? And everything was kind of set up. In this course, we don't want to do that. We want you to kind of feel how practitioners in the industry really have to figure out how to get everything running together. And that's actually a view from trenches that you won't get if you don't get your hands really dirty and get everything done.
Right, and in the previous courses, both in the Cloud Computing Concepts courses and the Cloud Applications course, we gave you, in many cases, code templates and unit tests and things like that. Here, it's a lot more hands-off because this experience is meant to be a lot more closer to what you might encounter as an employee inside one of these companies that's trying to store and process big data. So we will give you specification documents, we will give you pointers, we will give you pointers to tutorials, but beyond that, you have a lot of flexibility and a lot of freedom in making design choices and reaching the goal that we set for you in the capstone.
One important part of this course, this capstone course, when we were designing it, was we wanted you to work on real-world data sets, you to gain experience on something that is real and that is valuable for you. So that's why we chose a data set, in particular airline information data set,
yeah.
to get some interesting questions and knowledge out of it.
Yeah. And with that airline transportation data set, we will give you a series of queries that you will need to execute. And you'll have a little bit of choice in there, and there will be more details in the specification document.
Right. So, of course, we are talking about distributed systems. And to get your hands dirty and gain experience with these distributed systems, you need distributed systems, right? A platform to run your code on. And that's why we have partnered with Amazon.
Right. And Amazon Web Services has been gracious enough to give some cycles to the students, and more information about that will be forthcoming soon.
So the last point I'd like to mention here is that in our previous courses, we had a lot of students enrolled. We had in the order of like 50,000 or more students enrolled throughout the courses. But you guys, now that you guys are seeing this video, you capstone people, you are the cream of the crop. You are the people who finished up all the previous courses. So we do expect a lot from you, and that's why basically we are giving you the design specifications, and we are hoping to get fully functional systems.
Right, and I'd only add to that the capstone is going to be challenging. It's going to be more challenging than you think it's going to be. So we highly encourage you to start early and start often, if that makes sense. But do start early, because before you know it, deadlines will creep up. And with that, all the best, and we will stay in touch online.